My name is David Gassner, and this is Java Essential Training. If you want to build apps for Android devices or desktop applications that run on the Java runtime environment, you'll need to know Java. I'll start by showing you how to install the Java Development Kit and how to get started with IntelliJ IDEA Community Edition. I'll introduce you to the basics of the programming language, including its data types, keywords, and best practices. I'll show you how to control program flow using conditional logic and loops, and how to store data collections in memory with the Java Collections framework. And since Java is an object-oriented language, I'll describe how it implements concepts like encapsulation, inheritance, and polymorphism. The goal of this course is to help you get started with Java so you can go on to build mobile, desktop, web, or other types of Java applications. This course is designed for software developers who want to program in Java. Java is used in a lot of different environments to create a lot of different kinds of applications. You can use Java to build apps for mobile devices running on Android and BlackBerry. You can build web applications using Java Enterprise Edition and its servlets and JSP or Java Server Pages architectures. You can program micro devices, including cell phone SIM cards, and you can create many other types of applications. But Java is not a universal programming language, and it's not used everywhere. Here are some things that Java is not. Java and JavaScript are not the same language, for example. JavaScript is an interpreted language that's used in web browsers and other dynamic environments. JavaScript and Java share the word Java, but they're not the same language at all. And if your goal, for example, is to build dynamic front-end web pages, you want JavaScript and not Java. Java is also not the language of choice to build iOS apps, that is, apps for use on the iPhone and iPad platforms. The popular languages there are Objective-C and the newer Swift. And you also don't use Java to build Windows Phone apps. For Windows Phone, you can use either Visual Basic or the more popular C#. Java is also not the easiest language in the world. It is an object-oriented language, and to master it, you need to understand object-oriented concepts. But it's not the most difficult language in the world either. One of its virtues is its consistency. Once you learn the rules of Java, how to think in Java, you can apply those rules across the board, learning new skills and picking up new libraries and APIs as you need them. As I mentioned, this course is designed for everybody who wants to develop software with Java, but because Java is an object-oriented language, I will be using a certain basic programming vocabulary. If you're not sure whether you're ready for this course, here are a few questions you can ask yourself to find out. These questions test your understanding of some basic programming terms. What is a statement in a programming language? And what is a variable? What is a function or a method? And what is a condition? If you feel like you can confidently answer these questions, then you're ready for this course. But if you'd like a little bit more information about programming fundamentals, you can find that information in some lynda.com courses. Foundations of Programming Fundamentals will answer those basic questions. And to learn the terminology of object-oriented programming, you can look at Foundations of Programming, Object-Oriented Design. You can either start with these courses and then go to this course, or you can jump right into this course, and then if you encounter terminology that you're not familiar with, you can jump to these courses. Either of these strategies should work as you start on your journey of learning Java. This course is accompanied by exercise files that you can use to follow along with the demonstrations. I've copied the exercise files to my desktop, but you can place them anywhere on your hard disk. The exercise files are organized by chapter. Within each chapter, you'll find a number of subfolders, one for each video for which there's a live demonstration. For those videos where I'm only showing slides, there is no subfolder. Within the subfolder for that video, you'll find a project folder. And for most of these folders, there's a source folder under that. and under that a series of Java package folders. You'll find the actual Java code under COM, Example, Java, and as you'll learn in the course, that's the equivalent folder structure to a Java package, a concept that's used to organize Java code. These projects are designed to be imported into IntelliJ IDEA. I'll show you how to do that using the most recent version of IntelliJ IDEA Community Edition, version 14.1.3. From the Welcome screen, I'll click on Import Project. Then I'll navigate to my exercise files folder, to the chapter folder, and to the subfolder for that video. Then I'll choose the actual project folder. Make sure that you don't choose any of the parent folders above this. This is the folder that you want to import. Notice that it has a source folder underneath it. That's what marks it. I'll click OK. Then I'll see a series of dialogues. On the first dialog, accept the default to create the project from existing sources and click Next. And then you can accept the project name. If you prefer to change the location, you can do that at this point, but I recommend keeping it the same. On the next screen, IntelliJ IDEA tells you that it's found your source files under the SRC folder. That's the standard location for IntelliJ IDEA projects. Keep on clicking Next until you get to this screen, and then click Finish. And that imports the project and creates a number of other files and folders that you'll need. You can then open the project from the project window, and you'll find the source folder there. And you'll see that the package directory structure has been flattened, so it's shown as just a package. And from there, finally, you can open the Java code. From here, if you want to get back to your folder in Finder or Explorer, you can right-click on the project and then choose Show in Explorer on Windows or Show in Finder on Mac, and that'll take you back to the exact same place. Notice that there's now a file with the .iml extension and a folder starting with a dot named IDEA. On Windows, you'll see this folder clearly, while on Mac, it'll probably be hidden. I'll go back to this step, and I'll run the application for the first time. The first time you want to run the code, you'll need to make sure you've opened the main class. That's the class that has the main method in it. And then click into that class. Then go to the menu and choose Run, and then Run again. Choose the item with the class name and click it, and that should run the class for the first time. That creates something called an edit configuration. From there, though, you can run by going to the menu and choosing Run Main, or, as I'll show you later, there's a toolbar that has a number of icons, and you can click this Run button. But again, you can only do that after you've run the application for the first time. So that's how to use the exercise files in IntelliJ IDEA. It's also possible to open these exercise files in Eclipse, although I won't be using Eclipse during the course. For example, I'll go to my exercise files folder, to 0405, and I'll use this project, Math. Now, I'm going to copy the location of this folder to my clipboard, and in Windows that's easy to do. You just click on the folder icon and then copy the string that appears. Then I'll go back to Eclipse, and I'll say File, New, Java Project. I'll set the name of the project to Math. Then I'll uncheck the option to use the default location, and I'll paste in the location of the project. I'll make sure that I'm pointing to the actual project folder and not to its parent folder. Then I'll just click Finish. Eclipse, just like IntelliJ IDEA, assumes that your source files are in an SRC subfolder. And from there, you can open your files and do whatever you need to do. So that's a look at how to use the exercise files, both in IntelliJ IDEA, which I'll be using throughout the course, and in Eclipse. Java has a long history. It started in 1991, when Sun Microsystems began something called the Green Project. The goal was to create a new portable programming language, one that could be used to create applications that could run on multiple operating systems without having to be recompiled or ported. The original name of the language was Oak, for a large oak tree that stood outside the windows of the developers' offices. but by the time the language was first released, it was renamed Java, supposedly because of the amount of coffee that the developers were drinking. Java was first released to the public in 1995, and starting then, the phrase write once, run anywhere was popularized. Again, the goal of Java was that you'd be able to write a program, and you'd be able to compile it once and then run it on Unix, Solaris, Windows, Mac, and other operating systems for which there was a Java virtual machine. Java evolved swiftly. In the early years, there was a new release about once a year. In 1996, Sun released the first complete Java Developers Kit, or JDK, supporting a broad range of application development tasks. Version 1.1 the following year saw improvements to the object-oriented nature of Java, with inner classes and Java beans, the JDBC API for talking to databases, RMI, or Remote Method Invocation, for distributed systems, and Reflection for improving the dynamic capabilities of the language. In 1998, Java was rebranded as J2SE, or Java 2 Standard Edition. The Standard Edition moniker distinguished it from Enterprise Edition, which was the framework for building large-scale web applications. The version number was Java 2, version 1.2. A little confusing, and the 2 after the J stuck around for many, many years. But the versions were incremented using point numbers, 1.1, 1.2, 1.3, and so on. Java 2 SE 1.2 included the Swing graphical API for building desktop applications, the Collections framework for managing multiple data elements, and new tools including the just-in-time compiler and the browser-based Java plugin to standardize the version of Java across the web. A couple of years later, J2SE 1.3 added new tools including the Hotspot JVM, a new version of the Java Virtual Machine, the Sound API, and improved debugging. In 2002, version 1.4 added new tools in the language. And then, in 2004, in a major milestone, J2SE 5.0 was released, known internally as 1.5. From this point forward, Java would be known as Java 5, Java 6, Java 7, Java 8, and so on, but internally, it still maintained the point versions. So even now, the most recent version of Java has a marketing tag of Java SE 8, but internally it's Java SE 1.8. Java 5 was a major change for the language. A new feature called generics was implemented that allowed you to strongly data type elements belonging to collections. Enumerations, variable arguments, and looping with for each were all improved. In terms of core language syntax, this was really the last major change. Everything else has been incremental, features that you could choose to use or not to use, depending on the kind of programming you were doing. In 2006, Java 6 appeared. It improved performance for database connectivity, improved graphical programming, and added other small features to the language. And after that, the pace of change slowed. From 2006 to 2010, Sun Microsystems released occasional maintenance releases, and so you'd have Java 6 maintenance release 10, 11, 12, and so on. But it took 4 years until a new major version came out. And then in 2010, Oracle bought Sun Microsystems and all of its assets, including the Java programming language. Oracle Corporation now manages Java, along with JCP, the Java community process that Sun began. And after Oracle purchased Java, the pace of change increased again. In 2011, we got J2SE 7. It included significant new syntax changes, listed here, and some other small-scale tools. And then, the most recent version as of the time of this recording was released in 2014. Java SE 8 implemented Lambda expressions, a new date-time API, and other syntax improvements. And we're expecting another version of Java down the road, Java SE 9. It's currently planned for release in September 2016. According to the current plan, it'll implement modularization of the Java runtime libraries And at one point, it included a plan for a new lightweight JSON API, but that's now come into question. We won't know for sure what's going to be in Java SE 9 until about 6 months before it's finally released. But for now, Java SE 8 is the most recent major version of Java for everything except Android development. For Android developers, you'll want to look at the features of Java 6 and Java 7. From the beginning, Java has followed some clearly stated principles. First of all, it's a simple, object-oriented, and familiar language. Its simplicity lies greatly in its consistency. Once you learn how to do one thing in Java, you know how to do it the same way throughout the language, because it never deviates from the way the language is architected. It's an object-oriented language, so once you understand the principles of encapsulation, inheritance, and polymorphism, and how those are implemented in Java, you'll have a much better sense of how to architect your applications. And for developers who've worked with C-style languages like C and C++, the syntax of Java is very familiar. Java was created to be robust and secure. Its robustness lies greatly in its object-oriented characteristics. Because you're designing everything as an object, everything has methods, or functions, and properties, also known as fields, that are members of classes. This lets you create your code in small chunks, and it makes it easy to debug and maintain your applications over time. Java was designed to be portable, so that you'd be able to compile it once and then run your application on multiple operating systems and processors. The language was designed to be high performance. The original version of the Java virtual machine wasn't as fast as C++ applications, but over the years, it's been improved enormously, and today Java applications run just as fast as, or sometimes even faster than applications built in C++. And finally, Java was created as an interpreted language. It supports multi-threading, and it's dynamic. Interpreted means that the application is compiled to a format that's interpreted at runtime, rather than being run directly as machine code. That's what makes the applications portable. It's multi-threaded, and it makes it easy to build applications that can do more than one thing at a time. And it's dynamic, in that it can change data types at runtime so long as those data types are compatible with each other. Let's talk about Java's runtime architecture. Again, it's an interpreted language. Your text-based code is compiled to bytecode rather than machine language, and that's what makes it portable between operating systems. Here's the software stack that's used at runtime. You start with the operating system. You can run Java applications on Windows, Mac, Linux, Solaris, and any other operating system for which there is a usable Java virtual machine. The Java Virtual Machine, or JVM, that you use most of the time will be the one provided by Oracle, that was originally created by Sun Microsystems. But there are other JVMs out there, including one provided by IBM, and one that's provided for Android by Google, and there are many others. On top of the virtual machine, you add the core runtime and additional libraries. The core runtime is sometimes called the Java class library. It's included with both the JDK and the Java Runtime Environment, or JRE. And finally, your application is compiled into bytecode, and that bytecode runs on top of all of those other layers. Let's compare Java to a couple of popular languages. First, C++. Java was originally created by C++ developers, and they had in mind improving the developer's lot. Here are some ways in which Java is different from C++. If you're a C developer, all of your code can run in C++ as well. The two languages are compatible with each other. That's not true for Java. Even though Java has syntax that's very similar to C and C++, its code is unique. It has its own rules and its own syntax. I've mentioned earlier that C++ is compiled to native machine language. And while that makes it very fast and gives it access to low-level functionality, it means that your application has to be recompiled for each operating system and processor that you want to target. Java is compiled to bytecode. Because C++ is compiled to native machine language, it allows direct calls to the native system. In Java, there's an interface called Java Native Interface, or JNI, referred to sometimes as Genie, that lets you call those native functions through the JVM. To use Genie, you have to create your own native code, typically with C++. C++ lets you write once, and then as long as you followed standard C++ syntax and libraries, you can recompile for each operating system you're targeting. Whereas with Java, you can write and compile once and then run anywhere. Java runs in a protected virtual machine environment, and again, you have to go through that Genie interface to make those low-level system function calls. And memory management is also very different. C++ requires explicit memory management, allocating and deallocating memory as you need it. In Java, memory is managed for you. There are also certain areas where C++ can do things that Java can't. C++, for example, supports multiple inheritance, while Java is limited to single inheritance, although you can implement multiple interfaces in Java. Let's also compare Java to JavaScript. Even though the names of these languages share the term Java, they're not really closely related. They share C-style syntax, but otherwise have very different purposes and very different principles. JavaScript is based on the ECMAScript standard, and there are many implementations of that standard, including JavaScript itself, a version of JavaScript that Microsoft has implemented, sometimes known as JScript, Adobe's ActionScript used in Flash, and many, many others. Java is compiled to bytecode, whereas JavaScript is not compiled at all. It's interpreted at runtime. JavaScript is the dominant programming language in web browsers. To run Java code in a web browser, you would need an additional plugin. In Java, you can call native functions through the Genie interface. But JavaScript, at least when executed within a web browser, runs in a security sandbox that doesn't allow it access to local resources. Both Java and JavaScript are broadly portable, Java through its JVMs, and JavaScript through broad implementation of the language in various browsers and other runtimes. Both Java and JavaScript use managed memory access, but they have very different inheritance models. Java uses a class-based inheritance model, while JavaScript uses something called prototype-based inheritance. Java is published in 3 distinct editions. The language itself is known as Java Platform Standard Edition, or SE. This is the core language and runtime environment. On top of that, you can add Java Platform Enterprise Edition, or Java EE. This is a standard for building industrial-strength web applications, and there are many JEE application servers out there, including some that are paid and some that are free. And Java Platform Micro Edition, or ME, is the standard for programming microcontrollers, sensors, and mobile devices. For example, the SIM card on most smartphones is programmed in Java. I've mentioned the terms JRE and JDK previously. The JRE is the runtime environment. In the past, the JRE was installed automatically on common operating systems such as Mac and Windows. Modern distributions of these operating systems come without the JRE, so it's up to the user to install it. But the JRE is free and can be downloaded from Oracle individually, and there are versions of the JRE for Windows, Linux, OS X, Solaris, and other operating systems. The JRE runs all Java applications on the desktop, and is also used at runtime in a JEE environment to run server-based applications. The Java runtime environment has a reputation for having security issues. It's very hackable, but Oracle does its best to keep up with these challenges through issuing regular updates. But it's up to the individual computer user or administrator to install these updates to make sure that their systems are secure. And again, mobile operating systems, such as Android, have their own distinct runtimes. They don't use Oracle's JRE. The JDK, or the Java Development Kit, is also available at no cost from Oracle. It lets you compile and package your Java-based applications and includes these critical command line tools in addition to many others. If you code and compile Java from the command line, you'll need to learn how to use these tools. But if you use one of the common Java IDEs, or integrated development environments, they protect you from having to know the details of how these command line tools operate. So that's a look at the principles and components of the Java programming language. In this course, I'm going to focus on Java SE, just the programming language. I won't be getting into Enterprise Edition or Micro Edition, but those are also critical elements of the Java ecosystem. All Java code is defined in classes. Each source code file defines at least one Java class that has the file extension .java. You can create these text files in any text editor, although I'll be using IntelliJ IDEA for most of this course. The compiler, javac, compiles your text-based code into bytecode that can be interpreted by the JVM, and then the Java command runs that code. Here's a classic Hello World application. The name of the class is main, and so it's defined in a text file named main.java. The first line is called the package declaration. Java classes are typically organized into packages. A package is a globally unique string that typically starts with your domain name in reverse domain order. So if my domain is david.com, I would start my package string with com.david to ensure globally unique identifiers. Then, if there's more than one class named main in an application, I can distinguish them using the package. Next is the class declaration. The keyword public means that this class is available to the entire application, and each source code file will contain one public class. The name of the class is main, that's its identifier, and it implements a single method, also named main. Notice that the method's identifier uses an initial lowercase character. A console application always has this main method. It always has the three key words, public, static, and void. Public means that the method is available to the entire application. Static means that this method can be called directly from the class definition rather than from an instance of the class. And void means that the method doesn't return any value. This required main method must also receive an array of strings as an argument or parameter. It must be an array of strings, but the name doesn't necessarily have to be args. You can name it anything you like. Finally, the executable code is placed within the main method. This code is printing the string hello world to the console, and it ends with a semicolon, which is like a period. It means that's the end of the statement. Here are some critical Java syntax rules. Java is case sensitive, and all identifiers must be unique within their scope. Because Java is case sensitive, though, these three identifiers, or variable names, are seen to be different from each other. First name in all lowercase, first name with camel case, and first name in all uppercase could represent three distinct variables or values. Also, in Java, whitespace doesn't affect how your code is interpreted. For example, in Visual Basic and some other applications, a line feed means that's the end of the statement. In Java, a line feed is just like a space and a tab character. All three of those types of characters are collapsed during the compilation process into a single bit of whitespace. And so it's up to you to indicate where a statement ends with a semicolon character. This code, for example, says, print this string to the console, and the semicolon character is required. Identifiers, or names of your classes, variables, and other components, can't use keywords. The Java language implements a whole set of keywords that you should learn about. Keywords like for, while, assert, and others can't be used as your variable names, and if you try to do that, the compiler will reject them. Again, names of classes, methods, variables, and so on are known as identifiers. And all identifiers must start with an alphabetical character or an underscore character. You can't use numbers, and you can't use other special characters. There are some very strong naming conventions in Java, and you should learn them and use them. Class names always start with an uppercase character. So my class starts with an uppercase M, but then can use other uppercase characters as needed to make the code readable. Methods, variables, and other members of a class always start with a lowercase character. So this would be a method called doSomething. It starts with a lowercase d, and it receives an argument or parameter that starts with a lowercase w. If you were to type these identifiers with uppercase characters, your code would still work, but other Java developers would wonder what you were up to. And constants are always all uppercase. There is no constant key word in Java. Instead, a constant is static and final. Static means it's a member of the class, and final meaning once it's been set, it can't be changed. This is a string constant named firstName that has a value of David. And because it's a constant, firstName is in all uppercase. These are some of the most critical syntax rules that you should know about as you start to program with Java, but of course I'll talk about many others as the course goes along. Even though Java is a compiled and statically typed language, it manages memory for you. Unlike languages like C, C++, or Pascal, you don't have to explicitly allocate and deallocate memory whenever you create an object. The garbage collector is a major feature of the Java virtual machine that makes a lot of this possible. I'm going to describe how the garbage collector works and how little attention you as the programmer need to give it. When you create a variable that references a complex object, that variable is stored in the fastest available memory. But the object it references is stored in heap memory. There are two kinds of memory, stack and heap. The stack memory is somewhat faster, heap a little bit slower, but heap is more dynamic. When you create primitive variables, depending on their context, they might be stored in stack or heap. But complex objects are always stored in heap. And as long as any variable references an object in memory, that object will be retained. It won't be eligible for garbage collection. So if you create a variable and it points to a string, a date, an array, a collection, or any other complex object, as long as that variable can be addressed in your code, the object will be available. When all of the references to the variable expire, it's eligible for garbage collection. But it's up to the garbage collector process to decide when to do that. Variables that you declare within methods or within code blocks expire with that scope. Here's an example. Let's say I have a method named changeString, and within the method I declare a variable named localVar. That variable's scope is the method itself, and as soon as the method is finished executing, that variable is dereferenced. The value, the object it references, might stay in memory for a little while, but you can't address it anymore. And so it's eligible for garbage collection. And the next time the garbage collector looks for variables it can remove from memory, it'll find that one, and it might decide to remove it and reclaim that memory for future use. You can also dereference variables using the keyword null, all lowercase. No matter what the scope, if I execute this code, where I declare a string, and then I immediately set the value of that variable to null, I've dereferenced the variable. And again, the object might still stick around for a little while, but you can't get to it. The garbage collector runs in its own thread. Depending on the kind of application you're running, and depending on the hardware, the amount of memory, and other resources it has, you might detect a garbage collector process kicking in. You'll typically see it happen as a little pause in execution. The nature of the garbage collector is that it can destroy dereferenced objects and reclaim their memory. But it doesn't have to do that. The garbage collector is a smart process. It runs on its own, and you as the programmer can't do much to affect how it works. For example, you can't force garbage collection. You can't say, I want you to remove this particular object from memory. The most you can do is run methods that request garbage collection, but there's no guarantee it will happen, and there's no guarantee that any particular object will be destroyed. It's important to know what happens in Java when the Java virtual machine runs out of memory. Throughout this course, I'll be talking about exceptions. An exception is a runtime error. It's something that typically causes an application to stop execution or crash. It's sometimes called a fatal exception. If the Java virtual machine runs out of memory, that can cause this exception, out-of-memory error, and it can cause the entire application and the virtual machine itself to come to a screeching halt. To prevent that from happening, you should understand a little bit about managing memory in Java applications. First of all, minimize the number of objects you create. Understand when objects are being created, and see if you can find ways of recycling or reusing objects instead of creating new ones. If you're not sure whether your application is having trouble, you can use these methods. First of all, the runtime class has a method called max memory, and it also has a method called total memory. This will tell you how much memory has been allocated to the virtual machine and how much is currently in use. And you can set these values when you start up an application with command line options. This option will set the initial heap size, and this one will set the maximum heap size. And finally, this will set the heap size for new objects. You can experiment with these values and look in the documentation for more information about memory management in Java. It's also worth understanding that these techniques will differ from one platform to another. The recommended settings in a Java Enterprise Edition environment will be very different from those on an Android device. So again, check the documentation, ask other developers in your particular community for suggestions, and keep on experimenting with your applications as you fine-tune memory usage. Java developers have many tools to choose from. You can, of course, write your code in any text editor, but an IDE or an integrated development environment can help you write your code more quickly and make it more bug-free. Most of the popular IDEs work on multiple operating systems, but there are some effective tools that are specific to Mac or Windows. Here are some editors and development environments that are specifically built for OS X on Macs. BBEdit and Text Wrangler are products from the company Barebones Software. BBEdit is a commercial product. It requires a paid license, while Text Wrangler is more limited but is free. They both support Java syntax coloring, function scanning, and a certain amount of autocomplete functionality. But it's not a specialist IDE for Java. Instead, these products are typically used by developers who are moving around among multiple languages but want to do all their work in a single editor. On Windows, you could use TextPad. TextPad is an advanced text editor. It does a lot more than Microsoft's own Notepad, and it's shareware. To buy a license, it's fairly inexpensive, but it isn't completely free. Once again, it's a general-purpose editor, but it has good support for external tools, so you can integrate the most commonly used Java tools into it, including Java-C and Java. JCreator looks a lot like TextPad, but it's specifically built for Java developers. There's a free Lite edition known as LE and a paid Pro edition. But most developers, as I mentioned, are using the top cross-platform IDEs. They all have free editions if they aren't completely free, and they all offer effective, fast, and powerful Java functionality. NetBeans was originally created by Sun Microsystems, and it's now owned and managed by Oracle. It has excellent support for Java Enterprise Edition development, and whenever Oracle creates new JEE features, it's a guarantee that NetBeans will support them. NetBeans also supports C, C++, and PHP, and some distributions include a bundled JEE server to make setup and running of advanced web applications as easy as possible. Many developers use Eclipse with a plugin called the Java Developer Tools, or JDT. When you go to the Eclipse Foundation at eclipse.org, you can download Eclipse distributions that are specifically for Java developers. There's one that's generically for Java, and one that's for Java EE. Eclipse is a free open source product, so most of what you associate with Eclipse will be free, but there are certain third-party plugins that are commercial and require a paid license. Eclipse comes in many flavors. There are distributions for many programming languages, including C++, PHP, and many more. And Eclipse is delivered for Mac, Windows, and Linux. And finally, there's IntelliJ IDEA, the IDE that I'll be using primarily in this course. IntelliJ IDEA is a commercial product, but there's a paid Pro edition and a free Community edition. I'll be using the free edition throughout my demonstrations. Once again, there are tools for many programming languages and platforms. And importantly, IntelliJ IDEA is the foundation of Google's Android Studio. Android Studio is essentially a plugin on top of IntelliJ IDEA. So, because many viewers of this course might be learning Java in order to build Android apps, I'll be using IntelliJ IDEA so you can get used to that environment, and those skills will directly transfer to working in Android Studio. There are other IDEs that I haven't mentioned here, including BlueJ, a student IDE that I will use later in this course, and JBuilder, a product that was originally created by Borland that at one time had significant market share. But the top cross-platform IDEs that I've mentioned, IntelliJ IDEA, Eclipse, and NetBeans, make up the vast bulk of the current market share for Java IDEs. In order to follow along with this course on Windows, you'll need to install the Java Development Kit from Oracle. Click on Java SE under Top Downloads. Then click on Download under JDK. In this list, locate the version for your copy of Windows, Windows x86 for 32-bit Windows, or Windows x64 for 64-bit Windows, and download the installer. I've already downloaded it to my desktop, and I'll fire it up by double-clicking on the installer icon. If prompted with a user account control dialog, click Yes. If you already have a copy of Java installed, you might see a prompt showing that it's being uninstalled. But then you can follow along with the rest of the prompts. I recommend accepting all default values. Notice the location of the installation folder under C:\program files \Java. You'll then have a subfolder that includes your version of Java and the update version. I'll be installing version 8, update number 45, the most recent version as of the time of this recording. It'll take a few minutes to copy everything over onto your computer. You're actually doing two installations, one for the development kit and one for the Java Runtime Environment, or JRE. When the JDK installation is complete, you'll see this prompt, and you'll see where the JRE is being installed, and you can click Next, and that will complete the installation process. When the installation is complete, close the installer window. Next, you'll need to set a couple of environment variables to make sure that the Java compiler and other command line tools are accessible no matter what kind of Java development environment you're using. Go to the Control panel. In the search box, type Environment. Then click on Edit the System Environment Variables. Click the Environment Variables button in the lower right corner. Next, set a new variable named Java_home. I've already created this variable, and I'll show you what it looks like. Notice the value of this variable is the actual installation folder for the JDK, or the Java Development Kit. Make sure you're spelling it exactly correctly. This is how some development environments will find the Java Development Kit. You'll also need to take this value and append it to your path variable. I'll cancel that dialog. Then I'll go down here and double-click on Path, and notice that I've added this value to the end of the path variable, but it's not just the installation folder. I've appended the bin subfolder because that's the folder that contains the command line tools. You'll add this value to the end, separated from the previous string with a semicolon character. After you've done all that, close these dialogs, and then go to a command prompt. Then at the command prompt, type Java-version. That tests the runtime environment, or JRE, and I see that I can reach the Java runtime environment, and it shows me the current version. Then, to test the JDK location, type Java-C. That's the compiler tool, and once again append -version. And you should see this output, indicating the version of the Java compiler. If both of these tests work, you've successfully installed Java and set up your environment variables so that you can run the Java tools from the command line or from any Java development environment. The default installation of Mac OS X does not include Java. You need to download and install it. To find out whether you have Java on your computer, Go to Terminal and type java-version. On my computer, I have Java 6. It reads as 1.6.065. On your computer, if you don't have Java installed at all, you might be prompted to go to a page on the Apple website. But for the purposes of this course, I want to use Java 8, the most recent version of Java as of the time of this recording. So, whether you already have Java installed, version 6, or you don't have Java at all, you'll want to go to the Oracle website, and from there click on Java SE under Top Downloads. Click Download under JDK, and then you'll need to accept the license agreement and download Java for Mac OS X. There's only a 64-bit version. Older Macs with 32-bit processors aren't supported. I've already downloaded the installer to my desktop, and I'll open it by double-clicking on the DMG file. I'm using Update 45 of Java 8. Then I'll double-click to start the installer package, and click through the prompts to complete the installation. It'll take a few moments to copy everything over into place. Once the installation is complete, you can close it, then go back to your terminal window and try typing Java-version again. And this time you should see version 8. It reads as 1.8 and then the update version at the end. Also confirm that you can get to the Java compiler. Type javac-version. And you should see an output showing the version of the compiler. If you see 1.8 and then an update version for both Java and Java-C, then you're ready to use Java on Mac OS X. It's also worth knowing where Java is installed. I'll go to a Finder window, and I'll select /library/Java. Under there, I'll go to the Java Virtual Machines subfolder. And there's my new Java 8 installation folder. It contains a folder named Contents, which has a folder named Home. And that's where the JDK is actually installed. The bin folder contains all of the command line tools, including Java, Java-C, Javadoc, and others. Once you know where everything is stored, you can then effectively set up your integrated development environment, such as Eclipse or IntelliJ IDEA. And I'll show you how that configuration is set up when I install the IDE later on. For most of this course, I'll be using IntelliJ IDEA, an advanced integrated development environment for Java developers from JetBrains. Click the download link, and that'll take you to this page. You'll find that there are versions of IntelliJ IDEA for Windows, Mac OS X, and Linux. And I recommend using the free Community Edition. This will give you coding tools for Java and for 2 JVM languages, Groovy and Scala. I've already downloaded the installer on Windows. If prompted with a user account control dialog, click Yes to continue. Then click through the prompts. Notice on 64-bit Windows that you'll be installing to C:\program files x86 because this is a 32-bit software package. I'm using version 14.1.3. If you're using a more recent version, you might see some visual differences. I'll continue through and accept all of the options and let the installation complete. When the installation is complete, I'll check the option to run the software immediately and then click Finish. At this dialog, I'll say I don't have a previous version of the product and click OK. And that'll take me to the UI theme dialog. I'll click Skip All and Set Defaults, and then I'll see the IntelliJ IDEA welcome screen. Before I can create new projects, I'll configure my Java development kit as an SDK. I'll click the Configure link and choose Project Defaults, Project Structure. And then I'll click on SDKs under Platform Settings. I'll click Plus and choose JDK to indicate that I'm adding a version of the Java development kit. Then I'll browse to my JDK folder. On Windows, that should be under C:\program files \Java. And then choose the subfolder for your version of the JDK. Be sure to choose the JDK folder and not the JRE folder. Click OK, And you should see that the name defaults to the beginning of the version number, not including the update number. You should see a listing of jar files that are a part of the Java runtime, and then there are tabs for source path, annotations, and documentation paths. I'll come back to documentation paths later. For now, just click OK, and you should be ready to create your first Java projects in IntelliJ IDEA. You can download the free community edition of IntelliJ IDEA from this website. Make sure you've selected the right tab for your operating system, and then click the Download Community button. I've already downloaded the installer to my desktop. On Mac OS X, just click and then drag and drop the IntelliJ IDEA binary onto the Applications folder. And after a few moments, it should be copied over, and you can then double-click the Applications folder and locate and start the software. If you have any trouble opening the software, you might have to upgrade one of the Properties files. I'll show you how to do that in a moment. The first time you open IntelliJ IDEA, you might see this dialog, asking you whether you want to import settings from an existing copy of the software. I'm selecting I don't have a previous version and clicking OK. That takes me to this dialog to customize the interface, and I'll click Skip All and Set Defaults. And that takes me to the Welcome screen. Next, I'll tell IntelliJ IDEA where my Java development kit is. It's known here as the Java SDK. I'll click Configure, Project Defaults, and then Project Structure. Then under Platform Settings, I'll click on SDKs. I'll click the plus icon and choose JDK. Then I'll browse to my Java installation folder. I'll go to Library, then Java, Java Virtual Machines, and I'll click on My JDK folder and click Choose. And that adds the JDK. There are also tabs here for source path, annotations, and documentation paths. The documentation path will initially be empty. Next, I'll go to Project under Project Settings, and I'll select 1.8, my new SDK definition, as the default SDK, and I'll set my project language level to 8, so that I can accurately look at lambdas, type annotations, and other new features of Java 8. Then I'll click OK, and that takes me back to the Welcome screen, and I'll be ready to create my first Java projects. For most of this course, I'll be using IntelliJ IDEA to demonstrate Java coding, compiling, and running Java applications. But I'll also be using a simple learning application called BlueJ. This is a teaching environment. BlueJ isn't suitable for full production work, but it's great for learning basic Java concepts, including object-oriented concepts. As shown in some of these diagrams, it'll visualize the relationship of Java classes to each other. There are versions of BlueJ for the major operating systems: Windows, Mac OS X, and Linux. There's even a version for Raspbian Linux, the version of Linux that's installed on Raspberry Pi computers. I won't go through the full installation process here because it's so simple, but I will say that if you're running on Windows, you only need the BlueJ installer. You don't need the combined installer because you should already have the Oracle JDK installed. And if you're running on Mac, make sure you download and install BlueJ using the correct version depending on which version of OS X you're running. I've already installed BlueJ on my computer, and just give you a hint of what's to come. A BlueJ project is a basic Java project, and I'll create a BlueJ project on my desktop, and I'll name it BlueJ Project. Then, to create a Java class, you click New Class, and type the name of the class, and click OK. Then you can double-click, and that'll open the class in your editor. I'll come back to BlueJ later on in the course, but as I've described, I'll primarily be using IntelliJ IDEA as we get started with Java programming. For my first Java programming exercise, I'll create a Java source code file using a simple text editor. On Windows, I can do this using Notepad, or any other text editor I like. If you're working on Mac and you don't already have a text editor installed, you might try Text Wrangler, a free text editor from Barebones Software. To declare a Java class, start with the keyword public. That's called an access modifier, and it means that the class I'm about to declare is available to the entire application. Then add the keyword class, and then the name of the class, which I'll simply call main with an uppercase M. All Java class names should start with an uppercase initial character. Next, add a code block consisting of a pair of braces. In most Java coding examples, you'll see the opening brace appear on the same line as the preceding keywords, and then the closing brace should go down on the next line and can align with the first keyword, such as public. Now, anything I declare inside this code block will be a part of the class. To run the class from the console, I need a method that's called main, and there are a few keywords I need first. First, the keyword public, which again is an access modifier. Then the keyword static. That's a keyword that means that this is a member of the class that can be called from the class itself as opposed to an instance of the class. If that doesn't make sense, don't worry. We'll talk a lot more about static versus member methods later on. Then the keyword void, which means that this method won't return any value. And finally, the name of the method, main. This is a required method name. All method names should start with an initial lowercase character, and that's how you can distinguish the identifiers, say, of a class named main and a method named main. Next is a pair of parentheses that declares arguments or parameters that can be passed into the method. The name of the method and its arguments make up the method signature, and the required main method signature receives an array of string values. We'll declare an array of strings with the keyword string with an uppercase S. That means it's a class identifier, followed by a pair of brackets, and that means there's more than one string. It's an array. The name of this argument can really be anything you like, but it's typically named args. I'll add the closing parenthesis for the end of the method signature, and then I'll add another code block, and I'll fix up the tabulation to show where the method starts and ends. Now, when I run this class, the Java runtime will look for the main method and run it automatically. Any code I put within the main method's code block will be executed. And I'll add a single line of code that looks like this: system.out.println for print line, and then I'll pass in a string literal value. That's a string wrapped in double quotes. And I'll set the string to hello from Java. After the closing parenthesis, I'll put in a semicolon. That's the end of the statement. Now I'll save my file. I'll press Ctrl-S in Notepad, or if you're working on Mac, you can press Command-S. Then navigate to the folder where you want to save the file. I'm placing it in the Hello World folder under the subfolder for the current exercise. I'm going to set the file name as main.java. The first part of the file name must match the class name, and it is case sensitive. So this value, main, for the class identifier, matches the beginning of the file name main here. And the file extension must be .java. On Windows, if you're working in Notepad, change the type to all files, and that'll guarantee that you don't add a .txt extension at the end. Then save the file. Now I'm ready to compile and run the Java class. I'll go to a command prompt. Now, switch to your exercise files folder. On my system, I'll go to the desktop, and then to exercise files, then to ch03, and then 0301, and finally the subfolder Hello World. On Mac, you can do the same thing, but use forward slashes instead of backslashes. I'll list the contents of the directory and show that main.java is here. If you're on Mac or Linux, use ls instead of dir. Now I'll compile the file. I'll type javac and then the full name of the file, including the Java file extension. And after a moment, the command prompt comes back. If you don't see any errors, that means that the file compiled correctly. and you can list the contents of the directory again. You should see a new file there called main.class. That's your compiled class file. Now I'll run the class. I'll type Java, and then the identifier of the class. When you're running the class, don't include the .java file extension. And I get back the string hello from Java. So I've created my first Java class using a simple text editor, and I've compiled it and run it from the command prompt. When you run a Java class from the console or a command prompt, the runtime looks for the main method, and you can pass values known as arguments into that main method as strings. For this demonstration, I'll use the main.java file in the arguments folder under the exercise folder. You can open this again with any text editor, and I'll open it as I did before with Notepad. When you run from the console, you can pass string values in, and they'll show up in this array of strings. You can address each item in the array individually using the name of the array, a pair of brackets, and an index or a numeric value. So for example, if I wanted to output a value, which is the first argument passed in on the command line, I would once again use system.out.println, and then I would use this expression, args, open bracket, 0, close bracket. The first item in the array has an index value of 0. Java always uses 0-based array indexing. I'll save that change, and then once again, I'll go to a command prompt. Then press Enter, and you'll go to that folder. So here's my main.java file, and I'll compile it with javac main.java. Then I'll run it with Java, main, and I'll pass in a value, the argument. Notice I'm passing in a single string without any spaces, and I output that value. Now I'll do the same thing again, but I'll put a space in, and this time I just get the first value, my, because the Java runtime is splitting up the values using the space character as a separator. If I want to keep those two values together as a single argument, I can wrap them in double quotes. So I'll bring back that command with the up arrow, then I'll put double quotes around the whole thing. And this time I get the argument passed in as a single value. Now, if I try to run the code but I don't pass in a value at all, watch what happens. I'll type Java main, and I get an exception. And it's a particular kind of exception, something called an array index out of bounds exception. I'll talk a lot more about how these exceptions work later on. But just know that if you have code that looks like this, that's expecting a value in an array, if you try to address it and that value doesn't exist, it'll cause an exception in your code, and your application will simply stop working. It's a fatal exception, and the application can't keep running unless you add a lot of other error-handling code around it. Java developers typically organize their classes in packages. A package is a unique identifier that goes at the top of the class declaration, but it actually matches a folder hierarchy. As you've seen, you can create your Java classes in a project root folder, also known as the base package, but to keep your classes well organized, you should start with packages from the very beginning. I'm going to open this version of my main class, which is in the Packages folder. Packages is my project root. And once again, I'll use a simple text editor. And I'm going to add a string at the top of the class declaration, starting with the keyword package. Now, you can use any string you like as a package identifier, but typically they're formed from domains, using reverse domain notation. So if your domain is example.com, your package would start with com.example. And that would match your organization or company's domain, but then you might add another string under that to make this unique to the application. So you start with package, the keyword, then the package string, and then a semicolon. Now, this file has to go in a matching folder hierarchy. So I'm going to close my text editor, and I'm going to create the folder hierarchy by simply creating the folders here. I'll create a new folder named com. I'll double-click into that. Then I'll create a subfolder under that called Example, and then I'll double-click into that and create another subfolder named Java. Then I'll open another copy of my Finder or Windows Explorer window. I'll come back to the Packages folder, and then I'll drag and drop my main class and place it in this Java subfolder. Then I'll open the file in a text editor and show that the package name com.example.java matches the folder structure com.example.java. So now I'm ready to compile and run the application. I'll once again go to a command prompt. So now I'm deep inside my folder structure. But Packages is the actual root folder of my project, and I want to get back there. I'll need to make sure I'm starting from the project root in order to properly compile and run the class. Now I'll compile with this code. I'll start with Java-C, and then I'll address the file using standard file syntax. I'll start with com, then a slash, then example, then a slash, then Java, then a slash, and finally the name of the file, main.java. That compiles. Then I'll come back to my file listing and show that main.class was successfully created. Then I'll go back to my command prompt. Now to run the file, I'll once again start with Java, not Java-C, and this time I'll use the fully qualified class name. A fully qualified class name includes both the package and the class name, using dot syntax. So that'll be com.example.java.main. And once again, I don't include the file extension. And there's my result. I'm successfully running the code. I'm once again getting an exception because my code is expecting an argument from the command line. So I'll press the up arrow to bring that command back and pass in an argument of my argument. And now all of the code runs successfully. So I've created my package folder structure, and I've added the package declaration to the top of the code to indicate where the class lives. Again, you don't have to use packages to organize your Java classes, but nearly all Java developers do it this way. So it's a good idea to get started with good class organization from the very beginning. As I've shown previously, you can code in a simple text editor and compile and run your Java classes from the command line. But most Java developers use integrated development environments, or IDEs, and I'll be using IntelliJ IDEA. In the IntelliJ IDEA welcome screen, I'll click Create New Project. I'll choose Java as the type of the project, and I'll set my project SDK to 1.8, the SDK that I defined when I installed IntelliJ IDEA. I'll click Next, and on this screen, I'll select the option to create a project from the template, Command Line App. That'll create a Java class that has a main method, just like the Java class I created previously. On this screen, I'll set the name of the project to IDEA Project. And then I'll change the project location. I'll browse, and I'll go to my desktop, to my exercise files, to the subfolder for this video, 0304. And then I'll append to that the name of the project, IDEA Project. So this folder will be the root folder for this project. Next, I'll set the base package. I'll use the same package that I used previously, com.example.java. When you do this through IntelliJ IDEA, you'll add this base package declaration to the Java code, but you'll also create the equivalent folder hierarchy to store the class. And then I'll click Finish to create the project. I'm told that this project file directory doesn't exist, and I'll click OK to create it and create the Java code. Now, if this is the first time you've done this in IntelliJ IDEA, your display won't look exactly like mine. Down at the bottom of the screen, you'll see a message saying Indexing, and you'll need to wait until that's complete before you follow along with the next steps. But when the setup process is complete, you should see this display with the project window on the left and the editor on the right. I'm going to maximize this window so we can see it more clearly. You'll also notice that I have line numbers being displayed on the left. Here's how I set that up in IntelliJ IDEA. I went to the File menu, and I chose Settings on Windows or Preferences on Mac. Then I went to the Editor category, to General, to Appearance, and I checked Show Line Numbers here and clicked OK. So here's exactly the same sort of code that I showed previously. I have a class named main, and it has a main method at line 5. And any code that I want to execute should go right here where the comment says, write your code here. I'll delete that comment, and then I'll output a message. As before, I'll use system.out.println, but I'll go through this slowly to show how IntelliJ IDEA will help you code. I'll type the beginning of the system class name, SYS, and I see a list displayed of all the different classes that start with that string. Then I can press Enter or Return to select it. When I press dot, I see a list of elements that I can choose from the system class. And this will start with a list of methods that are members of the class. But when I type out, I see that this is an object, something called a print stream. We'll talk about print streams much later in the course. But for now, I'll just select it and then press the dot character again. And now I see methods that are members of the out object, the print stream. And I'll start typing print and then ln, and I see that there are many versions of the println method that accept various values as arguments, booleans, characters, doubles, objects, and strings. I'm going to be using this version, so I'll press the down arrow a few times and choose it, and then I can type in a double quote character, and again, IDEA is helping me out by closing the quoted string with a closing double quote character, and I'll say hello from IDEA. Now, in IntelliJ IDEA, I don't need to explicitly save my code. It's being saved for me as I type. And I'm getting all sorts of hints and help as to how I can improve the code. Whenever you see this little light bulb over on the left, that indicates that there might be some help available. I'll be using this feature quite a bit later on in the course, but for now I'll ignore it. To run the application, I'll go to the menu and choose Run, and notice that I have two menu items that say Run, one that says Run ... and one that says Run Main. They're both enabled. That isn't always true in an IntelliJ IDEA project. If I had created a project that didn't come from a template, the first Run menu choice would have been disabled, and I would have had to choose this one, which creates something called a Run configuration. And when you choose that menu choice, you'll see a list of new or proposed Run configurations. I'll choose the main configuration, and after a moment, my Java code is compiled and executed, and the Run window opens at the bottom of the screen, and I see the output, hello from IDEA. So now I can make changes to my code and execute it again. This time, I'll create a string variable. I'll declare its data type as string, and I'll name it a string. And I'll give it a value of my first name. Then I'll add the semicolon at the end of the line. Then I'll output a string again. This time, I'll type sout, and that's an abbreviation that opens a code template that will expand to system.out.println when I press Enter or Return. So that's a shortcut that's available in IntelliJ IDEA, and similar shortcuts are available in the other popular Java IDEs. Then I'll enter a literal string of your name is, and then I'll add a plus character after the string, and then I'll start typing the name of the variable, a string, and I see that IntelliJ IDEA knows that that variable exists, and I can press Enter or Return to select and autocomplete it. And once again, I can run my code. Now, to run the code this time, I'll open a toolbar that will appear at the top of my workspace. I'll choose View, Toolbar, and now I can run my code by clicking on the Run button on the toolbar. And then I see the output, hello from IDEA, your name is David. You can run your code from the toolbar, from the menu choice, or by pressing the associated keyboard shortcut, which you'll find on the menu. So now you know how to create a brand new project in IntelliJ IDEA, and these are the projects that we'll be using for most of the course. Before we continue with the details of the Java programming language, let's take a little tour of IntelliJ IDEA. I'm going to import an existing project from the exercise files by clicking the Import Project link on the welcome screen. And I'll navigate to the IDEA Tour folder under 0305, the folder for this exercise. This is the project root. Under that, there's an SRC or source folder, and that contains my root or base package, com, example, Java, and that contains my main Java file. I'll select the project folder and click OK. Then I'll click through the rest of the screens and accept all of the defaults. I'll accept the project name matching the current folder name. I'll accept the source folder as the folder containing my Java source files, and I'll click Next a few more times and then Finish. And that imports the current project. Now I can find my files by going to the source folder, and I'll see that my base package is displayed as a single string. I don't need to drill down through all the individual folders. And I can double-click to open my main Java file. By default, the project window is shown with the project view, but there are other views available. The Packages view simplifies the view enormously, eliminating the display of a lot of folders and going right to the base package and its contents. The Project Files view goes in the other direction, showing everything, including an IML file that's created when you import the project that defines a lot about the IDEA project itself. The Problems view is useful when you're trying to figure out what's wrong with your Java code, and there are other views available as well. For the most part, I'll be working in the Packages view. It makes it easy to see just the files I'm interested in for development work, and I'll only have main.java open initially. There are many other windows available. If you move the cursor to the lower left corner and just hover it over that little icon, you'll see a list of available windows. For example, the project window is already open, but there's also something called the structure window. The structure window will show you the contents of your current class, and you can click to go to a particular method or other declaration very easily. If you click on that icon, you'll see links appear along the left side, the bottom, and along the right that let you get to certain key windows. You can also get to various parts of your project by clicking on the links below the toolbar. So for example, if I double-click on Java, that takes me to that package. And if I double-click on the project icon, I'll go back to the root folder of the project. If you're in the root folder and you don't know where your current file is in your folder structure, you can click on this link, known as Scroll from Source, and the cursor will open the appropriate package and jump to the current class file. And that's an easy way to get to where all your Java files are. There are many other ways to speed up coding in Java using IntelliJ IDEA, but I'll show you many of these tricks as we continue learning the Java programming language. Although I'll primarily be using IntelliJ IDEA for most of this course, I'll also be using BlueJ later in the course, so I'll show you now how to create a new project in BlueJ and how to create Java classes and a bit of code and how to compile and run. I've opened BlueJ and I'll select Project, New Project. I'm going to place my project in the 0306 folder under the Chapter 3 folder of the exercise files. And I'll name the folder BlueJ Project. And I'll click Create. The BlueJ Project design window shows a single file, and if you double-click it, you'll see that it's the project README file. A new project in BlueJ doesn't have any Java classes yet. I'll close that window, and then I'll click the New Class button. And as I've done previously, I'll name my primary class Main with an uppercase M. Notice you can create a number of different kinds of files, including classes, interfaces, enums, and others. That shows an icon for the main class. I'll double-click that, and I open up an editor window. and I'll maximize this window so I can see all of the code. Your window might look different than mine. Again, I've turned on line numbering, and I've set a particular font size. In a default class in BlueJ, you'll see the same public class declaration here, but you'll also see a bunch of comments. Comments in Java that start with /*** are JavaDocs comments. Text within those comments will be extracted to documentation when you use the JavaDoc tool, and we'll talk about that much later in the course. Within the class, there are declarations of variables, known as fields, of constructor methods, and of simple instance methods. Again, if that vocabulary isn't familiar to you, we'll talk about all of it later. One thing you don't see here is a main method that can be executed when you run the class. So I'm going to add that main method here. Now, in BlueJ, you don't get much help in coding. You kind of have to do it all yourself, similar to using a simple text editor. So as I did earlier, I'll type public, static, void, main. I'll pass in an array of strings, known as args, and then I'll set up my code block, and within the main method, I'll say system.out.println, and then I'll output hello from BlueJ. And I'll finish the statement with a semicolon. Next, I'll compile, and you do that very simply by clicking the Compile button at the top of the window. And if everything works okay, you should see this message: class compiled, no syntax errors. If you make an error, for example, I'll eliminate my closing semicolon and click the Compile button, you'll see a message indicating what's wrong, and the code that has the problem will be highlighted. I'll put the semicolon back in, and I'll compile again. And I see that I don't have any syntax errors. And now I'll close the editor, and that takes me back to the project window. To run the code, I'll right-click on the main class, and I'll choose the main method. I'll be prompted for arguments. I don't need any arguments for this example, so I'll just click OK. And I see my output, hello from BlueJ. Now I'll take a look at the structure of the folder that was created. I'll go to my exercise files folder, and I'll drill down to the folder that I just created, BlueJ project, and I'll see that I have my main class here, and I have the compiled class file and the README file. The other two files, package and main.ctxt, are used to manage the BlueJ project itself. They don't affect the behavior of the Java application. So that's a simple introduction to BlueJ. Again, this is not an environment like IntelliJ IDEA. IntelliJ IDEA can be used to build complete production applications. BlueJ is purely for learning, but we'll come back to it later on when we talk about object-oriented programming and how classes can be related to each other in various ways. When you're learning Java, you'll need access to the documentation. You need to learn the core of the language, its basic syntax, but a lot of working with Java is about working with the runtime library, the set of packages and classes that are provided with the JRE and the JDK. You can get to a certain amount of documentation from within IntelliJ IDEA very simply. For example, if you want to learn about a particular class, you can click into the class name and then press a keyboard shortcut to bring up the quick documentation. It's Control-Q on Windows and Control-J on Mac. That opens up a version of the documentation that will tell you the most important things about the class, but it won't tell you all of the details. I will point out that if you want to increase the size of the font in this window, click on the gear icon, and you can drag to increase or decrease it. In order to get to the full documentation, you'll either need to get to it on the web or by downloading it from Oracle and installing it locally. I prefer getting it from the web. This diagram will show you elements of the documentation. At the top level, there's a link to the core documentation about the language itself, including the Java tutorial. But there are also links in this diagram to all of the elements of the Runtime API, So for example, if I wanted to learn everything about how to use the compiler, Java-C, I could click on that link. And if I wanted to learn, say, about web services, I could click here. If you want to download the full API documentation, you can go to this page, and you can download the full documentation for the most recent version of Java. But again, that's a large download, and since I'm almost always connected to the web when I'm doing my development work, I'll use the API docs that are available there. Now, in order to integrate this into IntelliJ IDEA, I'll copy this URL to my clipboard. Then I'll go back to IntelliJ IDEA's welcome screen. And then I'll click Configure at the bottom and choose Project Defaults, Project Structure. Under Platform Settings, I'll choose SDKs, and I'll make sure that I've selected the JDK that I'm using most frequently. I'll click on Documentation Paths. Then I'll click the plus icon to specify a URL. You might see the correct URL appear automatically, but if you don't see it, you can paste the string that you previously copied. Then click OK. Now IntelliJ IDEA knows how to link the documentation to my code. I'll reopen my project, which is my documentation project from the 0307 folder. Then I'll click into the name of a class, and I'll press Shift F1. And that's the same keyboard shortcut on both Mac and Windows. And I'll get to the full documentation for that particular class. Within the documentation, I can see lists of the methods that belong to the class, and all of the other elements that are members of the class. This will work on all class names. I'll go to the string class, and I'll press Shift F1 again, and there's the documentation for the string class. So I recommend setting up the documentation in IntelliJ IDEA right from the beginning. It'll be enormously helpful as you learn the details of the core Java API. As with nearly all programming languages, Java supports the use of variables to store data in memory. There are two major classes of variables or data types in Java, known as primitives and objects. Primitive variables or data types are used to store numbers, individual characters, and Boolean values. They're stored in the fastest available memory, so you can get to the data as quickly as possible. Data type names for primitives are all in lowercase, and that's how you can distinguish them from complex object data types which always have an initial uppercase character. Most of the simple values you might store in Java code are primitives, but one data type that's absolutely not a primitive is a string. That's a complex object. All variables in Java, whether primitives or objects, must be explicitly data typed when they're declared. Java is a statically typed language, and that distinguishes it from dynamic languages such as JavaScript or Python. All variables must have their types declared. Here's a classic declaration. Int myvar equals 5, semicolon. The first part of this is the data type. It's saying this is an integer value, and once the variable is set as an integer, it can't change. In JavaScript, for example, you could start off with something as a number, and then you could reset its value to a string, and it could change at runtime. In Java, you can't do that. And that's because the compiler looks at this declaration and allocates memory for you, based on the data type that you declare. The next part of the declaration is the variable identifier or name. Java naming conventions require that variable names or identifiers always start with an initial lowercase character. And then you can use camel case, using uppercase characters in the middle of the name to distinguish certain names. In fact, certain IDEs, including IntelliJ IDEA, know how to read camel case. They do spell checking to make sure you don't type something very badly, but they know how to read variables as individual names based on where you place the uppercase characters. Finally, the value is placed on the right side of the assignment operator, the equals operator. The first two parts of this declaration are required. You could simply say int myvar and finish the statement with the semicolon, and that would be establishing the variable, but not explicitly assigning its initial value. If you want to assign the initial value, you just add the equals operator and the initial literal value you're assigning. Here are the primitive data types for numbers, starting with the smallest amount of memory and going to the largest amount of memory. All primitive values are signed, meaning that their ranges extend from negative to positive numbers. The byte data type stores 8 bits of memory. Its minimum value is negative 128, and its maximum is positive 127. You also have short, int, and long integers. Each of them takes an increasing amount of memory and has an increasing range. The most common of these data types that you'll see is the int. It's a 32-bit value, and its range goes from negative 2 billion to positive 2 billion. If you need to store very large integers, you can use the long data type instead. There are 2 data types that you can use to store fractional values: float and double. Float is a 32-bit value, and double is a 64-bit value. Once again, they both support minimum and maximum values in the negative and positive ranges, and you can look at the Java docs to see the exact values. Double values tend to be used most commonly. They give you the largest range and the highest level of precision. Each primitive has something called a helper class that's a part of the Java runtime library. Each of these classes can be used for converting values from one primitive data type to another and to format values using very simple logic. Here are the helper classes. The primitive byte value can be helped by the byte class. Notice that the name of the class always starts with an initial uppercase character, and that's how you can distinguish the class name from the primitive data type name. The helper class for the short is short, and the helper class for int is integer. And here are the others: long for long and float for float. In fact, for most of the primitive data types, their helper classes are exactly the same name, but with that initial uppercase character, and where there's a difference is in the integer, where the primitive is int and the helper class is integer. Here's an example of how you might use a helper class. Each of the helper classes is a member of a package called java.lang. Just like your own code, Java classes in the runtime library are organized in packages. All classes that are members of the java.lang package are available to you always without you having to add any special declarations. The double class supports primitive double values. Here's an example of declaring a double value. The first part is double, the data type. The second is the variable identifier or name, double value. And the third part is the literal value that I'm assigning it. Notice the letter D at the end. This is saying that this value, which could be interpreted by the compiler as either a float or a double, is explicitly set as a double. You'll see the use of these alpha characters on all numeric literals where the compiler can't figure it out on its own. So now I have a value called double value, and I want to convert it to another primitive type. I declare an instance of the double class and pass in the primitive value. Now I have a helper object representing that value, and I can get a byte from the object's byte value method. If necessary, this method will truncate any fractional values. I can also now get equivalent values cast as other numeric types. To cast the number to a string, you can use the helper object's toString method. All Java classes have this toString method, which is in charge of converting the object to some sort of string. The toString method of the double helper class converts the double to a simple string value. All numeric primitives have default values, and they always default to a value of 0. Here's some code where I'm declaring a variable named myInt, data typed as an integer or a 32-bit value. I don't have an assignment at the end of the declaration. And then I output that value as a part of a string, starting off with a string literal of the value of myInt is, and then appending or concatenating the int value. Because it defaults to 0, the output will look like this. The value of myInt is 0. And that's going to be true of all numeric primitives, starting from byte, going all the way through double. So that's a brief look at how to declare variables with primitive data types, and a little bit about primitives and their complex helper classes. In the next video, I'll show you how to declare some primitive variables and output their values to the console in IntelliJ IDEA. You can represent numbers in Java as either primitive values or as complex objects. I'll show you how to represent them as primitives here, and then show how to use helper classes to get information about numeric values. I'm working in the project Primitive Numbers. It has two classes named main and max values. Both of these classes have a main method, but no executable code. In the main class, I'll add code to the main method, and I'm going to declare 6 variables, each using one of the primitive numeric data types. I'll start with a byte that I'll name b and assign it a value of 1. Then I'll create a short integer. I'll name that sh, and I'll give that a value of 1 as well. Then an int, a 32-bit integer. I'll name that I and give it a value of 1. And then a long integer with the type long. I'll assign that a name of L and give it a value of 1 as well. Notice all of these integer types are using a literal of 1. The compiler looks at the value of 1 and always starts with an assumption that it represents the smallest range and the smallest amount of memory, a byte. But then when you declare the type, it upcasts the value. If you want to be explicit with the literal, that is, if you want to say this is a 1, but it's a long integer, you need to add an alpha character after the numeric. For a long, that would be the letter L. Technically, you could spell that with a lowercase l, but it's easy to confuse that with the number 1, so typically developers use an uppercase L. You can do the same thing with floats and doubles. I'll declare a variable with the type of float, I'll name it f, and I'll assign it a value of 1f. Notice I'm using a lowercase f here, and you could use an uppercase f, but developers typically use lowercase for floats and doubles. And I'll assign a double value named d, and I'll give it a value of 1d. Now I'll output those values to the console. I'll use the sout code template, and I'll output a value of byte, and then I'll append to that the value b. Then I'll run that code. I'll go to the menu and choose Run, and then Run again, and I'll choose the new Run configuration for the main class. And in the Run window at the bottom of the screen, I see byte 1. Now, I'm going to duplicate this line of code a few times. I'll copy the line of code to the clipboard, then paste it in 5 times. I'll change the label for each of these outputs to one of the data types. And then I'll change the values that are being output to match the labels. Now, because I've created my run configuration, I can run the code again just by clicking on the Run button on the toolbar. And I see all of the values output, from byte through double. Notice for the 4 integer types, I only see the number 1, but for the float and double, I see .0. Those have been cast as the appropriate types. Now let's take a look at how to use helper classes. I'll go to the max values class, and I'll add code in its main method. I'll declare a byte value named b, and this time I'll assign it a value of 127. Then I'll output that value with byte colon, and I'll append the variable. I'll run this code by once again going to the Run menu and choosing Run, and this time I'll create a new run configuration for this class. And I see the value byte 127. Next, I'll increment the value by 1 with the expression b++. The ++ operator means increment by 1. And then I'll copy and paste the line of code that outputs the value. And then I'll run the code. Notice what happens. 127 is the maximum value of a byte. And if I try to add one more, it wraps around, and now it has the minimum value for that data type. To solve this, I'll wrap this bit of code where I'm incrementing the value in a conditional block. I'll use an if statement. I'll type if, and then press enter or return, And then I'll say if b is less than byte.maxValue. Then I'll add a code block, and I'll move this bit of code into the code block by cutting it and pasting it. Let's pick apart this line of code. The if statement is pretty obvious. It's asking the question, if this condition is true. Then there's a Boolean expression wrapped in parentheses. The expression starts with the name of the variable b, then the less than operator, then byte.maxValue. Byte with an uppercase B is the helper class for byte values, and it has a constant or a static field named maxValue in all uppercase that represents the largest value that this data type can have. So I'm saying only increment the value if the value of b isn't already at the max value. Then I'll run the code again, and this time the byte stays at 127 because this line of code is skipped. You can try the same sort of operation with all of the different primitive numeric data types. Set a value, check to see whether it matches the max value or is less than the max value, and if it isn't, then try incrementing it. Or try incrementing anyway and see what happens. If you exceed the maximum value with a primitive data type, you'll always wrap around to the minimum value, and that'll be true for all of the primitive data types. Primitive numeric types are incredibly useful for storing single values in memory, but specifically double and float types aren't entirely precise. That's because the way they're stored in memory doesn't map exactly to the value. For example, a double value is supposed to take 64 bits, but Java doesn't use all 64 bits. It only stores what it considers the important parts of the number. So you can see some pretty odd things when you start adding values together and then outputting the result. In this project, currency, I've opened the main class, which has a declaration of a double value with a value of .012. I'm going to declare a second double value that I'll name pSum for primitive sum. And I'll calculate it by adding value together 3 times, with value plus value plus value. Now that's pretty easy to figure out. 3 times 0.012 should be 0.036. But now I'll output the result. I'll use sout again and expand that to system.out.println. Then I'll put in a label of sum of primitives, and then I'll append to that pSum. And I'll run the code. And I get this result. Sum of primitives equals 0.036, and then a bunch of zeros and a 4. So clearly, the value I think I'm storing isn't exactly what I'm storing. And as I start adding values together, it can get more and more imprecise. And if I then store that value in a database and base other calculations on that, I can cause all kinds of problems. So to fix this, Java provides a class called Big Decimal. There are actually 2 of these classes. There's one called Big Integer and one called Big Decimal. But Big Decimal is specifically designed to take care of this precision problem. To use Big Decimal on a number, first you need to convert the number to a string. I'll declare a string value that I'll call strValue, and I'll use the double class. That's the helper class for double values, and I'll call its toString method and pass in value. Then I'll output the value with strValue, and I'll append that variable. And I get an accurate representation of the value. Now I'll take that string and feed it into an instance of the Big Decimal class. I'll declare Big Decimal. I'll type the beginning of the class name and then press Enter to select it. Notice at the top of my code, a new import statement is added. I'll be talking about imports later on, but what's important to know now is that the classes I've used so far, like string, double, and so on, are members of a package called java.lang. That package is always available to your code. But when you want to use classes that are members of other packages, such as java.math, you need to explicitly import them into your code. So I've declared the Big Decimal type, and I'll call this Big Value, and I'll instantiate the object with the keyword new, and then the name of the class again, and I'll pass in the string, str value. Now I've wrapped the number in a complex object, and I want to create a sum again. I'll once again create a big decimal object, and I'll call this one bsum for big sum. And here's how I'll add the values together. I'll start with big value, and then I'll call a method of that object called add. And I'll pass in big value again, and the add method returns a new big value object, so then I can simply call the add method again and pass in big value again. And now bsum will be the result of two addition operations. Then once again, I'll do some output. And this time I'll say sum of big decimals, and I'll append to that bsum.toString. You can't just pass in bsum as an object. It won't be interpreted as a string the way you want it to be. So instead, you call the toString method. And here's the result. The sum of adding the primitives together was imprecise. But after taking those values and turning them into strings, and then wrapping them in big decimal objects and adding them together again, I see that the result is accurate. This is especially important when you're dealing with currency values, where precision is absolutely critical. When dealing with money, you can't afford to have extra little bits of values because eventually they'll all get added together and your results will be incorrect. But using big decimal to wrap those numbers in your Java code can make sure that your calculations come out right every time. You can make copies of and convert numbers to different types. In this example, in the Converting Numbers project, I have one line of executable code. It's declaring an integer value named int_value1 with a value of 56. If I declare a second integer value with int_value2, and I say assign the value of int_value1, I now have two copies of the value. When you're working with primitives, you're always making a copy of the value. You're not creating a reference to the original value. So now, if I want to output the value with system.out.println, I'll say the second value is, and then I'll append the new value. Then I'll run the code, and I get the second value is also 56. But let's say that I wanted to take that integer and turn it into a long integer. Here are the rules. When you're converting from a type that uses a smaller amount of memory to a type that uses a larger amount of memory, that's called widening the type. When you're going from a larger to a smaller, that's called narrowing the type. Widening the type is automatic. There's no risk of losing data when you do that, so you don't need any special syntax. So I'm going to say long value1 equals int value1. And I don't see any errors as a result of that. Then I'll take this line of code, and I'll duplicate it, and I'll cut and paste the new version down here. Then I'll change the label to the long value is, and then I'll change the variable that I output to long value1. And here's the result. I see the long value is 56 also. But now let's see what happens if I want to take an int value and turn it into a short value. I'll declare a short, and I'll say short value1 equals int value1. I see an error indicator. And if I move the cursor over the little light bulb, I see a hint. It offers to cast this value to a short value for me. If I choose that, I see this syntax. The new data type wrapped in parentheses before the original value means treat that original value as the new type. And again, I'm narrowing the value to the new type. Now, there are risks here. If the original value is compatible with both types, as it is here, then this conversion will work fine. So I'm going to take this line of code, and I'll copy and paste it down here. And I'll say the short value is, and I'll change the value that I'm outputting. And I'll run the code, and I see that the short value has the same value as before. But now let's see what happens if I take a value of one type and I try to narrow or convert it down to a type that can't handle that number. It's not in that new type's range. Now I'll declare a byte. A byte has a range from -128 to +127. I'll name this byte value, and I'll assign it int value 3. Once again, IntelliJ IDEA tells me I have to add casting syntax. Here's a keyboard shortcut for this kind of operation. I'll hold down the Alt or the Option key and press Enter. And once again, I get the menu that shows up if I click on the light bulb icon. And I'll choose Cast to Byte. And now let's see what happens if I output the byte value. I'll paste in my output string, and I'll say the byte value is, and I'll change the value I'm outputting to byte value. And this time I get the byte value is 0. So essentially the conversion fails. I've lost data. So this is a great demonstration of the difference between widening and narrowing from one type to another. Going from a larger memory type to a smaller memory type is narrowing, and you're always at risk of losing data. And that's why that special syntax is required. Let's do one more example. This time I'll create a double. I'll name it double value, and I'll give it a fractional value of 3.99999, and so on. And I'll add the letter D after the string, so I'm absolutely clear that I'm working with a double value. Now I'll create an integer value, and I'll call it int value 4, and I'll assign it the value from double value. Once again, I get the error indicator, and I'll press Alt or Option and the Enter key, and choose Cast to Int. Then I'll output, and I'll output int value 4, and run the code, and this time what happens is that the value is truncated. I lose the fractional values, because an integer can't have fractional values. Once again, I'm narrowing from one primitive type to the other. So the rules are, whenever you assign one primitive value to another, you're making a copy, not a reference, and if you want to narrow from one type to another, you must add explicit casting syntax. Java supports the standard mathematical operators that you expect to see in all programming languages, but it also supports more complex operations using a special class called math. I'm working in the math project now, and I've started by declaring two integer values, and I'll add them together using code that's pretty intuitive. I'll declare another integer, and I'll name it result1, and I'll get its value by adding int value 1 and int value 2 using the plus operator. Then I'll output to the console, and I'll use a label of addition, and I'll append my result, and I'll run that code, and I'd get back an expected result. Now I'm going to copy and paste these lines of code 4 times, and I'm going to use 4 other operators. Then I'll change the operators that I'm using. I'll use the subtraction operator, the multiplication operator, the asterisk, division, which is a /, and remainder, which is a % character. And then I'll change the labels to match the operators. And I'll run the code. For the first 3 operations and for the last one, I get back the expected result. Addition, subtraction, and multiplication are exactly what you expect to see, and the remainder, again, is what you expect. But division isn't quite right, and here's why. Whenever you do a mathematical operation, the returned result will be a data type that matches the widest data type of any of the parts. So if I start with 2 ints, I'll get back an int. If I start with 2 doubles, I'll get back a double. But if I start with a double and an int, I'll still get back a double. To do a fractional operation, where I'm expecting a fractional value back, I have to start with double or floating values. So I'm going to add casting syntax here. So I'll say that this is a double value instead of an int value. I get an error indicator, and I'll press Alt or Option and the Enter or Return key, and in my list I see cast to int. That's not what I want to do. I started off with an integer. Or I see change variable result 4 to double. That's what I want. I'm saying I know I'm going to be getting back a fractional value, so I'll set the data type appropriately from the beginning. I'll run the result, and now I get back a result that I expect. And typically, I'll do the same thing when I'm using remainders as well. I still get back 14, but now it's 14.0. So those are the operators and setting your data types correctly. As I mentioned, you can also do complex operations using the math class. The math class is a member of the java.lang package, so you don't need any special imports or other notation to use it. You simply start off with the word math with an uppercase M because it's a class identifier, and then the method that you want to use. Let's say, for example, that I want to round a value. I'm going to declare another value. This one will be a double, and I'll give it a negative number of 3.99999. Now I want to round that value. There's a method in the math class named round, and it returns a long value. So I'll declare a long value that I'll name rounded, and I'll call math, and when I press period, I see a list of all the different methods that are available. I'll start typing round, and I see that there are two versions, one to round a double and one to round a float. I'll use the double version, and I'll pass in my double value. Then I'll output the result to the console. I'll start with a label of rounded, and then I'll output the variable rounded. And when I run the code, I see that the rounded value is -4. The round method has rounded to the nearest integer value, which in this case is 4. But let's also say that I want to take that value and make it absolute, that is, always a positive value. So this time I'll declare a double value, and I'll name it ABS value, and I'll call math.abs. Notice that there are a number of different versions of this method for various primitive numeric data types. I'll choose the one that accepts a double, and I'll pass in double value, and then I'll output to the console with a label of absolute, and I'll append the returned value, ABS value. And I get back a positive 3.99999. The math class supports many other operations. Check the documentation for everything it's able to do. I'll place my cursor in the name of the class and press Shift F1, and that takes me to the documentation for the class. If you see a little menu pop up showing different sources of the help, you can choose either one. Then I'll click Method, and that takes me to a list of all the different methods that are members of this class. Notice that the different methods return different data types, depending on what kind of operation they represent. But they're all static, meaning that you call them directly from the class definition, as I have here with math.round and math.abs. You don't need to create an instance of the math class to call these methods. The math class and the built-in mathematical operators let you execute whatever mathematical operations you need to on primitive values. A variable marked with the Boolean data type can have a value of either true or false. I'll demonstrate this in the Booleans project. Within the main method, I'll declare two variables, and I'll start with the keyword Boolean, all lowercase. That means this is a primitive variable, not an object. I'll name the variable b1, and I'll assign it a value of true. Then I'll create another Boolean variable, and I'll say that that one is false. Now I'm going to shrink down my project window to eliminate some flickering that's happening. Then I'll add some output to the console. I'll start with a string of the value of b1 is, and then I'll append the value b1. I'll duplicate that line of code and change both the label and the value, and then I'll run the class, and I get the expected output. The values of the primitive variables b1 and b2 have been translated to equivalent strings. So true gets a string of true, and false gets a string of false. All primitive variables, as I've mentioned previously, can have default values. So if you declare them, but you don't assign their values, a Boolean will always start off as false. If I try to demonstrate this within the method, it won't work. I'll get an error, because local variables must be initialized. But you can also declare a variable outside the method as a member of a class. I'll place the cursor after the class declaration and start with the keyword static, and then the data type, and I'll name this new variable bdef. I've declared it, but I haven't assigned its value. It's dimmed out right now because I don't have any references or other uses of the variable. But now I'll come back down here, and I'll duplicate my output code again, and I'll change the label and the value that I'm outputting. And I see that the value is false. Again, that's the default value. You can take any value and reverse its value by adding an exclamation mark. That's called the negation operator in Java. I'll create another variable that I'll name b3, and I'll give it a value of negation b1. So I'm reversing the value of b1. It's starting as true, and I'm changing it to false. I'll get some code to output the value, and I'll change the label and the value I'm outputting, and there's the result. b1 was true, and b3 is false. In addition to the keywords, you can also create Boolean values from expressions by comparing values to each other. I'll create an integer that I'll name I1, and I'll give it a value of 0. Then I'll say Boolean b4, and I'll assign that an expression wrapped in a pair of parentheses. The expression will look like this: I1 not equal to 0. And I'll close the statement with the semicolon. The operator exclamation equals means not equal to. So once again, I'll output the result to the console. And b4 is false. I1 does have a value of 0. The expression is evaluating whether the values don't match, and so it returns false. Finally, I'll show that you can take a string with a value of true or false and parse it as a real primitive Boolean. I'll create a string called sBoolean, and I'll give it a value of true, wrapped in quotes. Then I'll create a Boolean variable that I'll name parsed, and I'll give it a value by using the helper class for the Boolean data type. The name of the class is Boolean with an uppercase B. I'll call a method from that class named parseBoolean, and I'll pass in sBoolean. Then I'll output the result. I'll start with a label of parsed, and then I'll output the parsed variable. And there's the result. Note that when you call parseBoolean, you must pass in values that work for Java, the strings true and false. So that's a look at Boolean values. When you want to represent Boolean values, it's recommended that you use primitives whenever possible. You can also use the Boolean helper class in some circumstances, but it takes a bit more memory. But as you can see, it also has incredibly helpful methods you can use to manage your Boolean values. Java distinguishes between characters and strings. A character is a primitive data type, and it consists of just a single character. A string is a complex object and can consist of many characters. I'll show you how to declare and initialize characters here, and I'll add code to the main method to declare a single variable with a data type of char, C-H-A-R, a name of C1, and a value of 1 wrapped in single quotes. Literals for characters are always wrapped in single quotes, while literals for strings are wrapped in double quotes. I'll duplicate that line of code a couple of times, and then I'll change the names of the variables to C2 and C3, and I'll change their equivalent values. Then I'll output these values. I'll use systemout, and I'll start with a label of char1, and I'll append C1. I'll duplicate that a couple of times and change the labels and values. And I get the values as expected. You can also declare a character using a literal that's a Unicode escape sequence. That looks like this. I'll declare another variable, data typed as char, and I'll name it $, and I'll give it a value wrapped in single quotes of \U0024. That's the Unicode number for the $ character. Then I'll once again use systemout. I'll duplicate this line of code and move it down. I'll give it a label of currency, and I'll output $. and the output shows the actual $sign. Once you have characters, you can turn them into strings quite easily, but I'll get to that later in the course. For now, I just want to show you how to manipulate characters using the helper class for the car data type. I'll declare a character named A1 with the value of A. Then I'll duplicate that a couple of times and change the variables to A2 and A3 and the values to B and C. Now I'll use systemout, and this time I'll take off the ln, so I'm only printing but not adding a line feed. Then I'll pass into that a method of the character class. The name of the method is toUpperCase. If you look at the documentation for the character class, you'll find that it has a lot of useful methods. I'll choose this version of the method that receives a car argument, and I'll pass in A1. Then I'll duplicate that line a couple of times, and I'll change A1 to A2 and A3, but for the last one, I'll change the method I'm calling back to println. So I'm outputting the line feed only on the third call to system.out. Now when I run the code, I once again see my original output, but I see ABC in all uppercase and all on the same line. So again, a character is a primitive value, not a complex object. If you set it as a primitive, it won't have any methods of its own, but you can use the character class's methods to manipulate and otherwise manage it. I've already used a number of Java's operators in my examples, but I'll take a moment now to go through them in detail. Java's syntax is based on C. It's a C-style language, and so it uses most of the same operators that you'll find in most C-style languages, including C, C++, C#, JavaScript, and so on. There are various types of operators. The equality operators are used to compare values to each other. Assignment operators do exactly what it says, assign values. And there are mathematical operators and logical operators. Here are some of the most common assignment and math operators. When you declare a variable in Java, you always start with the data type, followed by the name of the variable. But you don't have to immediately assign a value. The default value will depend on whether the variable is a primitive or an object. But if you want to assign a value, you use the single equals character as the assignment operator. The data type and variable name go on the left and the value on the right. This would be a simple assignment, but you can also execute mathematical operations as you assign a value. These would be expressions that evaluate to the correct data type. The plus operator is for addition, the minus operator for subtraction, the asterisk for multiplication, and the / for division. There's also the percent character, which is the remainder operator, also known in some languages as the modulus operator. Here are some other things you can do with assignments and mathematical operations. I'm starting with an integer value of 10. You can increment and decrement that value with a ++ or a --, and that operator can go either before or after the variable name. I'll talk about the effect of that in just a moment. You can also increment or decrement and assign values at the same time using these operators. + means assign the value and execute the math operation. - does the same thing for subtraction, and there's also * and divide equals. Now, about placing the increment and decrementing operators before or after a variable name. Once again, I'm starting with an integer value of 10. If you place the ++ operator after the variable name, that's called a postfix assignment. You're evaluating the value and then executing the math. In this example, I'd be outputting a value of 10, but then resetting the value to 11. If you move the operator before the variable name, that's called a prefix. Then you're executing the math and then evaluating the value. And then your output and your new value would be the same. The equality operators are used to compare values to each other. The = operator is called the equality operator. With primitive values, it compares the actual values. With reference variables, though, that is, variables that point to objects, you're comparing whether the two variables are pointing to the same object, not necessarily whether they have a same value. The inequality operator is exclamation equals. Some Java developers like to call the exclamation mark the bang operator. But again, this simply means not equals to, and it has the same rules as the equality operator. Primitive variables are evaluated by their values, and reference variables by whether they point to the same object. In addition to double equals and not equals, you also have greater than, less than, greater than or equal, less than or equal, and a special operator called instance of that asks whether an object is an instance of a particular class. So for example, if I have a string and I have a condition of s instance of java.lang.string, that's the fully qualified name of that class, then my condition would be true, and I could say yes, this variable is a string. One of the exceptions to comparing values is with strings. Strings cannot be safely compared to each other using the equals operators. It'll work in some circumstances and not in others, and I'll describe the details of that later in this course. But I'll just say now that if you want to compare strings to each other, you shouldn't use the equals or not equals operators. Instead, you should use the string class's equals method. There's one version of this method that's case sensitive, this one, and another version that compares values without case sensitivity. And again, I'll describe those details a little bit later on. The result of this code would be they match. And then finally, there are the logical operators. The double ampersand is the AND operator. The double pipe character is the OR operator, and you can use those to combine two conditional expressions and get a result. And then there's the ternary operator that looks like this. You examine a Boolean condition, and then after the question mark, you set a value you want to assign if the condition is true, and after the colon, a value you want to assign if the condition is false. This is shorthand for an if-then conditional statement. Some developers love using this expression. I tend to avoid it. I tend to use a more verbose if-then statement because I think it's easier to read and maintain later on. But this expression absolutely works and is very popular in the Java programming world. So that's a summary of the most commonly used operators in Java. There are a few others, include operators known as bitwise operators, but they're used less commonly, and I encourage you to look at the Java documentation for a complete look at all of the operators that are available. So far, I've described variables in Java that use the primitive data types, numbers, characters, and booleans. But there's a whole other category of Java variables that are references to objects. An object in Java is an instance of a Java class. When you create a variable and you point it at an object, the variable isn't the object itself. Instead, it's simply referencing the object. And you can actually have multiple reference variables that are pointing to a single object in memory. So you might declare an object that has a name of an object, and then you might have 3 different variables that are all pointing to the same thing. If something changes about that object in memory, all 3 of those variables would update. Here's an example. Let's say that I've defined a Java class. This class is named clothing item. And I've declared a string variable that's a member of the class. Notice that this string variable doesn't have the word static. That means it's something called an instance variable, also known as a field. An instance variable is not a member of the class itself. It's a member of an instance of the class. Now, in my main method, I'm creating an instance of the clothing item class. This line of code has a data type, which is the name of the class, then the identifier, which is the name of the variable, item, then the keyword new, and then finally a call to something called a constructor method. I'll go through constructor methods in detail later, but what you need to know now is that this is how you create an instance of a class in Java. It's called instantiation. Now, once the instance is created, the variables that you declared as instance variables are now available. So I can assign a value to the type variable or field. And that's what the next line is doing. item.type equals hat. Class instances or objects can also have instance methods, and that's what display item is. This is a method, once again, without the static keyword, and therefore it's a member of an instance of a class, not a member of the class itself. So I can call it from item, the object, and then it will output information that belongs to that instance of the class. The expression this.type means the type variable that's a member of the current instance of this class. So instance variable, instantiation, and instance method are 3 bits of vocabulary you should know about in order to work successfully with Java classes and instances of those Java classes known as objects. A string in Java is a complex object. It's an instance of the string class. The string class, just like the helper classes for the primitive data types, is a member of java.lang, so you don't have to import it or use any special notation to use the string class. It's always available to you. Here's an example of creating an instance of the string class. Once again, I start with the data type, string with an uppercase S. Then I assign the name or identifier. Then after the equal sign, that's the assignment operator, I have the keyword new. Then I'm calling the constructor method of the class and passing in a value. This creates a string variable. The string class is a little bit special because you can also use a shortcut. The compiler understands this to mean exactly the same thing. Create an instance of the string class and assign it this value. But using this syntax, you can eliminate the new keyword and the explicit call to the constructor method. But again, these 2 lines of code mean exactly the same thing. Here are some other important characteristics of strings. A string is basically an array of characters. A character is a primitive, a string is a complex object. But a string can have as many characters as you want, assuming you have adequate memory in the computer that's running your code. So a string is a collection of characters in a particular order. This might be a string object, the string hello, but you can break it down into an array of char values. Another important thing to know about strings is that they're immutable. That means that once you instantiate and assign their values, you can't really change them. Now, the Java compiler will make it look like you can change them. For example, if I start with a variable named string1, and I assign it a value of hello, and then on the very next line I say string1 equals hello world, it looks like I'm changing the object. But in fact, in the background, I'm dereferencing the original object. That object can now be cleared from memory in a process known as garbage collection, and I'm creating a brand new object with the new value. It's essential to know this, because if you've worked with languages where strings aren't immutable, where you can change them at runtime, you might be used to simply appending values over and over again. But in Java, that results in creating a lot of objects when you might not mean to do that, and it can create memory management problems in the background over which you have very little control. Here are some other examples of working with strings and characters. In this class, I'm declaring an array of characters. The expression char with open bracket and close bracket means an array. Then I have the variable name, chars, that's the identifier. And then I'm explicitly assigning an array using the braces. Each item in the array is separated from the next with a comma. Each of the characters is a literal character, using single quotes. Now, to turn that into an actual string object, I create the string, and I use the string constructor method, and I pass in my character array. And the result is an actual complex object. So let's create a few strings. I'm working in the project string class, and I'll add code to the main method. I'll declare a string that I'll name S1, and I'll assign its value with a literal. String literals are always wrapped in double quotes, and I'll assign this is a string. Then I'll output that value using system.out.println, and I'll output S1, and I'll run that code, and I get what's expected. This is a string. Now I'll declare a second string, But this time I'll use class constructor method syntax, and I'll pass in another string literal of this is also a string. I'll duplicate and move this line down, and I'll output S2. And again, I get back the expected result. So again, there is no functional difference between these two syntax styles. They're both creating a string object, and which you use is a matter of preference. You can also create strings by concatenating or appending values together. I'll create another string that I'll call S3, and I'll give this a value of shirt size. Then I'll create another string with a value of M for medium. And finally, I'll create a string where I put those values together. And then I'll output the result. And I get shirt size :M. And I can continue concatenating values. To the end of this, I'll add another literal value, starting with a comma, and then QTY : and then I'll append a numeric literal to the end of that. When you append numbers, as we've seen previously, they're automatically turned into strings during the compilation process. And now when I output the value, I get a single string consisting of all of those values. I mentioned earlier that strings can be built from arrays of characters. So I'll declare an array of characters, starting off with the primitive data type car, followed by a pair of brackets. I'll name this array cars, and I'll instantiate it with a pair of braces, and then the 5 characters in the word hello. Each of these is a literal character, so they're wrapped in single quotes. So now I have an array of characters, and I want to turn it into a string. So I'll declare a string that I name S6, and I'll instantiate it with the strings constructor method. And I'll use the second version that accepts a character array, passing in cars. And then I'll output the result. And I get hello. Now let's take a look at what happens when I go in the other direction, when I want to take a string and turn it into an array of cars. I'll declare another character array, and I'll name it cars2, and I'll get its value by calling an instance method of the string class to character array. That returns exactly what I'm looking for, an array of characters. Now to print this out, I'll need to print one character at a time. I'm going to use something called a for each loop. This is a bit of syntax we haven't seen before. I'll type it in and then I'll explain it. I'll start with the keyword for, then inside a pair of parentheses I'll set a data type, car, and a variable name, then a colon, and then the name of the array I want to work with, cars2. Then I'll add a code block, and within the code block, I'll output the current character. So let's look at this syntax. Within the parentheses, I'm saying, for each character in the characters array. The character I'm currently working with on each iteration of the loop will have a data type of car and a name of C, and I'll keep on looping as long as there are items available in the array. Within the array, I can then operate on just that one character, that one primitive value. And here's the result. At the end of my output, I'm outputting one character per line, outputting the word hello vertically. So, strings again can be created using simple literal syntax or by using more complex constructor method syntax. Either way, it's an instance of the string class, and you have access in the string class to all of the instance methods that are members of this class. You can find out all about that class and its members by looking at the Java API documentation. I'll place the cursor in the name of the class and press Shift F1. And that takes me to the documentation. Then I'll click on the method link and I'll see all the different methods that are available from the string class. I've described previously how you can append primitive values to strings, for example, when you're outputting to the console. But you can also directly convert primitive values to strings using helper classes of various types. I'm working in the project Primitives to Strings, where I've declared 3 variables, an integer, a boolean, and a long, and I'll convert all 3 of these to strings. For the integer, I'll use a helper class. I'll declare a new string variable that I'll name fromInt, and I'll assign it using the integer class. This class has a number of methods I could use. In addition to the simplest one, toString, there's also toBinary to hex string, and to octal string, and even one named toUnsigned string. I encourage you to experiment with those, but I'll stick with the simplest one, toString. And then I'll pass in the value that I want to convert. Then I'll output the result to the console, calling system.out.println and passing in my fromInt variable. And when I run the code, I see the expected output, the simple number 42. Now I'll do the same thing with the Boolean value. Once again, I'll declare a string. This time I'll name it fromBool, and I'll get its value by using the Boolean helper class. Remember that all helper classes start with an initial uppercase character. The Boolean helper class only has one toString method. It doesn't have all the different variations that the numeric helper classes have. I'll call toString, I'll pass in my value, and then I'll output that to the console. And I get back a value of true, as expected. Now, when you use the helper classes for the primitive data types and their toString methods, you're limited to converting to the default formats. But there are also useful classes in the Java runtime that can do more complex formatting. The long value has been set to a value of 10 million. Notice the use of underscores to separate the zeros. That just makes the literal numeric more readable, but it doesn't affect the way the compiler looks at it. The use of underscores as separators in your code was introduced in Java 7, and it makes it much easier to look at long numeric values. But to format this as a string, I'm going to use a class named numberFormat. Now notice this is a member of a different package. It's not part of java.lang. So when I select it, IntelliJ IDEA is going to automatically add an import statement on line 3. That makes it possible to use the number format in my code. I'll name this object simply formatter, and I'll get this object's reference by calling a method of the numberFormat class called getNumberInstance. Notice that there's also getIntegerInstance, getCurrencyInstance, and getPercentInstance. Now I'll create my string, and I'll call it formatted, and I'll get its value by calling formatter.format, and I'll pass in my long value. Then I'll output formatted to the console. And here's the result. When the string is created, the commas are added as the separators. Now I'm seeing commas because I'm in the US locale. If you're working in another locale, you might see periods instead. But using the numberFormat class, you actually have control over all of that. You can change your locale, you can explicitly say what your separators are, and you can otherwise affect the formatting. I'll talk about those more advanced approaches to formatting numbers as strings later on, but for now you can see the various approaches to converting primitives to strings, using the toString methods of the helper classes or using the formatting tools that are members of the java.txt package. When assembling strings, it's tempting to put them together using simple concatenation. I'm working in a project named String Builder, and I've declared two strings with values of hello and world. Let's say I wanted to create a third string that put those strings together and added some extra characters. I could do this. I'll create my third string and start with str1, and then I'll add a comma and a space, and then I'll append str2, and then I'll append an exclamation mark. And that all works fine. I'll output the value to the console and show that putting strings together like this will achieve the desired effect. But the problem is that in order to do that, I've created three distinct objects, the original two and then the third. If you're dealing with a lot of string concatenation, this can cause problems in memory management. So instead, it's recommended that you use a class named String Builder. This class is a member of the java.lang package, so you don't need any special imports for it. I'll declare a String Builder object, and I'll give it a name of SB. and I'll instantiate it using the new keyword and then the constructor method for the class. The pull-down menu that appears here shows me that there are 3 versions of the constructor method. One that takes an integer, something called the capacity. That's a way of setting the capacity of the string builder object ahead of time if you know how much data you want to hold. Or you can initialize it with a string or something called a character sequence. I'm going to choose the string version, and I'm going to pass in the initial string that I passed in before. I'll finish that statement. Now, I'll call the string builder object's append method. Notice that there are many versions of the append method, one for each of the primitive data types, one for character sequences, one for strings, and one for a class named string buffer, which isn't used too much these days. I'll call the append method for the string, and I'll pass in a comma and a space. I'll finish that line, and then I'll duplicate that line a couple of times, and then I'll pass in 2 more strings, the word world, and then an exclamation mark. Then I'll output the results. I'll pass the string builder object directly into the print line method, and then I'll run the code, and I see that the string has been put together exactly the same way as before. But now I'm only creating 1 object instead of 3. Here are some other things to know about the string builder object. Each of the methods that you called, such as append, returns a reference to that string builder object, so you can chain your calls together. So for example, in this code, I could get rid of these SB references, and then go back to all the lines except the last one and remove the semicolons. Now I'm going to add some tabulation to make it clear that this is all one statement. When I first instantiate the string builder object, I get back a reference to the object, but then I can call its methods immediately, and each time I call the method, it's passing back the same reference. So I'm constructing the object and passing in the initial value, and then I'm calling the append method 3 times. And the result, again, is exactly the same, but just with a little bit less code. You can also use a string builder to collect data that the user provides. I'm going to use a class called the scanner class. This is a member of a package called java.util, so when I select it, an import statement will be added at the top of the code. I'll name my scanner object scanner with a lowercase s. So scanner with an uppercase s is the class, and with lowercase it's the object. And then I'll instantiate it with the new keyword and a call to the constructor method. The scanner's constructor method has a bunch of different versions. One of them looks for something called an input stream, and it turns out that system.in is exactly that. If I type in system.in, I see the data type in the list way over at the right, and so I'm saying collect the data from the console, just like system.out outputs to the console. Now I'll display a prompt for the user. Notice I'm using the print method, not println. I'll type enter a value, and then I'll declare a string variable named input, and I'll get its value by calling a method named scanner.nextLine. The nextLine method waits for the user to type in some text and then press enter or return, and whatever the user typed in will be returned from the method, and I'm saving that in the variable. Then I'll output to the console, and I'll repeat the text that the user typed in. I'll run the code, and I see hello world twice from the first part of the application. Then I see my prompt enter value. I'll click into my command prompt right next to the colon, and I'll type a value. I'll press enter or return, and I see the value printed back. Now I'll combine the two together, the string builder and the scanner. First, I'll delete the contents of the string builder with this code, sb.delete. The delete method takes 2 arguments, both integers, the starting character and the ending. The starting can be 0. As with arrays in Java, you're always counting starting at 0. The ending will be the number of characters minus 1, but I can simply pass in the number of characters in the string builder, and that'll be good enough. To get that value, I'll use the expression sb.length. Length is a method of the string builder class. So now I'm using the string builder again, and I'll be appending from scratch. Next, I'll add code for an iteration loop using the for keyword. I'll type the word for, and I see a menu pop up, and I'll choose for I, create iteration loop. And when I press enter or return, I see classic looping syntax for C-style languages. This is an iteration loop that looks for a certain number of loops. It starts with a value of 0 assigned to a variable named I, then continues looping until I equals a certain number, and I'll set that number as 3. The third part of this expression, I++, means increment the value of I by 1 each time through the loop. Now, within the for loop, I'll reuse that input variable that I already declared, and just as I did before, I'll get a value from scanner.nextLine. Then I'll append to the string builder using sb.append, and I'll pass in the input value, but I'll append to that a line feed, which in Java is expressed with an escape sequence of \n wrapped in double quotes. So that code is going to execute 3 times. When the loop is done, I'll output the result, once again using printLine, and I'll pass in the string builder object. If you want this code to be more explicit, you could use the expression sb.toString. But when you pass in the builder object, the toString method is being called automatically for you, so you don't need that extra code. So I'll run one more time, and when I'm prompted, I'll click into the window, and I'll enter a value, and I see that repeated back to me. That was the first call to scanner.nextLine. Now I'm in the for loop, and I'll type in 1, press enter or return, then 2, then enter or return again, and 3. And now when I press enter or return, I see all 3 values printed back. They're stacked on top of each other because I added the explicit line feed at the end. So that's a look at how you can use the string builder class to put strings together at runtime while minimizing the number of objects you're creating in memory, and how you can use the scanner class to get data from the user at runtime. There are many scenarios where you need to compare strings to each other, and using simple equality operators, as you might do with numbers, doesn't work the way you'd expect. In this project, Compare Strings, I've declared 2 string variables. They both have the same value, a string of hello. I'm going to add a bit of conditional code. In Java, you can write some simple conditional code with the if statement. The if statement places a Boolean condition inside a pair of parentheses. And I'll compare str1 to str2 using the double equals operator. That's called the equality operator, and it works great with primitive numbers, Booleans, and characters. With strings, it might appear that it works also. If this condition is true, I'll output a string to the console of they match. Then I'll add an else clause after the if clause, and in that section, I'll output they don't match. Then I'll run the code. Everything seems to match expectations. The 2 strings are identical, and I get back they match. But the reasons for that match aren't what you think they are. Let's take a look at another example. I'll declare a variable named str3 and give it a value of hello, all lowercase. And then once again, I'll execute some conditional code. I'll copy and paste this section down here, and I'll change the value that I'm matching to str3. And this time, again, as you might expect, I get back they don't match. Clearly, these 2 values aren't the same because one is uppercase and one is lowercase. But now let's try this. I'll declare a string variable named part1, and I'll give it a value of just hello, followed by a space character. Then I'll create a variable named part2, and I'll give it a value of world. Then I'll create the variable str4, and I'll create that by concatenating the strings together with part1 plus part2. So now I have a string of hello world. Then I'll create another string. This will be str5, and this will be the entire thing. hello world. Now those two strings, str4 and str5, should match. But let's see what happens when I execute some conditional logic. I'll copy and paste this code again. And this time I'll compare str4 and str5. And this time I get they don't match. So what's going on here? Well, in the first examples, when I declared the first string, that literal string was registered in memory by the compiler. Then, when I declared the second string, instead of creating a new object, the compiler looked in the table of existing strings, and it found a match. And instead of creating another object, it simply pointed the second reference variable to the original object. And this is safe. Remember that strings are immutable. Once a string object is created, its value can't change. So it's safe to simply point the second string at the first one. They are, after all, identical values. The second bit of logic worked because that sort of comparison is never case-sensitive. This process is called interning. The compiler interns the second value. It finds the original value, it finds a match, and then it interns or makes a reference. In the second example, it didn't find a match, so it created a new object, and the entire string was lowercase. So now we come to the last example. Here we have two strings, part 1 and part 2. They are their own objects. The compiler is asked to put those values together, but it decides it doesn't have enough information at compilation time to know for sure that these will match, so str4 is created as another object. And then str5 is a completely different object because the compiler doesn't know that that string matches str4. So when I try to match the values, I get they don't match. In order to do an accurate comparison of strings in Java, you should use the string classes equals or equals ignore case methods. I'll use equals first. I'll call it as a member of str4, and I'll pass in str5. And then I'll run the code, and this time I get they match. But now let's see what happens if one of these values is actually uppercase. I'll change this word, and then run the code again, and now the equals method returns they don't match. But then I'll change the method that I'm calling. I'll place the cursor after the method name, equals, and press Control space, and select equals ignore case instead. And then I'll run it, and this time I get they match. So the lesson is, when you want to compare strings to each other, to always get an accurate result, use the equals or equals ignore case methods. Don't use the double equals operator. In some cases, it might give you what you expect, but not always. And not always isn't good enough in programming. You want accurate, predictable results, and the string class's methods can give you that. I've previously described how to start with a string containing numeric characters and convert that to a primitive value using the primitive data type helper classes and their parse methods. For example, a string of 1, 2, 3, 4 could be turned into a double value using the double class's parse double method. But you can also go from a primitive value to a formatted string using a variety of classes provided in the Java runtime. In this project, Format Numbers, I've declared a single primitive value, named double value. It has a value in the millions. The underscores are only there for readability and are ignored by the compiler. I'm going to take that value and present a formatted string. As I did previously, I'll use the number format class. I'll type the beginning of the class name and select it, and an import statement is added for me. I'll give this a name of numF for a number format, and I'll get its reference by calling a static method of the number format class getNumberInstance. Then I'll output to the console, starting with a string of number, and ending with the formatted value using this expression, numF.format, and I'll pass in the value double value. And when I run the code, I get back a comma-separated string. Now that's the string you'll see in locales that use commas as separators and periods for fractions. In some locales, you'll see the opposite: periods for separators and commas for fractions. But you can explicitly control that by setting the locale yourself. I'll move the cursor to the top of the code, and I'll declare an instance of the locale class. This is a member of the package java.util, so when I select it, an import statement is added. I'll name my variable locale, all lowercase, and I'll instantiate it with the locale class's constructor. The constructor takes a few different versions. I'm going to use the second version that accepts two strings for the language and the country. The language is in all lowercase, and I'll set that to DA for Danish. And then for the country, I'll choose DK, uppercase, for Denmark. Then I'll take that locale object and I'll pass it into the getNumber instance method. There are two versions of this method, the one I'm currently using that accepts no parameters, and one that accepts the locale. I'll add the locale, and then I'll run the code again, and this time I see dots as the separators, and that should work for everybody, regardless of your computer's locale. So that's simple numbers. So what if you wanted to use a currency? I'll create another instance of the number format class, and I'll name this one curF. And I'll get that reference by calling getCurrencyInstance from number format. Notice that once again, there's a version with no parameters and one that accepts a locale. Then I'll start with a label of currency, and then I'll output the formatted currency value. And when I run the code, I'd get back a currency value starting with a $sign. Again, your display might look different depending on your computer's default locale. But then I'll go to Get Currency Instance, and I'll pass in my locale. And this time, instead of getting a $sign, I get KR for kroner. Finally, I'll show what happens with Get Integer Instance. I'll create a number format object. I'll call this one intf. I'll call numberFormat.getIntegerInstance. Then I'll make a copy of this line of code and paste it here. I'll change the label to integer and the formatter I'm using to intf. And there's the result. With integer formatting, I'm rounding the value before displaying it. In addition to these, there's also a decimal format object that you can use that lets you customize the display of your numeric values. But this is a good introduction to numeric formatting in Java. Use the number format class or the decimal format to take a primitive value and display it as a formatted string. Java's string class includes many methods that you can use to parse information and find substrings. I'll show you some of them here in the project Parsing Strings. I've declared a string with a value of Welcome to California. And first, I'll display the length of that string. I'll use some system output, and I'll start with a label of length of string, and I'll append to that the expression s1.length. Length is a method of the string class. I'll run that code, and the result is length of string 22. Now, let's say that I wanted to find a particular substring within that string. You can do that with a method named indexOf. It returns an integer value, so I'll create a variable named position, declared as an int, and I'll get its value by calling s1.indexOf. And I'll pass in the substring I'm looking for. Then I'll output that information to the console, starting with position of substring and then outputting the position. And the result is position of substring 11. Now, just as with arrays, you're starting counting at 0, so the letter C in California would actually be the 12th character. But you return a value of 11 because that's the index position. And you could verify that by calling a method of the string class named substring. I'll create a string, I'll name it sub, and I'll call s1.substring. And notice that there are two versions, one that has a beginning index and one that has both a beginning and an ending index. I'll use the version that takes just a single argument, the beginning index. And then I'll output the substring that I found, and I get back California. Here's one more experiment. Let's say that I had a string that had a bunch of spaces at the end. I'll create a string that I'll name S2, and I'll set its value as welcome, but then I'll add a whole bunch of space at the end. Then I'll report the length. I'll create an integer that I'll name len1, and I'll get its value from s2.length, and then I'll output that value to the console, and I get back 17. Next, I'll create another string that I'll name s3, and I'll call a method of the first string class named trim. The trim method removes white space from both the beginning and the ending of the string. Then I'll make a copy of my output code, and I'll paste it down here, and I'll change the expression of what I'm outputting to s3.length. And after trimming, the length is only 8 characters. You can learn a lot more about the capabilities of the string class by looking at the API documentation. Take a good look through all the different methods that are members of this class. If you want to parse a string, you should find the tools you need to do it here. There are 2 completely different APIs for working with dates and times in Java. The original set of classes that were introduced with Java in the mid-90s, and a completely new datetime API that was brought in with Java 8. If you're working on, say, a Java Enterprise Edition application, and you're working with the Java 8 runtime, then you can use the new API. But if you're working in older versions of Java, or if you're working in Android, which doesn't yet implement Java 8 features, then you'll need to use the older classes. I'm working in the project Dates and Times, which has a main class with an empty main method. And I'll start with the original Date API. I'll create an instance of the Date class, which is a member of the java.util package. Because it's not a member of java.lang, it must be imported in order to use it. I'll name my object D, and then I'll instantiate with new, and then the constructor method date. There are a number of different versions of this constructor method, but the strikeout for most of the versions means that those versions have been deprecated. Using the date class in this way is not how you're supposed to create a date with a specific year, month, and date, for example. But this is a good way to create a date object that represents the current moment in time. So that's what I'll use. Then I'll output the date object to the console. When I run the application, I get the date output using a date stamp format, starting with the day, the month, the date, the time zone, and the year. Now, let's say I wanted to represent a specific date. Instead of using the date class, I would use a class named Gregorian calendar. I'll select the class, and that adds the import, and I'll name this object GC, and I'll instantiate it with new, and then Gregorian calendar, and I'll pass in 3 values, a year, a month, and a day of the month as an integer. I'll pass in values of 2009, 1, and 28. Now, let's say I wanted to add a day. The Gregorian calendar class has methods for modifying the date it contains. I'll call a method named add, and then I need to indicate what kind of information I want to add, a year, a month, or a date. And I can represent that with a constant of the Gregorian calendar class. I'll call Gregorian calendar, and then dot, and I'll pass in date. And notice that there are constants for all of the other different kinds of information you might want to modify. Then I'll pass in 1, and that would mean add 1 to the date. Then, to get the date object, I'll create a date, and I'll name it D2, and I'll get its value from the method gc.getTime, and that returns a date object. And from there, I can output the result. And now, the resulting date is March 1st, 2009. Now notice something interesting here. When I initialized this information, I said I wanted month number 1, and then I added 1 to the number 28, and somehow I get March 1st. What's going on? Well, in the original API, months are numbered starting at 0. So January is 0, February is 1, Marches 2, and so on. So if I pass in 1 and 28, I mean February 28th, the last day of the month in that year. And when I add 1, that takes me to March 1st. Now, let's say that I wanted to format this date. I can do that with a class named dateFormat. I'll name this object df, and I'll call the method dateFormat.getDateInstance. You can call the getDateInstance method with no parameters, with a style, or with a style and a locale. I'll pass in a style, represented by a constant of the dateFormat class. I'll use the constant full, and then I'll output my date using system output, and I'll call df.format, and I'll pass in my date value. And now I get a nicely formatted output. The dateFormat class has a number of constants you can use, and it also supports explicit patterns that you can use to format a date for specific purposes. So that's a little bit about the older version of the API. But let's take a look at the Java 8 version. In Java 8, datetime values can be represented by a class named localDate, localDateTime, and localTime. I'll use localDateTime, and I'll name it LDT, and I'll instantiate it using localDateTime.now. That's a method of the localDateTime class. So that's the equivalent of constructing a date object with no parameters. But notice, when I created this class, IntelliJ IDEA added an import statement up here. The new API is in a package named java.time instead of java.util. Now I'll output that value. I'll just pass in the local datetime object to my system out, and I get back this string. This is a Unix timestamp, and it's the structure of a datetime value as represented in some databases. Next, I'll describe how to represent a specific day using the localDate class. I'll create a local date, I'll name it LD, and I'll get that value by calling localDate and then the of method. There are a couple of different versions of this. I'll use the version that looks for a year, a month, and a day of the month as integers. And I'll pass in the same values I did before, 2009, 1, and 28. And then I'll output that value without any special formatting. And I get back January 28th, 2009. So this is a difference between the old date API and the new one. In the new one, month numbering goes from 1 to 12. In the old API, it went from 0 to 11. Finally, I'll show you how to format a local date. I'll create an instance of a class called dateTimeFormatter, which is a member of the package java.time.format, and I'll name it DTF. There are a number of ways of doing this. I'll show you a simple approach using a constant of the dateTimeFormatter class. I'll choose ISO_date. Then I'll output the formatted value with DTF.format, and I'll pass in the value, LD. Notice that the format method is looking for a class named temporal accessor. That's the superclass, or the ancestor, of the specific classes you'll use: localDate, localDateTime, and localTime. I'll run that code, and I get back the same output. But now let's try a very specific format. This time, I'll create my format using a method named ofPattern. It looks like this. It's looking for a string pattern, and I'll pass in uppercase M, then a slash, then a lowercase d, then another slash, then YYYY. And then I'll run the code again, and here's the result. This time, I get back a date that's formatted for brevity and readability. Take a look at the documentation for more information about how to create these patterns, how to represent months as numbers or as strings, and how to add padding to date and month values. So again, there are two APIs in Java for working with dates and times. If you're working with Java 8, you can use the new API, but everybody else will still be using the older set of classes. So now it's time for a simple challenge to create a simple console application that takes user input, translates strings to numerical values, executes a mathematical operation, and returns the result to the console. I'm working in the project Simple Calc. Now, don't open it quite yet, but I'll show you what the finished application looks like when I run it. I'll run the application, and my run window opens at the bottom of the screen. I see a prompt, enter a numeric value. I'll type in a value of 15, and I'm prompted for a second value. This time I'll enter a fractional value, 16.5. And when I press enter, I get back the answer is 31.5, and the application finishes. So that's the application you should create. I encourage you to create the project from scratch. Create a brand new Java project and put all the code into the main method of the main class. Using the scanner class, get some input from the user. Using the helper classes for the primitive data types, parse the strings that you get into primitive numbers, do a bit of addition, and then report the value back using system output. When you're finished with the application, you can look at the next video and I'll show you how I programmed the solution. So here's my solution to the challenge, to create a simple calculator application that receives two numbers from the user, adds them together, and reports the result. I'm opening the project Simple Calc. In my main method, I've created a scanner object. Notice that I have an import statement on line 3. The scanner class is a member of java.util, and so it must be imported to be used. At line 11, I'm outputting a prompt, enter a numeric value, and then I'm collecting the data from the user, calling the scanner object's next line method. Then I'm parsing that string as a double value. Notice that right now I don't have any error handling in this code. I'll be talking about error handling in just a little while, but for now we're trusting that the user will type in a numeric value. I'm repeating that process to get the second number. Then I'm adding the two values together and displaying the results using system out again. So that's my solution to the challenge. Take a look at your code and see how you solved it, and then compare the two to learn about different ways of approaching problems in Java. Dealing with bugs is a common part of all software development. Before we get too much further into the Java programming language, I'll describe how to handle various kinds of errors, both syntax errors, which you must deal with before you can compile and run your application, and runtime exceptions, those exceptions that occur while the application is running. In the empty main method, I'll start by introducing a syntax error. If you've been coding for any amount of time, I'm sure you've seen some of these. I'll declare a string that I'll name S, and I'll try to assign it to the keyword null. Now, I'll intentionally misspell it. The keyword null in Java is all lowercase. When I type it with an uppercase N, and then I try to run the application doesn't even compile. Instead, I get a syntax error, telling me that the compiler can't find the symbol. It means this keyword null. And it tells me exactly where the problem is and how to deal with it. In a larger application that might have a lot of different Java classes, you might run into a situation where you don't even know where the file is. But IntelliJ IDEA gives you a very simple way of finding it. If you see these squiggly lines, that means there's a syntax error somewhere, and you can go to the project window and look at the problems view. And you'll see a listing of all files that have syntax errors. You can then double-click on the file, and then press the F2 key on either Mac or Windows, and the cursor will jump to the next error. Frequently, IntelliJ IDEA will even know how to fix it. If you see the light bulb icon, you can pull down the list and see if there's a solution. In this case, I know that the error is that the keyword is null with a lowercase n, so I'll just manually fix it myself. So that's a syntax error. And again, IntelliJ IDEA gets information from the Java compiler and then tells you where your errors are and, to whatever extent possible, gives you hints on how to fix it. So once you've fixed all of your syntax errors, you're then able to compile and run the application. But even then, it might not solve all of the issues. For example, I'll try to output this string to the console. I can find out whether I can build the application by going to the menu and selecting Build and then Make Project. Down in the lower left corner, if I see the message Compilation Completed Successfully, that means that I don't have any syntax errors. And notice that my Problems view is empty. But now I'll try to run the application, and I get something on the console, just the keyword null. That in itself is not enough to cause an actual exception. But let's put in some code that will cause an exception. I'll create another string named welcome, and I'll give it a value of welcome with an exclamation mark at the end. Then, as I've done previously, I'll create an array of characters that I'll name cars, and I'll get the value from welcome.toCarArray. So now I have a set of characters in a particular order. Next, let's say that I want to get the last character in the array. So I'll create a car variable, and I'll name it lastCar. And I'll get its value using array syntax. I'll start with the name of the array, and then pass in cars.length. Length in this case is a property, not a method, so you don't need the parentheses at the end. Then I'll output that character to the console. I'll wait a moment and look for any squiggly lines. I don't see any. And I also look at my Problems view and don't see anything listed there. So I don't have any syntax errors. But when I try to run the application, I get this message, exception in thread main. And it tells me what kind of exception it is. This is something called an array index out of bounds exception. I'll get more deeply into exception handling in a couple of videos, but what's important to know right now is that when you hit this kind of exception, it stops your application in its tracks. It's fatal, and the application can't continue. So the problem here is in this code. I tried to reference the character at an index position where the index is the same number returned by the length. But remember that I've said that indexing in arrays starts at 0, so the last character has an index that's 1 less than the length of the array. To fix this code, I'll ask for the character at the index position of the array's length minus 1. And then I'll run the code again, and this time it works. I display the exclamation mark that's at the end of the string. So that's how exceptions can be generated. If you write code that's syntactically correct, but where the logic is wrong, frequently you'll get this kind of exception. And understanding how to look for it, how to find out where it's happening, and then how to fix it is critical to good Java programming. All good integrated development environments for Java provide debugging capabilities, the ability to set breakpoints, and to watch variable values so that you can find out where errors are occurring in your code. I'll demonstrate how to do this in IntelliJ IDEA in the debugging project. This project has just a few lines of code. I'm declaring a string value. I'm then getting a character array from the string, and then I'm stepping through the character array using a for loop, and I'm outputting one character at a time. When I run the application, I see the string displayed vertically, one character per line. But now I'm going to step through the code one line at a time. I'm going to add a breakpoint. I'll click once to the right of my line numbers if they're displayed, but to the left of the code. And I see a breakpoint icon displayed. If I move the cursor off the icon and then back again, I'll see some useful information about it. Now, to run the code and hit the breakpoint, I'll run in debug mode. You can do this from the menu by choosing Run, Debug Main, or you can click the debug icon on the toolbar. Either way, when you get to the breakpoint, your application is suspended, and a debug window opens at the bottom of the screen with a Debugger tab and a Console tab, and you can click back and forth between these to see what's happening. Now, to step through your code one line at a time, click the Step Over icon, and each time you click through, you'll be running the code. Now, as variables are being set, you'll be able to see their values in a couple of different ways. Notice that the value of welcome is now displayed to the right of the code. That's being generated by IntelliJ IDEA. You can also move your cursor over the variable, and after a moment, you'll see the value displayed there as well. You can also add a variable to the Watches window. I'll select the variable by double-clicking it, then I'll right-click on it, and I'll choose Add to Watches down here. And that adds that variable to my Watches window, and if there are any changes to the variable, I'll see it here. While I'm at it, I'll also add the variable Cars to my Watches window. Again, I double-click that value to select it, and then I'll add to Watches, and I'll do the same thing for the variable I. You can even debug full expressions. I'll select the string Cars, open bracket, I, close bracket, and I'll add that expression to my Watches view. If an expression can't yet be evaluated, you'll get a message to that effect. But now, as you step through your code, as the expressions are filled in, you'll see them update down here. Now I'll step over a couple more times. When I click once, my Cars array is initialized. I'll move the cursor over the array, and I see the little pop-up appear, and then I can click on the plus icon and see the items within the array. I can also see that information down here in the Watches view. Now I'll step through the for loop. Again, I'll use step over for this, and each time I step over, the value of I is updated, and the value of Cars, open bracket I, close bracket is also updated. I'll step a couple more times and see the value updated again. Now I'm going to add another breakpoint. This will be on line 11, where I'm outputting the current character. Then I'll right-click on the breakpoint, and a pop-up appears, and I'll set the condition to I == 7. So I'm setting a condition, and I'm saying only suspend my code when this condition is true. I'll click Done. Then down here, I'll click on this left-pointing arrow, and that's the Resume Program button. And this time, I'll continue executing my code until I has a value of 7. I'll verify that over here in the Watches view, and I'll see that the value of Cars I is the exclamation mark. That's the character that's at that index position. Also notice now that all the variables are displaying their values in the code window. If you want to interrupt your debugging session, you can click on the Stop button down here. And then all that information goes away, and the Watches view still shows the items you're watching, but it doesn't show any values. If you want to clear out your Watches view, select all of your watches and click on the minus icon. And then you can get rid of your breakpoints, and you're back where you started. So those are some tips about how to debug your Java code using IntelliJ IDEA. Again, if you're using another IDE, the steps will be a little bit different, but the features should work pretty much the same for NetBeans, Eclipse, and other full-blown integrated development environments. Whenever you write code that could potentially throw an exception at runtime, you can wrap that code or surround it in a try-catch block. And I have code here that's going to throw an exception. This line of code on line 10 tries to get a character from an array, but it uses the expression cars.length, looking for an item in the length index instead of length -1. As we've seen previously, that's the wrong way to do it. And when I run the code, I get that exception, with an exception object that's an instance of the class ArrayIndexOutOfBounds Now, to fix this, I'll wrap these two lines of code in a try-catch block. I could type in the code, but IntelliJ IDEA can generate the right code for you. So I'll select those two lines of code, then I'll go to the menu and I'll choose Code, Surround With. Then, from the list that appears, I'll choose Try-Catch. That wraps the two lines of code that I selected inside a try block and then creates a catch block right underneath it. If the catch block is reached, it's because an exception has been thrown, and the exception object that's associated will be passed into this block as an argument. The data type will be exception initially, and the name or identifier for the exception object is E, lowercase. Now, the exception class is interesting. I'll click into the name of the exception class and then press Shift F1 to get to the documentation. The exception class is in java.lang, and it's the superclass for a whole bunch of specialized exception classes that are suited for particular issues that can happen when you're executing certain functionality in Java. There's an exception class called activation exception, general security exception, naming exception, and so on. So back to my code. In order to see what happens, I'll add breakpoints here and here so that I can know exactly what code is being executed. Then I'll run the code in debug mode. If I see this dialog, I'll click Yes, and I jump to the breakpoint where I'm outputting the stack trace. That's the list of exceptions that happened when the code stopped. I'll step over, and then I'll look at my console, and I see the output from the call to print stack trace. That's a method of the exception object. So now I'll stop the code, and I'll fix my problem by adding -1 to the expression for the index. And I'll run in debug mode again. And this time, I get to the code that wants to output the last character to the console. I'll step over, and I'll look at the console, and I see my exclamation mark is output. So I'll stop debugging again, and let's go back to the code. When you generate a try-catch block from within IntelliJ IDEA, by default, the object that's passed into the catch block is typed as exception. But because I ran the code, I know that it's a subclass of exception, specifically array index out of bounds exception. So I'm going to change the data type to array index out of bounds, and notice that this exception class is also in java.lang, so I can use it without importing it. Then I'll change my code back so that it generates the exception again. I'll remove -1, and I'll run in debug mode again, and once again I get to print stack trace. So that's the basics of the try-catch block. The try-catch block can change your execution path. If your code is successful, you'll execute all the code in the try block and then jump past the catch block. But if you run into one of the particular exceptions that you're handling, such as array index out of bounds exception, then your code path diverts to the catch block and you'll execute that code instead. Either way, your application should then run to completion. When you wrap a bit of code in a try block, you can actually have more than one catch section. Each catch block should look for a specific exception, and then your code path will change depending on which exception is generated. In this project, multi-catch, I still have code in place that's generating an exception. I'm looking for a particular character from a character array, but this expression, cars.length, will look at an index greater than the available number of items. And when I run the code, I'll hit my catch block and print the stack trace. To make it clear that that's what's happening, I'm going to comment out this line of code by pressing Ctrl/ on Windows or Command/ on Mac. Then I'll replace it with custom output, and I'll simply display my own custom message, array index problem. Then I'll run the code again, and I see my custom message is displayed, so that confirms that the try-catch block is working. Now I'm going to add a bit more code down here, still within the try block, but after the existing code. And I'm going to cause another problem. I have this string named welcome, and I'm going to try to extract a substring from it. I'll create another string that I'll call sub, and I'll get its value by calling welcome.substring. And I'll pass in a beginning index value that's greater than the length of the string. So I know that that's going to generate an exception. Now at the moment, I'm not even getting to that line of code. Before I can do that, I hit this line, it generates an exception, and that causes me to jump to this line. So I'm going to fix my first exception. I'll add -1 to that expression, and now that code should work correctly. and I'll run it. And this time I get my exclamation mark. That's the last character in my character array, but I get to my new exception. This exception is being caused by line 14, and the exception object is an instance of the class stringIndexOutOfBoundsException. I'll copy the name of that exception to the clipboard. Then I'll go back to my code, and I'll add another catch block right here. Within the parentheses, I'll paste in the name of the exception I'm looking for, and I'll give it a name of E. I can reuse that variable name because its scope is limited to the current code block. The variable E that's passed into this catch won't be around if I get into this catch block. Then I'll make a copy of this bit of code, and I'll paste it here. And for this catch block, I'll output a custom error of string index problem. And once again, I'll run the code. And now I get to the second catch block. Now, if I run into another exception that I haven't anticipated, I might still get a fatal exception. But I've handled both of the exceptions I know my code might generate. And that's the important thing in writing error handling code. Identify all of the different exceptions that your code might generate, and then write catch blocks for each one of those. And that makes your code more robust and more likely to survive when the application is running. I've described how to handle exceptions that are thrown by the Java runtime and its core libraries, but you can also generate your own exceptions and give them custom error messages. I'm working in a project named Throw, and I'm starting with code similar to what I had in the last one. I've declared an array of characters, and then within a try block, I try to get a value from the characters array. If I survive that, I then try to get a value from a substring. In either case, I could throw an error, and I have two catch blocks to handle the different errors, one for an array index out of bounds exception and one for a string index out of bounds exception. If you want to throw your own exceptions, you can either use the core exception class or create your own custom exception classes. I'm going to stick to the core exception class here, and I'm going to add some code within the try block. I'll add a bit of conditional code. I'll start with the keyword if, and then I'll set my condition to cars.length less than 10. Now this is an arbitrary condition. It doesn't make any real sense for the application I'm working on, but my goal here is to show you how you can generate and throw your own exception. To throw an exception, call the throw method. Then, in a pair of parentheses, pass in an exception object. I'm going to instantiate an exception object with the keyword new and the exception class's constructor method. Notice that the constructor can take a string as a message. I'll pass in a literal string of my custom message. Now, when the code encounters the throw statement, the path of execution will shift to the catch blocks, and Java will look for a catch block that catches this exception. If it doesn't find one, then the exception will be fatal. But notice that I have an error indicator. That's because when you explicitly throw an exception, you have to handle it one way or another. I'll click on the link to see my choices, and I see that IntelliJ IDEA is offering to add a catch clause. I'll choose that, and a new catch block is added at the end. And this is for the exception class. I'll replace the automatically generated code that calls print stack trace, and instead I'll output my custom message using e.getMessage. And now I'll run the code again, and I see my custom message. So I never got to this bit of code that's trying to use the array, or this bit of code that's trying to use the string. When I executed the throw statement, that threw me into the catch blocks, and finally, the code went to this catch block that handled that particular exception object. So this is how you can structure your error handling to handle different kinds of exceptions. As you explore the Java class library's API documents, you'll find that certain methods tell you this method can throw this kind of exception, and it's up to you to add the code to your application to handle those exceptions elegantly. In all programming languages, writing conditional code is a common practice. Conditional code is commonly called an if-then or if-else statement. I've already used if statements previously in this course. It's pretty unavoidable. But now I'll go into the details of the if keyword, its associated keyword else, and how to put these keywords together. I'll start by declaring an integer value named month number, and I'll give it a value of 8. Then I'll write some conditional code to evaluate it. I'll start with the keyword if. In order to evaluate a condition, you place it within parentheses. The parentheses are required. Then you write the condition. I'm going to ask whether the month number is greater than or equal to 1, and it's less than or equal to 3. The double ampersand operator is the logical AND. The double pipe character, that's the character on the backslash key, is the logical OR. I'll add my braces, and then I'll add some output to the console, and I'll output the string, "You're in quarter 1." Now, because my condition turns out to be false, 8 is not greater than or equal to 1 and less than or equal to 3, I don't get any output at all. So now I'll add another condition. I'll start with the keyword else, and then the word if. And then I'll add another set of parentheses and another expression. This one will be very similar to the first one, so I'm just going to copy and paste it. And I'll change the numbers I'm looking for to 4 and 6. Then I'll add my braces, and I'll copy and paste my output, and I'll change the quarter to quarter 2. Then I'll copy and paste my else-if clause twice. I'll start copying with the keyword else, and finish with the closing brace. Then I'll paste it in here, and paste it in again. Then I'll change my numbers. For the third one, it'll be 7 and 9, and that means I'm in quarter 3. And for the last one, it'll be 10 and 12, and that'll be for quarter 4. I'll run my code, and I get back the expected feedback, "You're in quarter 3. But what happens if none of these conditions are true? At the end of all this, you can add an else clause. And within the else clause, you can put in whatever code you like, and I'll output the string, "That's an unknown month." Then I'll come up here and change my month number to 13, and I'll run my code, and I get the else statement. So each if clause can have any number of else-ifs, but it can only have one else, and the else clause goes at the end of the whole thing. The rules for an entire if-else block are that only one of these blocks can be executed, and as the flow of execution goes into one of those blocks, the rest of the blocks will be ignored. This is pretty conventional if-else logic, and the syntax matches what you see in most C-style languages. Some of the critical things to remember are that your conditions must be wrapped in parentheses, and each condition must be a valid Boolean expression. It's also worth mentioning that if you're only executing a single statement, you don't really need these braces. You could eliminate them, and then only the first statement after the if clause will be executed. But I usually include the braces for readability. The if and else keywords give you complete flexibility in writing conditional code, but you can sometimes write conditional code more efficiently using the switch statement. A switch statement examines a single value and then compares it to multiple possibilities, and you can control the flow of execution based on when the two values match. I have code in place to collect a value from the user. I then parse that value as a primitive int. I'll run the code for the first time and show that in the run window I can click here, type in a number, and then the application finishes, but nothing else happens. My goal is to examine that value. I'll place the cursor after the existing code, and I'll add the switch keyword. IntelliJ IDEA adds parentheses. Place the value you want to examine within the parentheses. I'll place the value month number. Then add a pair of braces. That's the switch code block. Now within the switch code block, you can have one or more cases. Each starts with the word case, and then a value that you want to match, followed by a colon. Then the code that you want to execute goes after the case statement. Unlike the if statement, you don't use a pair of braces here, you just place the code after the colon. In this case, I'm going to output to the console a string. The month is January. After all of your executable code for this case, be sure to add a call to the break statement. That means I'm finished with the entire switch statement and I want to go to the end, and your execution will go to the last parentheses and continue from there. Now I'm going to copy and paste these 3 lines of code, and I'll make 2 more copies, and I'll change the values that I'm examining to 2 and 3, and I'll change the months that I'm outputting to February and March. To handle any other cases, use the default keyword and add code here that'll be executed if none of the other cases are true. I'll output, you chose another month, and I'll run the code. I'll type in a value of 2 and press enter or return, and I get the month is February. I'll run again, and this time I'll type 8, and I get you chose another month. When using a switch statement, be sure to include the break statement at the end of every case. Otherwise, your code execution path will continue through the other cases. For example, if I were to comment out this break command and then run the code, then press 1 and enter or return, I would see both January and February because I haven't told the code execution path to break out of the switch statement. So I'll get rid of that comment. Prior to Java 7, a switch statement could only examine primitive numeric and character values. But starting in Java 7, switch statements can now work with strings. To show this, I'll make a copy of this class. I'll go to my project window, and I'll right-click on the main class and copy it. Then I'll go to the package, and I'll right-click and paste. And I'll name the new class Switch Strings. And I'll change my code. In this class, I'll say enter a string, and then because I'm going to evaluate it as a string, I don't need to convert it to a number. Then I'll change the value that I'm examining in the switch statement to input. Then I'll change my cases. For brevity, I'll look for 3-character strings: Jan, Feb, and Mar. Then I'll change the output to 1, 2, and 3. And then I'll run the code again. Now this time, I'll go to the menu and choose Run, and then the second Run choice, and I'll choose Switch Strings to create a new Run configuration. I'm running that code now, and I'll click into the Run window, and I'll type Jan, and I see the month is 1. I'll run again, and I'll click here, and this time I'll type APR for April, and I get you chose another month. So again, using the switch statement on strings is something you can do in Java 7 and later. In Java 6 and earlier, you could only do this with primitives. Java provides a number of ways of looping through collections of data. In this project, loops, I've declared an array of strings. The brackets after the data type string means that this is an array of values. And the array has 12 items, 1 for each month of the year. I'll demonstrate how to loop through this data using 4 different types of loops: an incrementing loop, a for each loop, a while loop, and a do while loop. I'll start with an incrementing loop. To create the skeleton of an incrementing loop in IntelliJ IDEA, type for I and press enter, and that will use a code template. An incrementing loop has 3 statements between parentheses. The first declares a counter variable, a starting point. The second is a condition, and the loop will continue as long as that condition is true. And the third part is an incremental statement. I++ means increment the value by 1. I'll set my condition to I less than months.length. So I'll keep looping as long as the value doesn't match the length of the array. Remember, this is a 0-based array, so when they match, it means there's not an item in that position. Then within the loop, I'll use output to the console, and I'll output the value using array syntax with months, bracket, I, close bracket. So I'm retrieving the value at that index position of the array. I'll run that code, and I'm printing out the months one line at a time. One of the advantages of an incrementing loop like this is that you can work through the array from end to beginning. I'll select and duplicate those lines of code, then I'll comment out the original version. And I'll change the new version as follows. I'll set the initial value of my counter variable to months.length minus 1. I don't want to start at 12, I want to start at 11, again taking into account the zero-based indexing. Then I'll change my condition to I greater than or equal to 0. So I'll keep looping as long as there's an item available at that index. And I'll change this statement to decrement the value with I minus minus. I'll run the code, and now I'm printing out the months in reverse order. So that's the incrementing for loop. The next kind of loop I'll demonstrate is called a for each loop. I'll start with the keyword for. Then, within the parentheses, I'll declare a variable of the data type that matches the items in the array. And I'll name it month in this case. Then I'll put in a colon, and then the array name, months. Within the braces, I can now address that variable, and the iteration is now being handled for me. I don't need to keep track of a counter variable. Once again, I'll print out the month, this time using the variable that's being set each time through the array. I'll run the code, and there it goes. So a for each loop is syntactically a little bit more simple, but it's not quite as flexible as an incrementing loop, as I showed you. Next is a while loop. A while loop examines a condition and then keeps on looping as long as the condition is true. I'll start here by declaring a variable that I'll name counter, and I'll give it a value of 0. Then, on the next line, I'll type while, and then within the parentheses, I'll set a condition of counter less than months.length. I'll create a set of braces as a code block, and then I'll output a value using months, and then counter as the index. Now, with a while loop, the counter won't be incremented for me. I have to do it myself. And I'll do that with counter plus plus. So each time through the loop, I print the month, and then I increment the counter, and the next time around, that condition will be evaluated again. I'll run the code, and there's the result. And finally, there's the do while loop. This kind of loop is used less commonly than the others, but it is available. I'll copy and paste my while loop, I'll comment the original version out, and then I'll change the code as follows. I'll take my while condition, and I'll cut and paste it to the end of the code block. And then at the beginning of the code block, I'll add the keyword do. Notice the squiggly line at the end of the while statement, and that's because I need to finish this kind of statement with a semicolon. So now I'm saying, do this, then increment the value, then evaluate the condition. Functionally, it works just as well as a standard while loop. It just takes a little bit more code, and it moves the condition evaluation to the end of the statement instead of placing it at the beginning. Most programming languages support the ability to create reusable code blocks that you can call from multiple places in an application. These are sometimes called functions or subroutines, but in Java they're called methods, and they're always declared as members of a class. The main method is one example. This is the signature of a method that you have to start up an application from the console. But not all Java applications use this main method. For example, an Android application or a Java EE application have different requirements. Regardless, you can create your own custom methods and then call them from anywhere in your application. I'll declare a new method, and I'll place it outside of the existing main method, but still within the class declaration. In order to call this method from my main method, I must declare it initially as static. Then I have to declare what kind of data the method is going to return. I'll say void, which means it's not going to return anything. Then I'll name the method loopit and add parentheses. If you want to pass in arguments or parameters, you would declare their types and names here. After the parentheses, you place a code block, a pair of braces, and then the executable code for the method goes there. Now I'm going to take this existing code, and I'll cut and paste it, and place it within my new custom method. Then I'll go back to the main method, and I'll call my new method by calling loopit. Notice that IntelliJ IDEA already knows about the method and helps me complete the typing. I'll remove some extra space here to make this as concise as possible, and then I'll run the code. And there's the result. When you declare your methods, you can also declare arguments. I'll place the cursor inside the method declaration, and I'll declare one argument, a string that I'll name label. Then, within the method, I'll output that string using system output, and I'll pass in the label as the argument to println. I'll run the code again, and I get an error, and that's because I changed the signature of the method here, but I didn't change the way I was calling it here. So, to make them compatible with each other, I'll add in a literal string. I'll run the code again, and then I'll scroll back up to the top of the result, and there it is, months of the year. Right now, this custom method isn't doing much. It's just taking information and outputting it. But let's say you wanted to operate on the value in some way. I want to print a line of asterisks right below the label, and I want it to be exactly the right length, the same length as the label itself. So I'm going to create an incrementing loop, and I'll keep looping until I get to the end of the label. Within the for loop, I'll use system.out.print, and I'll output a single asterisk character. Then, at the end of the loop, I'll do one more print, and this will be with println, and this will serve to simply print a line feed. And there's the result. A label and a line of asterisks below the label that's exactly the right length. Finally, I'll demonstrate that I can call this method any number of times. I'll duplicate it a couple of times, and then I'll change the labels to second run and third run. And notice that the three strings are different from each other and have different lengths. I'll run the code, and I see that I've called the method 3 times, and each time the appropriate label is printed and a row of asterisks is printed that's exactly the right length. I'll talk a little bit more later about how to use methods that return values, but this example gives you an introduction for how to declare your own methods and how to accept values as arguments and execute code based on those arguments. Java supports the concept of method overloading. That means that you can create more than one version of a method. You just have to distinguish them from each other by the number of arguments or the argument's data types so that the Java runtime knows which method to call. In this project, I've declared 2 methods named getInput and addValues. They both receive arguments. The getInput method receives a string named prompt, and it displays that prompt, then creates a scanner object, and uses the scanner object to return a value. The addValues method receives 2 string arguments. It parses those values, adds them together, and then returns the result. Notice that both methods have data types set as their return types. GetInput returns a string, and addValues returns a double. And they're both marked as static so that they can be called from my static main method. Now, I'm going to create 2 more versions of the addValues method. I'll copy and paste the original version. Notice when I paste it, I get the squiggly lines on both versions of the method. That's because they have identical signatures. I have to do something to distinguish them from each other. And I'll change the new one so that it receives 3 string values instead of 2. Then I'll duplicate this line of code, and I'll change the names of the variables, and then I'll add the values together, and I'll return the result. Notice that the name of the new method is dimmed out. That's a visual indicator from IntelliJ IDEA that that method isn't yet called anywhere in your code. But I'll come back to my main method, And I'll duplicate a line of code here, and I'll collect another value, and then I'll copy and paste these lines of code. I'll change the name of the result to result2, and I'll pass in all three values. And then I'll change the label so I can distinguish between them. So on the first call to add values, I'll be calling my original method, and on the second one, I'll be calling the new method. I'll make sure I'm displaying the right result, and now I'll run the code. And I'll enter three values of 2, 3, and 4. And the result for the first operation is 5, and for the second one it's 9. And again, you aren't just distinguishing by the number of arguments, you can also distinguish by the data types. I'll also show you how to create a method that receives an indeterminate number of arguments. I'll once again create a static method that returns a double value, and I'll name it addValues just like I did before. And once again, I'll receive a string value, but this time instead of naming it immediately, I'll put in 3 dots, an ellipse, and I'll name this values. That means that the user can pass in as many values as they want. Then I'll work with the collection of values that's passed in. I'll use a for each loop. Within the for each loop's declaration, I'll get a string that I'll name value, and I'll get it from values. Now before I do that loop, I'll declare a variable that I'll name result, and I'll give it a value of 0. Within the loop, I'll declare a double value named d, and I'll get its value from double.parseDouble, and I'll pass in the value variable, that's the string. Then I'll add that value to the existing result, and I'll use an operator called plus equals. That means add this to the existing value. Finally, at the end of the loop, I'll return the result. So now this method can be called with any number of arguments. And I'll make a copy of these 2 lines of code and paste them in. I'll change the name of this variable to result3, and I'll change the value that I'm outputting and the label, and this time I'll pass in 6 values. I'll take these arguments, I'll put in an extra comma, and I'll paste those in. So now I'm adding all of these values together twice. I'll run the code, and once again I'll enter some values, 2, 3, and 4. And now I see that the answer for 3 values is 9, but the answer for many values is twice that, 18. So Java gives you quite a bit of flexibility in how you build your code. You can build just one version of a method, or you can build overloaded methods, distinguishing them from each other by the number and data types of their arguments. One of the questions you have to answer when you learn a new programming language is whether arguments passed into a method are being passed by copy or by reference. Let's define these terms. When you pass arguments by copy, that means you're passing a variable into a function or a method, and within the method, a copy of the variable is received. It's not attached in any way to the original value before it was passed in. And when you pass into a method by reference, that means you're referring to the original object, the object that existed outside the method, and if you make any changes to the object within the method, it will affect whatever was passed in originally. In Java, variables are always passed into methods by copy. But there are certain behaviors that can make you think you're passing by reference. I'm going to describe 3 scenarios and explain how each of them proves the point that arguments are passed by copy. Let's take the simplest scenario, passing primitive values. When you pass a primitive value into a method, a copy of the original value is made, and any changes inside the method won't change the original. Here's a custom method named incrementValue. It receives an integer value named inMethod. Then within the method, it's being incremented by 1, and then that new value is being output to the console. In the calling code, I start with a variable named original with a value of 10, and I output that original value. Then I call my custom method and pass in the original value, and then I reprint the original value again. With primitive values, it's pretty straightforward. The original value is not affected. The change is made to the copy of the value inside the method. but the original value stays the same. But now let's take another example. Primitive values wrapped in complex objects. In this example, my custom method receives an array of integers. The array is a complex object. The values that are referenced by the array are still primitives. Within the method, I'm incrementing the first item in the array by 1 and then printing out its value. Here's my calling code. I create an array named AROriginal. It has 3 items, 10, 20, and 30. I print out the first item in the array, then I call the method, then I print out the original first item again. In this example, I'm making a copy of the array. That's what I'm passing in. But the new array is still referencing the original values that are stored in the outer scope. So, in the original print, I get 10. Within the method, I get 11. But when I return to the outer scope, the original value has now changed. And let's take a third example, an object variable or reference variable. Remember that I've mentioned that reference variables point to an object in memory. So when you pass the variable to the function, a new variable is made, but it's pointing to the original object. And so you now have 2 references pointing to the only object. And if you change the object, it's pretty obvious what's going to happen. Here I'm starting off with an array. It has 3 items. And here's a diagram showing the location of these items in memory. There's item 0. And when I reference the object from within the method, also using an index of 0, I'm pointing at the same object. So when I return, it's not surprising that it's changed. Now strings are a special case. Let's take a look at this example. I have a method named changeString, which receives a string as an argument. Within the method, it changes the value to a new string and prints it out. Here's my calling code. I create a variable named original and print it out. Then I call my method and I pass the value in, and then I return and I print it out again. And in this example, the string does not change. The string data type is a contrary example. With most complex objects, changing the object within the method would have changed the object outside the method. But as I've mentioned previously, string values are immutable. Once declared, they cannot change. So this is a different behavior that you'll see with strings than with other complex values. When you pass a string into a method, a copy of the entire string is created within the method, and it's detached from the original value outside the method. In this challenge, I'll ask you to create another calculator application. As with the previous calculator application, I'm prompted for 2 numeric values. I'll type in one and then type in another, but this version of my calculator can execute addition, subtraction, multiplication, or division. I'll type in the operator that I want to use. I'll use minus for subtraction, and I get back the result. I'll run the application again, and this time I'll execute another operation. I'll start with a value of 10, and then I'll put in a second value of 2, and then I'll divide, and I get back the answer. This application has a little bit of error handling going on. I'll run the application again, and this time I'll enter a value that's not numeric. It doesn't matter which one I enter, either will cause the error to be triggered. I'll enter a numeric value for the second one, and then I'll choose an operation, but I get back this error message. This is a customized error message. I'm not just calling print stack trace, so you can tell I'm using the try and catch blocks to elegantly handle the errors. And there's one more issue that this is handling. This time I'll enter 2 numeric values, but I'll then enter a value that's not an operation, and I get back unrecognized operation. In the next video, I'll show you how I solved this programming challenge, but I'll suggest that you break down each operation into its own method. Use a switch statement to determine which operation to execute, and then wrap all the code within a try-catch block to catch numeric formatting problems. In this challenge, I asked you to create a complex calculator application that executed any of the 4 standard mathematical operations. Here's how I solved the problem. First, I have an import statement at the top of the code for the scanner class. As I've done in previous exercises, I'm using the scanner class to let the user type in values. And down here at the bottom of the code, I have a getInput method. It receives an argument, a prompt. It prints that prompt to the console, creates a scanner object, and then returns the user's input to the calling scope. In the main method, I'm calling that method twice to get the 2 numeric values. And then I'm calling it again to let the user choose an operation. So by the time I get to line 12, I have everything I need to process the request. At this line, I'm declaring a double value, and I'm initializing it to a value of 0. Now I'm doing it here because once I get into the next block, I don't want to declare the variable. I want the variable to be available for the entire main method. So by declaring it before I get into the try block, its scope will be as broad as I need it to be. Next, at line 14, I'm starting a try block. And within the try block, I have a switch statement. There are 4 cases and 1 default. Each of the cases is calling one method. There's a method named addValues, one named subtractValues, and so on. Now, you could have done this with a single method named, say, calculate, and let it pass in 2 values and the operation, and then have another switch statement inside that method. But I find breaking things down into small pieces a lot more maintainable. So my 4 methods are at the bottom of the code down here. There's addValues, subtractValues, and so on. Within each of these methods, I'm parsing the values to get the double values. Then I'm doing my mathematical operation and returning the result. When you call the parseDouble method, you can get an exception. If you don't handle the exception at this level, the exception bubbles up through the call stack. And then you'll have to handle it here. And that's where I've placed my catch block, at the top level of the code. So I only have to handle the exceptions once, even though they might happen in any of the 4 methods. And to print out my method, I'm starting with a literal string, number formatting exception, and then I'm printing the exception object's message. And that's where I'm getting the information about the specific value that wasn't parsable. Finally, this is how I'm handling the situation where the user types in a character that's not a recognized math operation. In addition to the 4 cases, I have a default section. And if I hit that code, I simply output a message and then call return. And that means leave the main method, which means finish the application. So that's my version of the code. Take a look at what you came up with and compare it to mine and see what kind of variations there are in solving programming problems. I've used simple arrays a number of times in this course, but I'd like to talk a little bit more about them. They're one of the easiest ways to store ordered data in Java, but there are certain limitations. I'm working in the project Simple Arrays, and I'll add a bit of code here, declaring an array of primitive values. Arrays can point to any kind of variable, primitives or objects. I'll declare a set of integers. I'll start with the data type int, and then add a pair of brackets. And then I'll set a name for the array, ints. You can actually place the brackets either after the data type, or you can place them here after the array name. You shouldn't do both, but it's preferred to place them after the data type. Now I'll initialize the array's value with a pair of braces, and I'll add in a comma-delimited set of values that match the data type, 3, 6, and 9. This array now has 3 values. The array is not resizable. Once it's been set, its size can't be changed, but you can change the values at each index position. Next, I'll use an incremental loop, and I'll loop through the array, and for the second part of the loop declaration, I'll set a ceiling of ints.length. And then within the loop, I'll output the value at that position. So I'm starting at 0 and going through 2. And the result is outputting values of 3, 6, and 9. Now let's see what happens if I change the values. I'll set the values initially as 9, 6, and 3, and then I'll run the code again, and I see that the array order is exactly what I declared. But it's also possible to sort an array. So now I'll use a class named arrays, and I'll call the sort method. Notice that there are versions of the sort method for all the different primitive data types. And there's also a set of methods called parallel sort. Those were added in Java 8. I'm going to just choose the sort method, and I'll pass in the ints array, and then I'll run the code again, and I see that after sorting, the values are back in ascending order, from 3 to 9. An array can point to any sort of object, and I'll use the object that we use the most, a string. I'll declare a string array. I'll name it strings. And once again, I'll start with a pair of braces, and I'll add in 3 values, red, green, and blue. Then I'll use a for each loop to loop through the values. Each time through the loop, I'll be working with the string, and I'll name it color. And I'll get its values from the array that I named strings. Within the loop, I'll output the color value. And I'll run the code, and I see red, green, and blue. But now let's see what happens when I sort that array. Once again, I'll use arrays.sort, and I'll pass in the array. And I'll run the code, and this time I get blue, green, red. The colors are now in alphabetical order. When you declare an array, you can set the initial size without declaring the values. Just as before, I'll start with the data type. I'll use int again, and I'll name this array sized. And now, instead of using braces, I'll start with the keyword new, and then the data type again, and brackets, but this time I'll pass in a numeric value. That's the number of items that I want to be available in the array. Then I'll use a for each loop. Each time the loop, I'll be looking for an integer, and the name of the integer will be value, and I'll get that value from the sized array. With an array of primitive values declared in this way, the values will all be the default for that data type, 0 for the numeric primitives, false for booleans, and so on. But now I'll add a bit of code before this, and I'll set the values explicitly. I'll add an incrementing loop, and I'll loop from 0 to the size of the array, with sized.length. Then within the loop, I'll set the value of the item at that index. I'll use the expression sized and then the index in brackets, and then I'll set the value as I times 100. And I'll run the code again, and I see that the values have been updated as I expect. Notice that the first value is still 0. It's the value I times 100, which is still 0. But then each of the other index values has also been multiplied by 100. Finally, I'll describe how to copy an array using a method of the system class called reccopy. I'll declare another integer array, and I'll name this one copied. And as I did before, I'll use the keyword new and the data type again, but I'll set the size of this array to 5. Then I'll call system.arrayCopy. This method takes 5 arguments. The first argument is the original array. Then there's an integer, which is the beginning position from where you want to copy. Then the third argument is the destination array, and then a beginning position where you want to copy to, and a length, the number of items you want to copy. I'll pass in sized and 5, meaning that I want to copy from the sized array starting at index 5, halfway through the array. Then I'll set my destination array to copied and pass in values of 0 and 5. I'm copying to the range starting at 0, going through 5. Then I'll output the results. I'll use a for loop, and I'll start with int, then value, then copied, and then within the braces I'll output the value. Notice I'm reusing the variable value because its scope in the original declaration was limited to this for loop, so I can reuse the variable name. I'll run the code, and I see that my copied array has the values starting at 500. Java supports the use of multi-dimensional arrays using the same sort of syntax that you use with simple arrays. But instead of using a single pair of brackets, you add brackets as you add dimensions to the array. In this project, multi-arrays, I'll declare a string array, and I'll start with a pair of brackets, just like I did before, but this time I'll add a second pair of brackets. This will be a two-dimensional array. I'll name the array states, and then, as I did before, I'll initialize it with the new keyword and the data type. But this time, when I select the data type, IntelliJ IDEA adds two pairs of brackets to match the original declaration. And I can set the size of both dimensions of the array here. I'll set the outer array as 3 items, and each item within that array will have 2 sub-items. And so now I have a two-dimensional array. Next, I'll set the values. I'll reference an item in the array starting with the array name, and then once again 2 pairs of brackets. For the first pair, I'll set the index of the outer item, and for the second pair of brackets, I'll set the index for the inner item. So this is the first sub-item in the first outer item of the array. And these have to be string values because I said every item in the array is a string. I'll set this value to California. Now I'll duplicate that line of code, and I'll set the index for the second item to 1. And I'll set that value to Sacramento, the capital of California. So this is my data structure. Each item in the outer array will be a state, and each item within the inner array will be either the name of the state or its capital, depending on the index position. Now I'll select those 2 lines of code, and I'll duplicate them twice. Then I'll modify the index for the outer array. The third and fourth lines will be for the second item in the outer array, so I'll use an index of 1 for those, and the final items will have an outer index of 2. Then I'll change the values. Next, I'll loop through the array using an incrementing loop. I'll use for I, and that creates the loop structure, and I'll set the ceiling of the loop as states.length. The length property refers to the outer array, so I should iterate through this loop 3 times. Within the loop, I'll declare a string builder object. I'll name it SB, and I'll initialize it with its constructor method. Then I'll call the append method of the string builder a number of times. I'll call sb.append, and I'll pass in a literal string of the capital of. Then on the next line, I'll add .append, and I'll add the name of the state. And I'll use 2 pairs of brackets for this. The first pair of brackets will refer to the current state within the loop, and the second index will be 0, the first sub-item within that item, and that'll be the name of the state. Then I'll call .append again, and I'll add another literal string, and this will be the word is with spaces around it. Then I'll append again, and this time I'll refer to the capital. I'll copy this expression that refers to the state name. I'll paste it in, and I'll change the index. And finally, I'll append a period. And that completes my statement. Then I'll output the result with system.out.println, and I'll pass in the string builder object. And when I run that code, I get 3 lines of output indicating the capital of each state. So you can add more dimensions to an array, but practically speaking, I've never found that I need to go to more than 2 dimensions in an array. The Java Collections Framework is a set of interfaces and classes that make it easy to manage data in your applications. You can manage either ordered or unordered data, and you can use one of 4 categories of classes. Each of these categories is represented by an interface named set, list, deck, and map. I'm going to focus in this course on 2 of the most commonly used classes from this framework, ArrayList and HashMap. And these are both implementations of 2 interfaces. ArrayList implements list, and HashMap implements map. I'll start with ArrayList in this project, and I'm starting with an empty main method. First, I'm going to declare a list. The list interface is a member of the package java.util. When I select it, I get an import statement at the top of my code. Each of these collection objects, including lists and maps, can contain as many items as you want, but it's good practice to declare what type of item they're going to contain, and you do that with something called generic notation. This is called the diamond operator, and within the diamond operator you declare the type of the items that you're going to add to the list. I'm going to add strings. Each item within a collection must be an instance of a class. If you want to contain integers, you would declare integer, the helper class for int, not the int primitive itself. Now I'll give this object a name, and it'll be named list. Then I'll use equals and new, but then instead of declaring list as the constructor, I'll use the implementing class or the concrete implementation of the class. That'll be array list. I'll finish this declaration and then point out a few things about its syntax. First, when I selected array list, I got an import statement at the top of my code. This is also a member of java.util, so to use the class, you should import it. Next, notice again that I'm using the constructor method for the array list class, not for the list interface. While it's possible to create an instance of an interface, you would have to completely implement all of its code. If you want to use a list object that's built into the Java framework, use ArrayList. An array list contains an ordered collection of data. You can think of it as a resizable array. When you declare the array list, you can declare it with a constructor with no values, and then the array list will grow as needed. Or if you already know how many items you're going to add to the list, you can pass in an integer value, and that would result in more efficient allocation of memory. I'm going to leave this to an open number of items. Also notice that you don't have to pass in the data type of the items again. This was something that was introduced in Java 7. Prior to Java 7, you would have had to add a declaration of the data type again, but it was redundant. So in Java 7, you can simply say, use the same declaration as I did before. Now I'll add some items to the list. All implementations of the list interface have a method named add. They also have methods named addAll, clear, contains, get, and so on. I'll call the add method, and I'll pass in a name of a state. I'll complete that statement, then duplicate this line of code a couple of times, and then I'll change the values to Oregon and Washington. Then I'll output the list. Then I'll run the code, and I see the data listed in the order in which I declared it. Now, when I pass the list object into println, I'm actually calling the toString method of that object, and that method outputs a pair of brackets and then the values separated with commas. I'll describe later how to use your own iterating code to loop through the data on your own. Next, I'll add another item to the list. Once again, I'll call list.add, and this time I'll pass in Alaska. And then I'll duplicate this line of code, and I'll move the new version down, and I'll run that code again. And I see that I've updated the list. Now I'll show how to remove an item from the list based on its index position. I'll call list.remove, and I'll pass in an integer value of 0. Then once again, I'll output the list, and I'll see that California has been removed, and all the other items in the list have moved up a position. Next, I'll describe how to access a single item from the list. I'll declare a string that I'll name state, and instead of using bracket notation as you would with an array, call a method of the list interface named get, and pass in a value. I'll pass in a value of 1, and then I'll output the second state is, and then I'll append state. Notice I'm using an index value of 1, but I'm outputting the second state, and that's because of the zero-based indexing that's used in lists and in arrays. And the result is displaying that the second state is Washington. And finally, I'll show how to find an item in the list. I'll create an integer that I'll name POS for position, and I'll call list.indexOf, and I'll pass in Alaska. I'll make sure that I've spelled it correctly because in order to find this object, Java is going to intern the string. That is, it's going to look up that string in its list of string objects. Then I'll output Alaska is at position, and then I'll append my integer value. And I get back Alaska is at position 2, and that's correct because of the zero-based offset of the indexing. There's a lot more you can do with lists and array lists, and I encourage you to look at the documentation. I'll click into the interface and press Shift F1 to go to the docs, and notice all of the implementing classes of the list interface. These are all classes that are parts of the core Java runtime, or the class library. Then I'll click on Method and show the list of all the methods that you can explore to manage ordered data using the list interface and the array list class. I've described how to use an array list to manage an ordered set of data, and now I'll show you how to use a hash map to represent an unordered data collection. Just as with an array list, which implements the list interface, a hash map is an implementation of an interface named map, and typically you'll see code like this. I'm going to declare a collection of states. Each item in a map is a key value pair. The data types of each of these can be anything you want, but frequently you'll see that the key is a string, and then the second value might be a number, a string, or any other sort of complex object. When I select map, I get the import statement. And then, just as with the list, I use the diamond operator to declare the data types of my keys and my values. So I need two data types, and these will both be strings. I'll name my object map, and then I'll initialize it with new, and then I'll use the concrete implementation of the map interface named hashmap. Just as with the generic notation used in array list, I don't have to redeclare the data types of my keys and my values. That's assumed from the original declaration over here. Also, just like with list and array list, I can't directly instantiate a map without implementing all of the code I need. So I'm using a concrete implementation that already exists in the Java class library. Now, in order to add items to the map, I'll call a method of the map interface named put. The put method takes two arguments, the key and the value. In my example, they'll both be strings, and I'll pass in the name of a state and its capital. Now I'll duplicate that line of code a couple of times, and I'll change the keys and the values. And then my second two items will be the state of Oregon with the capital of Salem, and the state of Washington with the capital of Olympia. Then I'll simply output the map object using system out, and I'll run the code. And just as with the list object, the toString method of the object is responsible for the formatting. It outputs a pair of braces, and then each item in the map is separated from the next one with a comma, and then within the item you see the key and the value separated with the equals operator. Next, I'll go back to my code, and I'll add another item to the map. And then I'll output this again. And notice this time that the order of the data is not guaranteed. In fact, if you were to run this a bunch of times, you might see a different order in the second version each time. Now, because each item has a key, you can look it up by that key. So I'm going to create a string variable that I'll name cap, and I'll call map.get, and I'll pass in a value of Oregon. The data type returned by the get method will differ depending on your original declaration. I said this would contain values that were strings, and therefore my get method will return a string. But if I were using some other kind of class, that's what it would return. Then I'll output the string, the capital of Oregon is, and I get back the capital of Oregon is Salem. Finally, I'll describe how to remove an item from the map. I'll call map.remove, and I'll pass in California, and then I'll go grab one of these lines of code that's outputting the map object, and I'll duplicate and move that code, and the last bit of output shows that I still have Oregon, Alaska, and Washington, but California is gone. Java gives you a number of ways of looping through or iterating through collections of data, either ordered or unordered data. I'm going to demonstrate some of these techniques in the project Iterate Collections. I'm starting with an array list, declared at line 13, and it contains 3 items. And at line 19, I'm outputting that list using simple output, passing the object to print line, and that calls the toString method of the object. When I run the application, I get the data printed out with the standard formatting. Now, I'm going to describe how to use something called an iterator object. This used to be the most common way of looping through a collection. You create something called an iterator object, and there's an interface available for this. And notice up at the top that now I have an import statement that says java.util.*. IntelliJ IDEA has decided that I'm using so many interfaces and classes from this package that instead of importing them individually, it's just going to import the entire package. That doesn't affect performance at all. It's simply a way of reducing the amount of code. An iterator is similar to the other collection interfaces in that it takes generic notation, so you can indicate what kind of data you're looping on. I'll say I'm looping on a string. And I'll name this object simply iterator. Then I'll call the list object and its iterator method, and that returns a reference to an iterator object that I can use to loop through the list. In order to loop through the data using an iterator, you'll use 2 methods. A method that returns a Boolean called hasNext that indicates whether there's available data in the object you're looping through, and then another method named next that moves to the next available object and returns a reference to it. I'll create a while loop, and my condition will be iterator.hasNext. Then within the loop, I'll create a string that I'll name value, and then I'll call iterator.next. And then I'll output that string. So this is the code you need. You get the iterator object, then you create a loop, and within the loop you get the reference to the object, and you do whatever you need to do with it. And when you run the code, you get the output. You can also loop through an array list using a for each statement. I'll create a for loop, and within the for loop, I'll create a string, I'll name it value, and then after a colon, I'll say I'm getting the data from my list. And within the list, I can output the value. And there's the result. It's exactly the same output, but I don't need the additional object that the iterator requires. So it's a little bit more memory efficient and takes less code. And finally, another technique was introduced that you can use for this in Java 8, called method references. I have a loop containing strings. And let's say I have a method of some object that's accepting a single string argument. I can simply say, use this method, and the compiler takes care of everything else. I'll call list.forEach. Now be warned, this method only exists in Java 8 and later. It doesn't exist in Java 7, and it doesn't exist in Android's version of Java. Next, I'll pass in a class that has a static method I want to use. I'll call system.out. Then I'll put in a pair of colons, and then the name of the method I want to call, println. Now the logic is, the println method accepts a string. I'm passing the object, and the compiler says each of the items in the list is a string, so it then calls the method for you and passes the string in. I'll run that code, and again I see exactly the same output. In Java 8, this is unquestionably the most efficient, not just in terms of performance, but in terms of the amount of code you have to write. You can also loop through unordered data. I'm going to uncomment the rest of this code, and now I have a map containing 3 items. Each item has a key and a value. And if I run the code, I get an output of the data using the default formatting of the toString method of the list interface. But now, I'll use a hash map iterator. First, I need to get a set of keys. A set is similar to a list in that it contains ordered data, but it guarantees uniqueness. and that's not something that an array list will do. I'll create a set, and I'll set the data type of the items in the set as string, and I'll name it keys. Then I'll call the method map.keySet. The keySet method returns a set, and now I have a unique set of keys that I can use to reference the items in the map. Next, I'll create an iterator. Once again, I'll set the generic data type as string, and I'll name this one iterator1, and I'll call the method keys.iterator. Next, I'll use a while loop. My condition will be iterator1.hasNext, and then within the loop, I'll create a string. Then I'll call iterator1.next, and now I have the current key, and then I'll output the capital of, and then I'll append the key, then another literal string, and then the value with map.get, and I'll pass in the key. So using an iterator on a hash map takes a bit of code, but it absolutely works. And I see the output of the three states and their capitals. And just like an array list, you can use a for each loop on a map. I'll use that same set of keys, and this time I'll create a for loop, and then within the parentheses, I'll create a key variable, a string, and I'll get its value from the keys collection. And within the loop, I'll output the same value. I'll just copy and paste this bit of code. And there's the result. So you have iterators, you have for each loops, and in Java 8, you have method references. You can use any of these three coding strategies to loop through or iterate through a collection of data. Java is an object-oriented language, and one of the most important principles of object-oriented programming is encapsulation. Encapsulation means that you're packaging complex functionality to make it easy to use. When you first create Java applications, most new programmers will put all of their code into the main method, and I've been doing that so far in this course. But you quickly find out as your applications get larger and more complex that putting all of the code into one place makes it very difficult to manage. So instead, you want to break the code out into individual classes, grouping the functionality as the logic dictates for your application. This gives you some great advantages. For example, not all functionality should be available to all parts of an application, and encapsulation lets you restrict access as needed. Each class can be placed in a particular package, and within the class, methods can be marked as public, private, or protected, so only those parts of the application that should be able to call a bit of functionality can get to it. Each of those methods can then hide complex functionality. Not all developers on a particular team will probably know everything about a particular application. Everyone has their own area of specialization. So, a developer who knows a lot about, say, file I/O can write methods that deal with writing and reading files on disk, and then can publish the API or the programming interface for those methods, so other programmers can call the methods. They can get all of their work done, but they don't need to know everything about how it's being done in the background. And this hiding of functionality goes to data storage too. When you encapsulate data access, you're essentially hiding the mechanism by which the data is stored. So you might store data, say, in XML files when you first create an application, and you create methods to read and write that data. But then later, you decide to change to JSON format. If you've successfully encapsulated that functionality, the reading and writing of the files, then other parts of the application can still call those methods, and the inner storage mechanism can change, and it can reduce the risk of breaking the application. One way to think about encapsulation is to look at a real-world analogy. Let's take a look at an example of an industrial machine, in this case an olive press. In order to use an olive press, if you were asked to know everything about how the press worked, it might be difficult to get started. If you had to know which direction each gear was going to turn, which order each of the pressing arms is going to come down, and how much oil might come out of each individual olive, you might not be able to get any work done at all. So most real industrial machines are encapsulated. That means that they wrap up and hide their complexity in a big box. With an olive press, you can simply add the olives, maybe press a button, and out comes the olive oil. It's much easier for a new user or programmer to understand how to use the olive press. There's still complexity, there are still gears, and there are still pressing arms, and there are still calculations to be done. But getting started with the machine is greatly simplified. Code encapsulation works the same way. Let's take a look at non-encapsulated code. If you're a new Java developer, you might be tempted to put all the code for the application in the main method of your primary class. In this example, I'm creating an array of olive objects, and then I'm looping through the array and doing something with it. I have to create an object named oil, an object named press, and then I have to use a for each loop. I then have to call a method and do something with it. Now, this little bit of code might not look too daunting, but imagine if the code expands, so you have literally hundreds or thousands of lines of code all in one place. Then somebody comes along and says, "Would you add a new feature to the application?" Or, "I found a bug and it needs to be fixed." This sort of monolithic code is very difficult to manage. So in Java applications, you're encouraged from the beginning to break your applications down into smaller pieces. So for example, I might take some of that code and move it into its own custom class. This is a class called the olive press. It has a constructor method, a method you call to create an instance of the class. And it has a public method named getOil that executes some code and returns the result of a calculation. That calculation might be in this method, where it's doing exactly the same work as before. It's creating the olive oil object, it's looping through the array of olives and doing something with it, and returning the oil. Then, to call the code, it's incredibly simple. At the top level, you simply create the olive press object, you pass in your array of olives, and then you call the getOil method. It's the equivalent of pressing the button on an industrial machine. When you call the top-level method, you don't need to know what's going on inside, and that code could be the responsibility of an entirely different programmer. Object-oriented programming can make working in a development team much easier and maintenance of the application much more successful in the long run. So that's how encapsulation works. When you encapsulate your code in classes, you're breaking the functionality down into small maintainable units, and you're grouping functionality, that is, methods, and data together, and wrapping it all up in Java classes that you can then create instance of, call methods, access and modify the data, and so on. It's much easier to fix bugs when you're looking at a small amount of code, and much more difficult when you're looking at a massive amount of code. And breaking things down into small pieces also makes it easier to test. You can do something called unit testing, where each class is a unit, and you're testing to make sure that class does what it does without all the complexity of the larger application. Rather than looking at your application as one huge block of code, you're breaking it down into small, manageable pieces. So in the rest of this chapter, I'm going to talk about the mechanics of this in Java. How do you create your own custom classes? How do you move code from a monolithic application and break it down into smaller pieces? How do you declare classes that serve as utility libraries? That is, libraries of public methods that you can call from anywhere in an application. Or how do you create custom classes that can serve as data containers, but have all the functionality they need to manage and maintain that data for you when all you need to do is call a simple method? In this project, Create Class, I'm going to demonstrate breaking code out to a separate class. I'm working with a version of my calculator application. It allows the user to type in 2 numeric values and select a math operation. The code to collect data is in the getInput method. It's called 3 times. And the code to do all the math operations is down here in 4 separate methods. Now let's take a scenario where I need to break out these methods to a separate class to make it easier to call them from multiple places in the application. My first step will be to create a new class. I could put the class in the same package as before, com.example.java, but one very common practice is to create sub-packages for special parts of the application. So I'll start by creating a new package. I'll right-click on the base package, com.example.java, in the project window, and I'll choose New, Package. And I'll enter a new package name of Utilities, and click OK. That creates a secondary package. Now, if I right-click on that and choose Show in Explorer or Show in Finder on Mac, I'll see that this Utilities package is now a sub-package of com.example.java. And that's where I'll create my new class. Now I'll right-click on the new package and choose New Java Class. And I'll name my class Math Helper and click OK. I'll get rid of this automatically generated comment and then make a little bit of space inside the class declaration. Now I'll return to my main class, calculator.java. I'll select my 4 methods that are doing the math. I'll cut them to the clipboard. I'll go to Math Helper, and I'll paste. Notice that the name of the class and the names of the methods are currently dimmed out. That's a visual indicator that these are not being used in the application yet. So far, so good. Now I'll come back to calculator.java, get rid of a little bit of extra white space, and then I'll come back up here to my call to add values. My goal is to be able to call add values from the Math Helper class. I'll type in Math Helper and a period, and I see immediately that Math Helper can't be found. So I'll hold down the Alt or Option key and press Enter, and that adds an import statement at the top of my code for my Math Helper class. Just like the classes in java.util, I have to import this class because it's not a part of the same package that my main class is in. But I still have a problem. Now I'm being told that add values, that's the method I'm trying to call, is marked with private access in the Math Helper class. The code I copied from my main class has the keyword private on all 4 methods. That means the methods can only be called from within this class, and that's definitely not what I want. So I'll go through all 4 and change private to public. You can do it manually just by retyping, or you can place the cursor on the line and press Alt or Option and then Enter and choose Make Public. And that's a little bit faster, so I'll just go through and do that for all the rest of the methods. Now this class and its methods can be used. And notice immediately I'm shown that add values is now being used. And if I come back to Calculator, I see that the error on that call is gone. So now I'll select the name of the class, Math Helper, and the dot, and I'll copy and paste that into place on all of the other method calls. I'll then go back to my project window and look at my problems view. And it tells me nothing to show. So that means all of my syntax errors have been taken care of. And I'm ready to test again. I'll run the application, and it's compiled and ready to run. I'll type a number of 5, and a number of 4, and a minus for subtraction. And I get back a correct answer of 1. My main class is now much shorter and easier to navigate. My Math Helper class is very easy to use, and I can now use it from anywhere in the application. So that's the first level of encapsulation, breaking methods out into their own libraries so that the code can be called from anywhere. I've previously described how to create custom classes that are libraries of methods that you can call from anywhere. For example, this Math Helper class is defined in a file named mathhelper.java, and it's public, and all of its methods are public. But you can also define classes that are nested within other classes, and those classes are only available to their parent classes. I'm going to start by refactoring or modifying this code. I'm going to take all the code within the main method and extract it to its own separate method. And I'm going to turn this class file into something I can create an instance of. I'll select all that code within the braces. Then I'll go to the menu and choose Refactor, Extract, Method. I'll name my new method calculate, and I'll change the access modifier to protected. That means that this class can be used by any other class in the same package. I'll click OK, and that creates the new method, but it also adds code to call the method from within the main method. Now, instead of calling it that way, I want to create an instance of the calculator class. So I'm going to place the cursor right here and create an instance of the class. I'll declare the data type calculator, I'll name it calc, and I'll instantiate it with new and the constructor method. Notice that there is no explicit constructor method defined in my code, but that's okay. The Java compiler creates a no arguments constructor method for me. Then to call the method, I'll say calc.calculate. And to make that possible, I'll take this static keyword and get rid of it. So now, instead of a static method, calculate is an instance method, a method that now must be called from an instance of the class, instead of from the class definition itself. So far, so good. I should now be able to run the code, and it should work exactly the same way it did before. I'll type in values, and I'll choose an operation, and everything's working. Now I'm ready for a nested class. I'm going to take this last bit of code, the getInput method, and wrap it inside its own class. I'll place the cursor above the method declaration, and I'll start with the keyword class. Then I'll name this input helper. This is a class, and so the initial character is uppercase. Now I'll take this method, and I'll cut and paste it, and place it inside the class declaration so it's a member of that class. Then, just as I did before, I'll get rid of the static keyword. GetInput is now an instance method of the input helper class. And again, this class is only available to the calculator class because that's where it's defined. Now I'll come back up here to where I'm calling the getInput method. Notice that that method is currently not accessible. So I'll place the cursor above those lines, and I'll create an instance of my input helper class. I'll name it helper, and I'll instantiate it with new input helper. Then I'll add helper dot to the beginning of each call to get input. I'll go to my problems view and make sure that all of my syntax errors are gone, and I'll test again. And once again, everything's working just fine. So this code has now been redesigned or refactored. GetInput is now a method of the input helper class. It's marked as private, but it's declared in the same code file as the calculator class, so I can still call it from here. For Android developers especially, it's critical to understand nested classes. They're used a lot in the Android SDK. But for all Java developers, it's a great tool for building well-designed, easy-to-manage code. Before I continue working with the actual programming, I'd like to show you a little bit of visualization of class relationships, the relationship between a main class and a helper class. In this project, Class Relationships, I've changed the location of the class files. I've eliminated the packages, and I've placed both class files, Calculator and Math Helper, in the root folder of the project. The Calculator class is here, and I'll open it in a generic text editor and show you that there is no package declaration at the top. And the same thing is true for Math Helper. With no package declaration, it means that both classes are at the root of the project. Now, to visualize the relationship between the classes, I'll open BlueJ, the other development environment I suggested you install at the beginning of the course. And then I'm going to import that project. I'll select Project, Open Non-BlueJ, and then I'll navigate to my desktop, then to Exercise Files, Chapter 9, 904, Class Relationships, and I'll open it. Notice that when it's imported into BlueJ, BlueJ draws a line between the Math Helper class and the Calculator class. You can open either of the classes by double-clicking, and you'll open it in BlueJay's editor, which does a great job of visualizing the separations between the different methods. This is the Math Helper class, and this is the main Calculator class. BlueJay can help you not just describe the class relationships, but also create them. So for example, if I wanted to create a new class that was outside the calculator, I could click New Class and type Input Helper, and I'll put it down here. Now I'll go back to the calculator class, and I'll scroll down here, and I'll grab the code from the nested Input Helper, and I'll cut it to the clipboard. And then I'll completely delete the class declaration. Then I'll come back to my new Input Helper class. I'll delete all these comments, and I'll get rid of all the other internal code within the class that was generated. And then I'll paste that code in. And then I'll change the access modifier from private to public. I'll come back to my diagram, and I see a new arrow has been created, indicating that Input Helper is being used. I'll go back to my calculator class, and now the calculator class is getting the Input Helper from that external class. If that relationship didn't already exist, I could create it by clicking on one of these buttons, and specifically this one labeled Insert a Uses Relation. So BlueJay offers a very simple relationship diagram using a modified version of UML, Unified Modeling Language. It lets you see the relationships between different classes, and as you drag classes around the screen, it redraws the arrows so you can easily visualize the relationships between the classes in your application. I won't continue with this version of the project only because BlueJay doesn't have great support for packages and also doesn't help you auto-complete your code the way a real IDE does. But it does have this great class visualization feature. When you create a custom class, you can design it to encapsulate data using instance variables or fields. I have a main class, and I'm going to create a new class in a new package that I'll name Model. I'll right-click on my base class, com.example.java, and choose New Package. And I'll name the new subpackage Model. I'm naming it this because this is a common bit of Java vocabulary. A model class defines your data model. Now I'll right-click on that new package and create a new Java class, and I'll name it Olive. My goal is to create my encapsulated olive press system. Each instance of my olive class will represent a single piece of fruit, a single olive, and so I'll need to represent its name, its color, and the amount of oil it would yield when crushed in an olive press. I'll define these values as fields of the class. I'll start with a public string, and I'll give it a variable name of simply name. Then I'll create another public string, and I'll give this one a type of long, and give it a name of color. And finally, I'll define a public integer, and I'll name that one oil. Now, for this first version of the application, each instance of the olive class will have the same values. So I'm going to give this one a name of Kalamata. That's one kind of olive. And I'll give it a color of 0x2E0854. That's indigo, which is a dark purple and approximates the color of a Kalamata olive. And I'll set the amount of oil that I get from a single olive of the Kalamata variety at a value of 3. So now my class is ready to use. I'll just get rid of this comment that was generated, and I'll come back to my main class. Within my main class, I'll create an array list that will contain all of the olives I want to crush. I'll declare an instance of the list interface, and then I'll set the type of the members of the list as olive. Notice when I select olive that an import statement is added for that class, because it's in a different package. I'll name my list olives, and I'll instantiate it with new array list. Just as before, I don't need to redeclare the type of the objects that are referenced in the list. Next, I'll declare one of the olives. I'll set the data type as olive, and I'll name it olive1, and I'll instantiate it with new olive. As I described previously, this class does not have an explicit constructor method, but that's fine, because the Java compiler creates it for me. Then I'll add the olive to the list with olives.add olive1. Now I'll select and duplicate this line of code 3 times, and then I'll change the names of the olive variables to olive2 and 3, and I'll change them here as well. Now notice I declared all 3 of these instance variables or fields as public, so I can set and get their values without any other special code. So next I'll add a for loop, and I'll loop through the collection of olives. I'll declare a variable, data typed as olive, and I'll just give it a name of O, and I'll iterate through the olives collection. Then I'll output the name of the olive with O.name, and the result is that I have 3 Kalamata olives in my collection. Now I'm also going to create one more class before I'm done with this step of the process, and this will be my olive press class. I'll place this in my base package. I'll create another new Java class, and I'll name it olive press, and then I'll create an instance method, a method that's a member of the olive press class. This will be a public method, so it can be called from anywhere in the application, and it'll return an integer. Its name will be getOil, and it'll receive an argument, a list of olives. If you see this message indicating that the list interface isn't recognized, place the cursor back on that line and press Alt or Option and the Enter key, and that should add the required import statement. Now for the moment, I'm just going to return any integer value, just to make sure that the code is working. Then I'll come back to my main class, and I'll take this for loop, and I'll cut it from the code. I'll move back to the olive press class, and I'll paste the code right before the return statement. I'll come back to the main class. Now I'll create an instance of the olive press class. I'll declare its type, and I'll name this one press, and I'll instantiate it with new olive press. Then I'll call press.getOil, and I'll pass in my olives collection. So now the olive class contains the string, the name of the olive. The olive press class has a method that can process the data, and the main class is creating the data and passing it to the olive press for processing. I'll run the code, and the result looks the same, but now I've separated the code out. I have a model class, olive, to contain and manage the data directly, and an olive press class to do the processing. In the next steps, I'll fine-tune my code a little bit more, following some best practices of Java development. As I've previously described, when you create a method that's a member of a class and you don't include the static keyword, that means it's an instance method, a class that's designed to encapsulate data, such as my model class, named Olive, typically will have instance methods known as setters and getters. The getter is called the accessor method, and the setter is known as the modifier method. If your class already has instance variables, your IDE typically will be able to generate the setters and getters for you, and IntelliJ IDEA does this well. I'll make a bit of space below the variable declarations, then I'll right-click and choose Generate. And from the menu that appears, I'll choose Getter and Setter. Then I'll choose all 3 instance variables and click OK. And that generates public methods. They all start with the words get or set and finish with the variable names. Getters simply return the value, and setters receive an argument. Notice within a setter method, the keyword this is used to distinguish the variable that's a member of the instance from the argument, which has the same name. So I'm taking the argument, and that's the reference to it, and I'm assigning it to the instance variable. Now just for fun, I'm going to change the name of this method, getOil, to crush, because it's going to return the amount of oil that this particular olive yields. And then, so I can track what's going on, I'll add some output code, and I'll output the word ouch which is what an olive says when you crush it. Now I'll come back to the olive press class. Within the olive press class, I'll declare an integer value, and I'll name it total oil. I'll initialize it to a value of 0. Then within the loop, for each olive, I'll extract the oil from the olive by calling the crush method. I'll say total oil plus equals o.crush. So that's going to return the value, and it's going to output the string that I commanded it to. Then I'll change the return statement so it's returning the total oil. I'll come back to my main class. Within the main class, I'll declare an integer variable, and I'll assign it the value from the call to the getOil method. Then I'll report the total olive oil that was extracted with total olive oil plus total oil. For each olive, I'm outputting the name of the olive, and I see the message ouch as the olive is crushed, and then at the end of the process, I see that the total olive oil is 9. But let's make some changes. Let's say that we have different sizes of olives. So for each of the olives, I'm going to set the explicit amount of oil. Here I'll say olive2.setOil, and I'll give it a value of 1. That's a really small olive. And then for this one, I'll call olive3, and again I'll call setOil, and I'll pass in a value of 4. That's a slightly larger olive than the norm. And I'll run the code again. And this time my total olive oil is a little bit less, 8. So now all the work is being done by the olive class, which tells the rest of the world how much oil the olive has, by the olive press that knows how to process the oil, and the olives are actually being created and given their oil values by the main method. We're using instance methods and instance variables to manage the data. To fully encapsulate this and make sure no other part of the application can get to this data without going through the methods, I'll change all 3 of these instance variables to private. And now the only access to them is through the getters and the setters. When you create an instance of a class, you typically call its constructor method. In this code, in the project constructors, I'm calling the constructor method 3 times, creating 3 instances of the olive class. But my olive class doesn't have an explicit constructor method declaration. That's because of a specific compiler rule. If a Java class doesn't have an explicit constructor, the compiler creates a no-arguments constructor for you. But the other part of the rule is that if you have a constructor that does receive arguments, then a no-arguments constructor won't be generated for you. If you want it, you have to explicitly declare it. You can have as many constructor methods as you want, as long as their signatures, that is, their data types or the number of their arguments, differ from each other. So I'll make some changes to my olive class. I'll start here, right after my declarations of the instance variables or fields. A constructor method starts with the public access modifier. Then you don't need a return value, and the name of the constructor method always matches the name of the class. So this is my no-arguments constructor. Notice I'm declaring it all on one line, because I'm not going to have it actually do anything. It's just there to satisfy the compiler's rules. Next, I'll declare a constructor that accepts 3 arguments, 1 for each of the instance variables. Once again, the name of the method is olive, but this time the 3 arguments will match the data types and the names of these variables. And I'll just copy and paste them into place. That's the first variable and argument, name, and then color, and then oil. Now, when this constructor method is called, I'll take the values that are being passed in, and I'll save those values persistently in the instance variables. To distinguish between the argument names and the instance variable names, I'll start the instance variable names with the prefix this, meaning the variable that's a member of the current instance of the class. So this.name equals the argument name, and this.color equals the argument color, and this.oil equals the argument oil. So those are my constructor methods. Now I'll come back to the main class, and I'll modify the way I'm constructing the objects. For the first olive class, I'll pass in columnata, and my next value is long, and that'll be that dark purple I used before, 0 to E, 0.0854, and the final value is the amount of oil that this olive will yield. Now I'll make a copy of this, and I'll overwrite my other assignments, and I'll change the variable name so it's all consistent. But this olive will have a name of Ligurian, another olive varietal, and it'll have a color of black. That's 0x and then 6 zeros. And I'll say that that's a pretty small olive. It only yields 2 units of oil. Now at this point, I no longer need the calls to the set oil method. I'm setting those values as I create the objects, the instances of the oil class. So I'm adding 2 Kalamata olives and 1 Ligurian. I'll check my problems view and make sure I don't have any syntax errors, and then I'll test the code. And there's the result. I have 2 Kalamatas and 1 Ligurian and a total olive oil yield of 8 units. But now I'm going to clean up my code a little bit and make it a little bit easier to read. For each olive object, instead of creating the object on one line and then passing it in on the next, I'll combine the two into a single statement. I'll take this constructor method call, and I'll cut it to the clipboard, and I'll paste it here. And now I no longer need that line of code. I'll duplicate that line of code and delete these, and then I'll do the same cut and paste operation to pass the new olive object into the olives array list without having to assign another reference variable. Now, I haven't reduced the number of objects that I'm creating. I've only reduced the number of reference variables that are pointing to them, but it's cleaned up my code quite a bit. And I'll run the code again, and I see exactly the same output. But now I can duplicate these lines of code, so now I have 4 Ligurians and 2 Kalamatas, and I can run the code, and I get a whole bunch more oil. And again, all of the processing of the oil is all in the olive press class. Many programming languages support the concept of a constant, a variable whose value can't be changed. There is a const keyword in Java, but it's not currently implemented. Instead, Java developers create constants using the final keyword. Final, when applied to a variable, means that its value can only be set once. I'm going to demonstrate this in the project constants. Right now, in my main class, I'm setting the names of my olives with simple strings. That works fine, but it's problematic because it's easy to misspell it and to be inconsistent. So I'm going to add constants to the olive class, one for each type of olive I want to support, and then I'll refer to those constants in my main class. I'll place my constant declarations at the top of the olive class. Each of the constants will be public and static, so I'll be able to refer to the constant from the class declaration, and it'll be final. And it'll be a string. There's a strong naming convention for constants. They should always be in all uppercase. And then I'll set the value of the constant to the name of the olive. Now that I've set the constant, I can replace it here as the default value for this olive class. Because the compiler now recognizes it as an identifier, I can type the first character and then IntelliJ IDEA will autocomplete it. Now I'll go back to the main class, and I'll look for all references to the Kalamata string, and I'll replace them with the constant. With olive, dot, and I see Kalamata. And I'll do that for both Kalamata olives. Now I'll go back to the olive class, and I'll duplicate this line of code, and I'll change the name of the constant to Ligurian, and change its value to the actual name. Then I'll come back to the main class. This time I'll just do a search and replace. I'll select and copy the literal string, click anywhere so I don't have anything selected, then I'll go to the menu and choose Edit, Find, Replace. I'll search for Ligurian, and I'll replace it with olive.ligurian. And replace all. And there's the result. The processing and the output is exactly the same as before. The difference is in the ease of use and in the robustness of my code. Because I'm now using the constants, I now can't misspell the strings so easily. And if I did originally misspell something, it only occurs now once. in the declaration of the constant, and it's easy to fix. So again, constants can help you solve a number of programming issues. They can help eliminate the errors that literal strings are prone to, and they can help you code more quickly. I've previously described how to standardize values using the static and final keywords. These are Java's versions of constants. But you can also set up enumerations, lists of possible values that you can use for any particular variable. An enumeration in Java is called an enum class. You can create an enum class either in its own separate code file or as a nested enum if it's only going to be used in one Java class. I'm going to create an enum class in the enums project, and I'll place it in the model folder, the same folder that contains my olive class. I'll right-click on that folder and choose New, Java Class. I'll set the name of the class to olive name, and I'll set the kind of class to enum, and click OK. And notice that the big difference is in the keyword that identifies the file. Instead of class, this is an enum. Now, I'll set up the possible values as a simple list, separating the values with commas. Just as with constants, the naming convention is to use all uppercase. And I'll finish the list with a semicolon. Now I'll go back to my main file, and instead of using olive.kalamata, I'll use olivename.kalamata. Notice that I'm getting an error, and that's because the olive constructor is looking for a string, and now I'm using an olive name enumeration. So I'll go back to my olive class and make some changes here. First, I'm going to get rid of these constants. I won't need those anymore. And I'll change the data type of my name variable from string to olive name. The enum becomes a type of its own. Then I'll change the value that I'm assigning to olivename.kalamata. And that gets rid of the syntax error. Next, I'll go through and change the types wherever I'm referencing the name variable. I'll change the type here in the constructor method. Again, that will change to olive name. And I'll do the same thing in the return value of getName and in the argument that's passed into setName. I'll look for any remaining problems, and I find one in my main class, and I see that my reference to olivename.kalamata is working fine, but now, because I got rid of those constants, all these other references are broken. So I'll do a search and replace. I'll search for olive dot and replace it with olivename dot. I'll look back at my problems view and see that I've gotten rid of all my syntax errors. And I'll run the code. And everything seems to be working fine. But notice now that the values that are being printed out are all uppercase, because they're automatically matching the names of the values in my enumeration. So here's how you can fix this. In order to translate the identifier of the enumeration value into a string, declare a string variable. Make it private to the enumeration. I'll call it name. Then create a constructor method for the enum. A constructor for an enum can only be called by the enum itself, so you can't put the public keyword on it. And I'll set it up to receive a string that I'll call name. And within the constructor, I'll save that value to the current instance of the enum. Now, to associate the identifier with a string, I'll place the cursor after the identifier declaration and put in a pair of parentheses and pass in the literal string I want this to translate to. And I'll do that for both Kalamata and for Ligurian. So far, so good. But now, whenever this instance of the enum is output to the console, I want this string to be displayed. And to do that, I'll override the toString method. Every Java class and enum has a toString method. The default toString method of an enum simply translates the identifier. To override the method, I'll start typing the name of the method, and then I'll select toString from the list that appears. That creates an override of the toString method, and I'll change the statement to return the name variable. Now, whenever the object is passed to a method that's expecting a string, my version of toString will be called instead. I'll run the code again, and there's the result. I'm now seeing my version of the string instead of the identifier. So that's how you can use an enum to standardize your values. One of the advantages of an enum is that if you decide to add another value later on, you only have to do it in one place, in the enum itself. And if you need to change the way a particular identifier translates to a string, again, it occurs in only one place. I previously described encapsulation, but there are two other concepts that you need to master to be a great object-oriented programmer: inheritance and polymorphism. Inheritance means that there's a relationship between classes in your application that lets you inherit or extend functionality from one class to another. Not all object-oriented languages are the same. For example, C++ supports multiple inheritance, but in Java, there is only single inheritance. Each class can extend or inherit functionality from only one other class. This actually makes it a lot easier to manage your code. If you run into a bug, that bug can either be in the class that you're working on, or in its direct superclass, or in its superclass, and so on. But the issue has to be somewhere in that very linear path. But Java does allow you to implement multiple interfaces in a single class. We'll get to interfaces later. There are a number of different ways to describe an inheritance relationship, but these are just different vocabularies. Some developers use the terms parent class and child class. The parent has functionality, and the child inherits it. And others use the terms base and derived. In the world of Java, the most commonly used terms are superclass and subclass. The superclass has the original functionality, and the subclass is inheriting it by extending it. Polymorphism means that an object can either be addressed as either its supertype or its native or subtype. Let's take the example of list and array list. List is an interface. Array list implements the interface. This is a similar relationship to a superclass and a subclass. I can declare an object as a list, but then instantiate it as an array list. It is an array list, but it's also a list. And the same is true of super and subclasses. So you can write methods that accept the supertype as an argument, and then you can take an object that's natively an instance of the subtype and pass it into that method. And this allows you to create code that's highly flexible and very, very reusable. You can think of a method that accepts a supertype as an argument as a contract of a sort. It's saying, as long as this object extends this superclass, I'll accept it, because that's a guarantee that the subclass will implement the functionality that I'm looking for. This is known as contract-based programming, and it's something you get with the inheritance model of Java. Let's take a look at a visualization of an inheritance relationship. This is an olive class. Now, this class doesn't explicitly extend any other class, but that means that it implicitly extends the object class. And that's why it has methods like toString. The toString method is originally implemented in the object class, and then the olive class inherits that method. It can override that method and create its own custom version, but if it doesn't, you can call the toString method as a member of the subclass. The olive class is also a superclass. It has 4 subclasses in my example, and they're all subclasses of olive. So the Kalamata class can call methods of the olive class, but it can also call methods of the object class. The olive class is the superclass in this relationship, and the 4 classes at the bottom are the subclasses. Here's a bit of code that describes how these might be implemented. The superclass doesn't need any special code. In fact, as long as you haven't marked a class as final, it can be extended. It can have subclasses. And all of its members, that is, its fields and methods, can be inherited also, unless they're marked as private. The most common practice is to mark fields as private, and then create setter and getter methods and mark them as public or protected. and to create other custom methods as needed and mark them as public or protected to allow them to be called from other places in the application. Here's an example of a superclass. The class is named Olive, and it's public, and it's in the Olives package. It has a couple of private fields, and it has 3 public methods. And then the public class Kalamata extends that class. If you create an instance of this class, you can call the public methods, but you can't reach the private fields. So, in the rest of this chapter, I'll describe different ways of implementing inheritance in Java and using polymorphism in your applications. And I'll also talk about interfaces and abstract classes, more advanced aspects of Java that let you implement inheritance in different ways. So now I'll demonstrate creating and using subclasses of a superclass. I'm working in a new version of my project named Extending Classes, and I've refactored it a bit. Notice in the main class that instead of passing in a long value as the color, I'm instead using a new enumeration named olive color. To jump to the enum, I'll hold down the Control key on Windows or the Command key on Mac and click the name of the enum, and that opens that file and jumps to the declaration. This enum has 3 options, purple, black, and green, and they each have associated names and long color values. The constructor method receives both values and saves them, and the toString method returns just the name. So now my goal is to refactor my code. Instead of passing in an instance of olive and explicitly setting the name, color, and amount of oil each time, I'll have a special subclass for each type of olive, and that subclass will already know those values. I'll create these subclasses in the model package. I'll right-click on the model package and choose New, Java Class, and I'll set the name of the class to Kalamata, and click OK. Now, to make this a subclass of olive, I'll add the extends keyword and then select the olive class. I'll get rid of this comment, and notice initially that I have an error. It tells me there is no default constructor available in the olive class, and that's because I removed it. By default, the subclass is expecting there to be a no-argument superclass in the subclass, but it doesn't exist. So I need to create it explicitly here. I'll create a constructor specifically for this subclass, and it'll receive no arguments. And that makes the error go away. But now I have a new error. It's also telling me there's no default constructor available. But that's okay, because I want to call the version of the constructor that accepts 3 arguments. And here's how you do it. Use the keyword super, and this is actually a method call. The method is expecting an olive name, an olive color, and an amount of oil. So I'll pass in olivename.kalamata. Then I'll pass in a color, olivecolor.purple, and an amount of oil. And I'll say that all Kalamata olives return 2 units of oil. And that gets rid of all of my errors. Now I'll go back to main.java. Now, instead of creating an instance of the olive class, I can get rid of this bit of code, and this time I'll just say, I want a Kalamata olive. And the Kalamata olive already knows all those values. I'll get rid of the second version of this, and then duplicate the first, and now I have 2 Kalamata olives. Now I'll go through the same process for Ligurian. I'll go to the Kalamata class that I just created, and I'll right-click and copy it to the clipboard. Then I'll right-click on the model package, and I'll paste. IntelliJ IDEA asks me what's the new name of the class, and I'll say it's Ligurian. And that creates a new class named Ligurian that extends the olive class, just like Kalamata. But now it's up to me to change the values I'm passing in. I'll change the name to Ligurian, and I'll change the color to black. And again, we've been saying that Ligurian is a particularly large olive, so I'll set the amount of oil to 5. Then I'll come back to the main class, and I'll do the same sort of refactoring I did before. Instead of creating an instance of olive, I'll create an instance of Ligurian. I'll get rid of these 3 lines of code, and then I'll duplicate Ligurian 3 times. And you can see how much simpler the code is and how much easier it is to read. Now later on, if I decide I was wrong, and Ligurian olives get a smaller amount of oil, I can change it once here. Before I test, I'll look at my problems view to verify I have no syntax errors. Then I'll return to Packages, and I'll run the code. And there's the result. I'm getting 2 units from each Kalamata and 5 units from each Ligurian, and a total of 24 units of oil. I recommend reviewing the code for this entire application because there are a few other minor changes that I made. But the important thing to learn here is that the subclass can contain all sorts of specific information and override the defaults or set specific values that a superclass requires. But it can still use the features of the superclass where it doesn't need to have specific functionality. In object-oriented programming, an interface is a contract. It defines a set of methods with particular signatures, and any class that implements that interface must implement those methods. We've already seen a couple of examples of interfaces, the list and the map. These are parts of the collections framework. In my existing code, I'm declaring an object that's an instance of the list interface, but then I'm using the concrete implementation of that list, the array list. You can find out about these contracts by going to the documentation for the interfaces that are a part of the core Java class library. The list interface, for example, says you must implement all of these different methods in order to be considered a list. And then it's up to each concrete implementation of the interface to write the exact code that's needed for its own functionality. I'll show you here how to create your own interface and then how to implement it. I'm going to create an interface that defines the method getOil, and then OlivePress will implement that interface. I'll place the interface file in my base package. I'll right-click and choose New, Java Class. Then I'll change the kind to Interface, and I'll name the interface simply Press. I'll get rid of the comment, and then make a little bit of space in the interface declaration. Now, I'll come back to the OlivePress class, and I'll select just the method signature. I won't take the entire code block, and I'll copy that, and then I'll paste it within the press interface, and notice that when I paste with Control or Command V, I'm told that there are certain classes that I'll need to import. So I'll accept that, and then I'll add a semicolon at the end of the statement. I'm not implementing the method here. I'm just saying that any class that implements this interface must have this method. The method name must be getOil, it must return an integer, and it must accept a single argument, a list of olive objects. Now I'll come back to the OlivePress class, and I'll click here right after the class name. I'll add the implements keyword and then type in the name of the interface, Press. So far, so good. My contract says that any class implementing this interface must have this method, and this class already has the method. So I can run the code, and everything works fine. But now let's see what happens if I add a new method declaration in the interface. The method will be public, and it'll return void, or nothing, and it'll receive a single argument, an integer that I'll name oil. Now I'll go back to OlivePress, and I see an error now exists, and it tells me that this class must either be declared abstract or it must implement the abstract method setOil. The word abstract in Java means exactly this. You've defined what a method should look like, but you haven't said how it's supposed to do its work. So, in the OlivePress class, I'll place the cursor on the line that's displaying the error. Then I'll hold down the Alt or Option key and press Enter or Return, and I see an option to implement methods. I'll select that, and the dialog shows me the setOil method that's a part of the interface. And I'll accept that, and that adds the method declaration to my implementing class. Now, I'd like this method to be able to do something, So I'll go to the top of the class and create a private field. It'll be an integer, and I'll call it current oil. And then in the setOil method, I'll say current oil equals oil. And so now this method can be used to initialize the amount of oil that the press already has before you call the other method. I'll also change this value, so instead of initializing total oil as 0, I'll say it's current oil. So now to demonstrate the use of the interface, I'll go to line 20 in the main class where I'm creating the instance of the olive press. Instead of setting the type as olive press, I'll set it as press. I'm saying it's an instance of this interface, and that means that I'm guaranteeing that these methods exist. Then, before I call getOil, I'll say press.setOil, and I'll say I'm starting with 5 units. Then I'll run the code, and this time instead of getting 24 units of oil, I got 29, because I started at 5. The important thing here is that I knew I'd be able to call this method from the press interface because this class was promising to fulfill the contract. It's also very common in Java code to see interfaces instantiated directly, but when you do that, you have to implement all the code yourself. For example, right down here, I'll create another instance of press. I'll name it P2, and this time I'll say new press. And watch what happens. IntelliJ IDEA adds implementations of all of the abstract methods of this class. This sort of code is very common in the world of Android. Interfaces are used in Android for event handling, callback methods, and other more advanced Java programming functionality. I'm not going to use this feature right now, so I'll select and comment this out, but it's important to know that if you try to instantiate an interface directly, you'll need to implement all of its abstract methods yourself. When designing an object-oriented, contract-based programming architecture, you can frequently choose between using interfaces and abstract classes. An abstract class is abstract because you add the abstract keyword, and then it can contain a mixture of fully implemented methods and abstract methods. An abstract method is just like a method in an interface. It doesn't have an implementation. It just indicates the method's signature. And then any subclasses of an abstract method must implement that method. In this project, the Olive class is the superclass for two subclasses, Ligurian and Kalamata. I'm going to change this class and make it abstract by adding the abstract keyword after public and before the keyword class. Now that doesn't change any behavior on its own. I'll run the application and show that everything still works. But now I'll declare an abstract method as part of this class. I'll place this new method down here after all the setters and getters, but before toString. I'll set it as public and then put in the keyword abstract. This method will return a string, and its name will be getOrigin. I'm saying that every subclass of this class must declare its own origin, or the country that it comes from, by returning a string value. The Olive class itself doesn't have an origin, so all it's saying is the subclasses have to do this. Now, because I declared this method, I've immediately caused some issues in my application. I'll open one of the subclasses, Kalamata, and show that there's now an error indicator over the class declaration. And I'm told that the class Kalamata must also be abstract, or it must implement the abstract method. I'll click into the method declaration, and I'll press Alt or Option and Enter or Return, and then choose Implement Methods from the menu that appears. In the dialog, I'll choose getOrigin, and press Enter or Return or click OK, and that creates the override of the getOrigin method. For this subclass, I'll return a value of Greece, and that solves the problem for this subclass. I can then look for any other problems by going to the Problems view, and if I don't see anything there, I might try to run the code, but I know that there's still an issue, because Ligurian is extending that same superclass. So I'll do the same thing. I'll click into the class declaration, and I'll use an intention action That's what IntelliJ IDEA calls it when you press Alt or Option and then enter or return. And once again, I'll implement the method. And for this olive, I'll return a value of Italy. Now, to show that this is working, I'll go back to the olive class. And I'll modify my crush method. I'm going to take this string that I'm outputting, and I'll move its declaration to a separate line. I'll create a string named message, and I'll paste in that string. And then I'll pass that value into println. Now, I'll add some text to the message. After the name, I'll add a pair of quotes and a comma space, and then the word from, and then I'll call the getOrigin method. And now I'm putting together the name of the olive, a string, the value from getOrigin, and the rest of my output. And I'll run the code again. And there's the result. Each time I crush an olive, I'm seeing the name of the olive and its country of origin. And notice that the olive class itself is calling the getOrigin method, but it doesn't know what the result will be because the subclasses have that specific information. Abstract classes cannot be instantiated directly. Only their subclasses can be instantiated. So again, they're very similar to interfaces, but they give you a little bit more flexibility. And whether you use abstract classes or interfaces is frequently just a matter of choice by the application designer. In this section of the course, I'm going to describe some practical tasks that most developers need to know how to do, including reading and writing files and communicating over the Internet. I'll start with File I/O. The Java class library, in Java 8, implements two completely separate File I/O systems. The original system that was delivered with the original version of Java back in 1995 and has evolved somewhat since then, and a completely new version that was delivered with Java 7. In this demonstration, I'll talk about techniques that are available in all versions of Java, including Android's implementation, because the newer libraries aren't available in all versions of Java, including Android's. I'm working in a project named Copy File, and this project, in addition to the source files, has a files folder, and there's a file there called loremipsum.txt. I'm going to demonstrate the Java code you'd need to make a copy of this file. Now, you can use any file you want, including a file that might be much longer, but I'll use this short file just to make things go very quickly. I'm starting in an empty main method. And first, I'll declare a couple of strings, one pointing to the existing file and one pointing to the name and location of a file that I want to create. I'll declare a string, and I'll name it source file. And I'll set its value to files/ and then the name of the file, loremipsum.txt. Make sure that you spell the name of this file correctly. Also notice that I'm using a / even though I'm working on Windows. In Java, the / is used as the directory separator on all operating systems. Then I'll declare another string, and I'll name this one target file. And I'll place the file in the same directory, the file subdirectory of this project, but I'll name it target.txt. Next, I'm ready to create a few classes that I'll need. I'm going to be using 3 classes from the Java class library, named FileReader, BufferedReader, and FileWriter. I'll start with the try-catch block. And right after the try keyword, I'll add a pair of parentheses, and this is where I'll declare these objects. I'm using a syntax style known as try with resources. Whenever you declare objects within the parentheses after the try keyword, that means that these objects implement a method named close, or to be more accurate, they implement an interface named autoclosable. All of these objects need to be closed before you finish what you're up to. By instantiating the objects here, I'll allow the Java runtime to call the close methods for me. Now, within those parentheses, I'll create an instance of the class FileReader from the java.io package. When I select the class, an import for that class is added. And I'll name it freader for FileReader. And I'll instantiate it by calling the constructor method, and I'll pass in the name of the file. Notice you can pass in a string or an instance of a class named file, but that would be an intermediate step that I don't need. I'll pass in source file, and that's the file I'm going to be reading. Now, if I were only creating one object, I wouldn't need the semicolon here, but I am going to create more than one closable object. So I'll add the semicolon, and then on the next line, I'll create an instance of a class named BufferedReader. The BufferedReader class has a method named readLine that'll make it very easy for me to read the file one line at a time. I'll name this one bReader, and I'll instantiate it with new BufferedReader, and I'll pass my FileReader object into it. Finally, I'll create a FileWriter class, and this class will be used to create the target file. I'll instantiate it with new FileWriter, and I'll pass in target file. Before I continue with the rest of the code, I'll come down here to the end of the try section, and I'll add a catch block. I'll be very general in the exception handling. I'll just look for an exception object that I'll name E. Notice when I add the catch block, all of the error indicators go away on my declaration of the closable objects. So now I'm ready to actually do the work of reading and writing the file. Here's the logic I'll use. I'll create a while block and I'll set my condition to true. So that means I'm creating an infinite loop, and I'll need to explicitly break out of the infinite loop whenever I want to. Within the loop, I'll read one line using the BufferedReader. I'll create a string, I'll name it line, and I'll get its value with bReader.readLine. If readLine successfully finds text, it'll return that value as a string. Otherwise, it'll return null. So now I'll do a bit of conditional code to find out whether I got a string I can work with. My condition will be line matches the value of null. And if it is null, I'll break out of my while loop by calling the break keyword. But then in the else block, I'll take that string that I read and I'll write it to the target file with writer.write, and then I'll pass in the line, and I'll also pass in a line feed. When you call readLine, you're only getting the text of the line itself. The line feed that separates the lines is ignored, so I need to put it back into my final file. Within my catch block, I'll just add some code to print the stack trace with e.printStackTrace. I'm not expecting any exceptions, but if I do get one, I'll get some help understanding what it is. So, let's read through the code one more time. I'm using the try with resources syntax that was introduced in Java 7, and I'm creating three closable objects, a file reader, a buffered reader, and a file writer. Then, I'm doing an infinite loop and reading one string at a time. If I get to the end of the file, I'll get a null value back and I'll break out of the loop. Otherwise, I'll write that line to my target file. At the end of the loop, I'll just add a little bit of output, and I'll say file copied. And I'm ready to test the code. I'll run the application, and I get the message file copied, but more importantly, I see my target file has been created in the files subdirectory. And I'll open it and confirm that it looks exactly like my original file. So again, this bit of code will work in pretty much all versions of Java, with the exception of try with resources. The try with resources syntax was added in a later version of Java. If you're working in Android, you might not be able to use it, depending on which version of Android you're coding for. And if you're working with an older version of Java, you won't be able to use it either. So instead, you would instantiate these objects within the try block and then close them explicitly by calling their close methods before you finish executing your code. In Java 7, a new I/O library was introduced that greatly simplified a lot of common operations. You can only use this library in Java 7 and later, and unfortunately, at least at this point, it has not been implemented for Android, so Android developers will still need to use those older classes. But I'll show you how to accomplish the same task I did earlier, copying a simple file. In this project, new I/O, I'm once again starting with a file named loremipsum.txt in a files subdirectory of the project. And this time, I'll be able to copy the file with far less code. I'll start in my main method by creating two instances of a class named path. The path class is a member of the package java.nio.file, and it needs to be imported. A path object can point to either a directory or a file. In this case, it's going to point to my lorem ipsum.txt file. To get the reference to the file, I'll use another class named paths. All of the methods of this class are static, and I'll use this one, the get method. The get method takes a series of strings, and it allows you to put together the location and the name of the file without having to worry about slashes as separators. I'll pass in the name of the subdirectory of the project that contains my file, and then as a second argument, I'll pass in the name of the file, lorem ipsum.txt. Next, I'll duplicate this line of code, and I'll change the second version to target file, and the name of the file that I'm going to write to target.txt. And now I'm ready to copy the file. I'll use a class named files. Just like paths, it has a series of static methods that you can use for common operations. I'll select it to add the import statement, and then I'll use the copy method that asks for path objects for the source and the target. I'll pass in source file and target file. And this method also looks for something called a copy option. I'm going to use a class called standard copy option and a constant of that class named replace existing. And that means that if the target file already exists, I want to delete it and create a new version. Notice I have an error indicator, and that's because the copy method might throw an exception. I'll use an intention action, and I have options to either add the exception to the method signature or surround with try-catch. If I choose the first version, that'll cause the I/O exception to be thrown to the method itself, and that would crash the application, but also display an error on the command line. If I want to control the process, I can undo that code, and then once again, I'll use an intention action, and this time I'll say surround with try-catch. And now I have a good try-catch block, and I'm looking for an I/O exception object, and I can write whatever custom code I want to handle the exception here. But other than the try-catch block, I'm executing this operation with just 3 lines of code, declaring the source and the file, and calling the copy method. And I'll run the code, and the application completes, and I see that my target file has been successfully created. If I want to add a bit of output, I would do it here, within the try block, and I'll output to the console file copied. I'll run the code again, and I see file copied, and I'll open the file again to make sure I'm not appending to an existing file, and in fact, I have replaced the existing one. So that's a look at the simplicity of the new I/O library that was introduced with Java 7. Again, it's not available to Java developers who are working in Android, or if you're stuck on older versions of the JDK. But for Java 7, Java 8, and other future versions, the new I/O library makes these sorts of tasks a lot easier. I've previously described how to copy a file using both the original file system that came with the original release of Java and the new I/O libraries that came with Java 7. But there's yet another way to go, using the Apache Commons libraries. Apache Commons is a project that incorporates utilities for many common tasks. The goal of Apache Commons is to take solutions that developers have found and let them share them easily with the rest of the community. For file management, there's a special category called Commons I/O. You'll find all sorts of utility classes here. Now, if you're working with the most recent version of Java, and you can use the new I/O libraries, I recommend doing that. But if you're working with older versions, or you're working under Android, and you want to simplify a lot of these tasks, it's worth looking at these tools. Now, I've already downloaded the files that I need, and I've included what you need in the exercise files. I'll go to the current chapter, to 1103, and I'll be working with this project, Apache Commons, but I've also included this jar file, or Java archive file, Commons IO 2.4, and that's the library that I'm going to demonstrate. I'll go to IntelliJ IDEA, where I've already opened the project Apache Commons. And all I've done so far in my main method is to declare two file objects. This is the file class from java.io. I'm not using commons yet. And in the files folder, I once again have my lorem-ipsum.txt file, my source file. Now, in order to use the library, I'll copy it into my project. I'll go back to Explorer or Finder on Mac, and I'll copy the jar file to the clipboard. Then I'll go back to IntelliJ IDEA, and under the project folder, I'll create a new directory called lib, L-I-B. Then I'll right-click on the new directory, and I'll paste the jar file into place. And when I see the dialog asking me if I want to copy the file, I'll click OK. Then I need to add the jar file to the project's class path. There are a number of ways to do this, but the simplest is to right-click on it, and then go down to the bottom of the menu and choose Add as Library. And choose OK. So you're adding it as a library of the current project. Now, everything in that jar file is available to your project, and when you package the application, the jar file will go with it. You can see the effect of this by going to the menu and choosing File, Project Structure, and then click on Libraries, and you should see the jar file listed there. Now I'm ready for a bit of code, and copying a file using Apache Commons turns out to be just as easy as with the new I/O library. After the declarations of my file objects, I'll use a class named FileUtils. Notice the package, org.apache.commons.io. This class is coming from the jar file that I added to my project. I'll select the class, and that imports it into the project. Then I'll use the method copyFile, and I'll use this version that takes two file objects, a source and a destination. And I'll pass in my file objects. And that's all the effective code I need, but just like with the new I/O library, I do need to add error handling. So I'll use an intention action, and I'll surround the code with a try-catch block. And that's it. Now I'm ready to test the code. And the code runs to completion without any errors, and I see my target file appear in the files directory. I'll double-click it and show that it copied successfully. Now I'll delete it by right-clicking and choosing Delete, and OK. And then I'll go back here to the try block, and as I've done previously, I'll output a string to the console to report the success of the operation, with file copied. And I'll run the code again. And this time I see my message, and I see that the file is copied. So, knowing what's in the Apache Commons libraries can help you enormously. A lot of the common tasks that you might have to accomplish have already been solved by other Java developers, and they've shared their solutions through Apache Commons. Many Java applications have to communicate over the Internet, making requests for content and processing the content after downloading it. I'll demonstrate one technique for doing this with core classes from the Java class library. I'm working in the Internet project, and there's already a constant declared named flowersFeed. This is a URL that points to a static XML file that's located on a remote server. I'll select that string and copy it to the clipboard. Then I'll go to Google Chrome, and I'll paste the string in and request the file. And I'll see that it's a simple XML file with a root element of products, child elements of product, and then more child elements within that. So now my job is to request that file and download it and display its contents for my application. I'll start in the main method, and I'll create an instance of a class named URL. Notice that there's more than one URL class. Be sure to choose the version from java.net. I'll name it URL, all lowercase, and I'll instantiate it using the constructor method, and I'll pass in my constant, flowersFeed. Notice that there's an error indicator, and that's because this constructor method can throw an exception. I'll leave that alone for now, and I'll fix the exceptions after I've done everything else. Next, I'm going to create an instance of a class named InputStream. This is a member of the package java.io. I'll name it stream, and I'll call url.openstream. Then I'll create an instance of something called buffered input stream, and I'll name that buff for buffered input stream, and I'll instantiate that with new, and then I'll call the constructor method for the class, and I'll pass in the stream. I'm almost ready to make my request, but before I do, I'll create a string builder object that will let me collect the data from the request. I'll name it SB and instantiate it with its standard constructor method. Now I'll execute a while loop. As I did once before, I'll set a condition of true, so I'll just keep on looping until I explicitly break out of the loop. Next, I'll declare an integer variable that I'll name data, and I'll get its value with buff.read. The read method goes and gets a single character from the stream. If it gets it successfully, it returns a numeric value. If it's unsuccessful, it returns -1. So next, I'll use an if statement, and I'll examine the value, and if it has a value of -1, then I'll break out of the loop. If the data value isn't -1, then I'll take that data value and interpret it as a single character with this code. First, I'll call sb.append, then I'll pass in the data value. But before I do, I'll recast the value as a char. So the data value will come back as a numeric, an integer initially, but I'll translate it to a character and then append it to the string builder. Once I break out of the loop, I will have successfully downloaded everything from the website. And so at that point, I'll output the results to the console, and I'll pass the string builder object to my println method. Now before I can run this code, I'll need to wrap all of it with a try-catch block. Notice that there are a number of places where I'm seeing error indicators, and that's because all of those spots could generate exceptions. So I'll select all of that code. Then I'll go to the menu and choose Code, Surround With. And I'll choose Try Catch Finally. We've seen try catch a number of times before, and it's effectively doing the same sort of thing as before. I'll run all of this code until I get to the end of the try block. But if at any point I get an I/O exception, the flow of the code will jump into print stack trace. Now, the reason I created a finally block was because I wanted a place to explicitly close my streams. The streams, just like in a previous example, implement the auto-closable interface. But this time, instead of using try with resources, I'm going to model my code so that I can close the streams explicitly. First, I need to make sure that both the input stream and the buffered input stream are visible to the current scope once I get into the finally block. So to fix that, I'll declare both objects before the try. I need to break up the declaration and the instantiation of both stream objects. IntelliJ IDEA makes it easy to do that. I'll click into that line and press Alt-Enter, and then choose Split into Declaration and Assignment. Then I'll take the declaration and I'll move it up above the try block. And then I'll initialize the value of the stream to null. I'll do the same thing for the buffered stream input. Now those variables will be visible when I get into the finally block, and that's where I'll close them. I'll come down here and say stream.close, and then buff.close. Notice, once again, I see possible errors, and so now I'll press Alt-Enter again, and this time I'll just add an exception to the method signature, because it's conceivable that I could hit an exception when I call the close method, but I don't want to wrap all that in yet another try-catch block. By adding the throws clause to the method signature, it means I can run this code safely. I'll go to my problems view and make sure that I don't have any syntax errors, and then I'll run the code. And there's the result. I've successfully downloaded the XML content. From this point, you might parse the XML content using Document Object Model, JDOM, or one of the many other approaches that are available for parsing XML using Java. So that's a look at how to communicate over the web. making requests for content, and then downloading and getting content ready for processing. The Java Development Kit includes the tool named JavaDoc. JavaDoc's job is to extract documentation about your Java application, including information directly drawn from the code, but also from comments that you can put into your code. I'll demonstrate this in this project named JavaDoc. In order to create a JavaDoc comment, place the cursor before a class declaration, a method, or a variable declaration. Then add a comment. A JavaDoc comment starts with a slash and 2 asterisks, and you can create it easily by typing those characters, slash, asterisk, asterisk, and then pressing enter or return. And the cursor will land right there, and you can start typing. So for example, in this position, I might write a whole bunch of information about my application. Along the way, you can include a certain amount of HTML markup. So for example, I'm going to wrap the words olive press with bold tags. And then I'll also wrap the words press olives so that they're emphasized. If you add a JavaDoc comment above a method, IntelliJ IDEA automatically adds a param tag and populates it with the name of the argument, but then it's up to you to add any additional explanation. I'll just add the text, the main method, and then next to args, I'll add an array of string values. Now I'll generate the docs for the first time. The docs will be placed in whatever folder you like. I'm going to go to my project. Notice I'm in the project view, and I'll right-click and create a new directory, and I'll name it Docs. Then I'll go to the menu and choose Tools, Generate JavaDoc. For the output directory, I'll browse and select the folder I just created. I'll type Desktop to get to my desktop, and then I'll drill down to my exercise file folder. That's under Chapter 12, 1201, JavaDoc, and I'll choose the Docs subfolder. The Output Directory slider lets you choose what level of visibility you want to include in your documentation. By default, it's set to Protected, so only public and protected classes would be included. But if you want to include nested classes, you would drag this up to the top, to Private. You can also select certain tags. For example, I'll say that I want to include the author and the version tag. You can also set the locale and add other command line arguments and control the amount of memory that's available to the JavaDoc tool. Then I'll click OK, and after a few moments, my documentation is generated. It's just as fast as I showed you here on screen. Now notice up at the top, I'm getting a message in Internet Explorer, JavaScript is disabled on your browser. You can turn that restriction off, or as I prefer to do, you can actually open the files in another browser that doesn't have that restriction. I'll come back to IntelliJ IDEA, then I'll right-click on the project and choose Show in Explorer, or if you're working on Mac, Show on Finder. Then I'll double-click into my project, and then into my Docs folder. And here are all the files that have been generated. The starting file is the index file. Now these next steps will differ depending on your operating system, but on Windows with Chrome installed, I can right-click and choose Open with Google Chrome. And when they open in Google Chrome, you don't have the JavaScript restrictions. Here's what the documentation looks like. In the top left corner, there's a list of packages. My application has 2 packages, the base package and the model subpackage. And as you click on the packages, you'll see a list of the classes, enumerations, interfaces, and other files that you've created in those packages. You can click into any class to see the documentation about that class. This is an example of a class where the docs have been generated purely from the code. I didn't add any special comments. And notice that the JavaDoc tool has figured out that Kalamata and Ligurian are subclasses of the current class. I can easily click those classes and jump to their documentation. I'll go back to the base package and choose my main class. And this is where I see the comments that I added. Here's the comment for this is an olive press application, and you can see the effect of the HTML tags that I added. And here's the comment for the main method. I'll scroll down to the bottom of the page to the method details section, and here's the additional comment that I added about the args parameter. If you decide to use the JavaDoc tool, you can go through your entire application and add JavaDoc comments to your classes, methods, arguments, and any other members that you think need a bit of explanation. For applications that you want to keep around for a long time that will need to be maintained, the JavaDoc tool is absolutely critical to help you understand later what you were programming today. A jar file is a Java archive, a file in zip format that contains one or more Java classes pre-compiled so that you can run the jar file as a complete application. This is all done using a tool that's included with the Java Development Kit called jar, but you have access to that file through IntelliJ IDEA and other IDEs. I'll describe how to create this jar file using IntelliJ IDEA, and I'm using a project named jar files. This is my internet project. It's a single-class project that makes a request to a web server and downloads some XML content. So I'm going to wrap this up as a package, and then I should be able to take that jar file and move it to any operating system for which there's a valid Java runtime, and it should work exactly the same everywhere. With the project open, I'll go to the menu and choose File, Project Structure. Then I'll click on Artifacts under Project Settings. I'll click Plus and choose Jar, and then from Modules with Dependencies. You can only add one module to a jar file. My project only has one module, so that's what's chosen for me automatically. Next, I'll indicate which is the main class, that is, which class contains my main method and should start the application. I only have one class, so it's an easy choice. I'll choose main. I'll leave all the other settings at their defaults, including the location of a file called manifest.mf. This is a file that will contain the instructions for how to run the jar file. I'll click OK. And then I'll check this option, Build on Make. And that means every time I rebuild my project, the jar file will be regenerated for me. If I have any other Java classes or jar files I need to reference, I can list them here. But again, this is a very simple application with just one class, so I'll leave that empty. And I'll click OK, and that takes me back to my editing screen. Now I'll go to the menu and choose Build, Build Artifacts. And then in the Action menu, I'll choose Build. And then after a moment, I'll look at the Out folder under my project, and I'll see a new subfolder named Artifacts. And that contains another subfolder, and under that folder I find my jar file. Next, I'll run the jar file. I'll move the cursor to the lower left corner, and from the menu that pops up, I'll choose Terminal, and that opens a command prompt. Now, this will look a little bit different if you're running on Mac or Linux, but the idea is the same. You want to navigate to the folder that contains your jar file. So I'll type cd and then out, and then on Windows I'll type a backslash, on Mac or Linux type a /. Then press Tab, and another slash, and Tab again. Then list the contents of the directory. You should see the jar file that you just generated. Now, to run the jar file, type Java, then -jar, and then the name of the jar file. Make sure you spell it exactly correctly. And when I press Enter or Return, that runs the jar file. And the main class, which is marked that way in the jar file manifest, is executed automatically. My request goes out over the internet, and the data comes back. The manifest file looks like this. It's created in a folder named metainf under your source folder. It has a manifest version setting and a main class setting. The main class setting is indicating which class contains your main method and should launch your application. So that's how you can generate your own jar files. There's a lot more to learn about jar files, but I recommend looking at the documentation to see all of the options that are available. Thanks for watching this course, Java Essential Training. The lynda.com library has many more courses that can help you get started building the kinds of applications you want to build. There are courses that are particularly about the language and about the Java class library. If you want to work with databases, say in Java Enterprise Edition, you can watch the course Java Database Integration with JDBC. Or if you need to work with XML in Java, there's a course on that, XML Integration with Java. For developers who want to work with Java EE, building dynamic web applications, you can learn about web services with Building Web Services with Java EE. And for Android, you can get started with the course Developing Android Apps Essential Training, and then learn more about the IDE offered by Google, Android Studio Essential Training. And you can take a tour of building an Android app from start to finish with Building a Note-Taking App for Android. As you learn more about Android, you can take deep dives into particular APIs with Android SDK Local Data Storage that teaches about how to use SQLite databases and local file storage, and building mobile apps with Google Maps Android API v2, where you can learn how to integrate maps into a compelling visual application. All of these courses and more in the lynda.com library can help you leverage your Java programming skills to build the kind of applications you need to build.